Hi, this is David Voss, CCIE 11372, and in this video we're going to cover network design principles. Specifically, in this video, you're going to learn about the design of a Cisco ecosystem. Then we're going to talk about the modern organization, specifically organizational IT architecture and the policy cycle. And then finally, we will talk about infrastructure design considerations. And by the end of this video, you will be well versed in all 5 areas. When building a network, choosing the network hardware and software components must be performed with consideration for design, planning, deployment, and support. All phases have design principles that must be taken into account and which will be covered in this video. Today's modern organizational models try to leverage internetworking power and the benefits of the global internet. The modern approach is different in many ways from the traditional organizational model that was based on an isolated network design. Traditional companies have closed structure and a limited ability to integrate with other organizations and other companies from an IT standpoint, which results in limited access to information. These companies are difficult to both partner and interact with because most of the processes and applications are done internally. Therefore, companies that adopt this model are unable to adapt and take advantage of new technologies. Let me give you an example. If I roll out a network with private leased lines over a specific provider using non-standard hardware such as HP, Juniper, and Cisco, and maybe Dell, and then a variety of protocols such as OSPF and ISIS. When it comes time to merge with a company or connect with a company, I'm not ready to do that unless they happen to support the same technologies in the same areas or the locations. As you can see, how are we supposed to connect with this new strategic partner using our existing infrastructure with the wide array of technology platforms and private lines is very difficult. This is the old way of doing things. These disadvantages created the need for a new modern networking organizational model based on a network design that allows partnership and collaboration with other entities. It also provides a more focused expertise over the products and services vital to a company's business model. The reality is that it's much easier for companies running simply just Cisco with, let's say, OSPF and BGP, and who are already leveraging internet-based technologies to communicate with one another, because the infrastructure that is needed is already in place. As you can see here, because this company leverages internet technologies and standard platforms and protocols, it's very easy to integrate with external entities, whether it's a strategic partner or a customer, anybody you need to communicate with or create private connections to. This can easily be done with the leveraging of internet technologies and standard platforms, which can be implemented with a strong policy governance, which we'll talk about very shortly. The design of an ecosystem must include a scalable and flexible network infrastructure that will be able to leverage enterprise networking and the internet, creating an environment that is highly accessible and collaborative, and that can break geographical boundaries and will promote an efficient integration of all stakeholders. The modern organizational model includes the following 4 entities: employees, who consume HR information, data about such things as benefits and job openings, stock reports, schedules, or even expense reporting. These all depend on the corporate intranet. This intranet provides instant access to all of the most recent information and services and application updates used by the employees. The customer-related aspects of a company are online support, technical support, or providing different types of customer services. Depending on the situation, customers might need to access some of the company's resources, for example, opening a support ticket. The vendors and suppliers are involved in the process of ordering, billing, and delivery of the products the company uses. These processes can be very time and labor intensive So organizations can leverage their existing internetworks to create links to their suppliers and vendors, which lowers costs per transaction. Strategic partners work to create strategic relationships in order to leverage resources and services to complete in-house expertise and skills. This modern organizational model applies to small, medium, and large companies. Designs that support this model are built around a modular architecture that uses technology consistent with the needs of the organization and allows companies to have a network infrastructure that is better suited for scalable applications. Now, when discussing the architectural components of the network, the architecture that Cisco recommends is divided into multiple layers, which make the processes in the organization easier to expand, implement, and scale. So let's go ahead and cover those now. Applications and services comprise the top layer and include organizational goals. Applications and services offer a concrete set of functions that can be accessed by the network, but only by authorized users. This layer also includes productivity tools, such as word processing, databases, and email. The next layer is intelligence solutions, and then there is structured data and business logic. These comprise this middle layer. These elements make the modern network much more intelligent and help support applications and services in an efficient manner. This level includes such functions as messaging, such as chat, VoIP, or video conferencing, database structures, and other content networking solutions. The bottom layer is the foundation of the organizational architecture, the network infrastructure. This is composed of the network platform, the connections that work together to provide a highly available, secure, and scalable network. All of these layers are combined to offer a foundation for all organizational policies, goals, and procedures that are put in place by management and then handed down to the other departments in the company to support the overall goals and mission of the organization. Before designing a network, an important aspect must be considered. All organizations have policies at one level or another. Even if the procedures are not written well, there is some kind of understanding at the management level about the goals of the organization. Organizational policy and procedures are generally a collection of very specific guidelines and rules, which are in written form for all to understand and implement and maintain at every level of the organization in order to reach the well-defined business goals. The organizational policy cycle contains the following three components or steps. First, set the policy. Next, enforce the policy. And then the final step is to maintain and or adapt the policy as needed. Now, the policy makers include the following from top to bottom. You have your board of directors and other executives, departmental management, employees. These can be subject matter experts who can be relied upon to formulate procedures. External consultants and strategic partners can also provide outside input to set policy within an organization. Now, a flexible network infrastructure helps the organization and its customer meets the needs, policies, and procedures to help facilitate these information flows. And designing that network infrastructure involves considering the following essential features recommended by Cisco. First, availability. Critical business applications must have access to network resources on a 24/7 basis. All components of the network infrastructure should be redundant and resilient. Efficiency. The best equipment and software that is tuned for optimal results should be provided. Obviously, this should be accomplished with reasonable costs and investment. Functionality. The network infrastructure must support the business applications and services regardless of what is being rolled out today or tomorrow. Manageability, using management tools such as Cisco Works, should include technology that improves the control of the network, such as SNMP. Performance, obviously important applications need to get the bandwidth they need in order to operate correctly, and the latency on the network needs to be within an acceptable range. And finally, scalability. This includes the ability to grow and expand depending on the organizational goals of today and tomorrow. So take 3 quick challenges for me, and pause the video when I say so. On a piece of paper, write down the 4 primary entities of the modern organizational model. Go ahead and pause the video and write those down now. The 4 entities of the modern organizational model are employees, customers, vendors and suppliers, and partners. Next, on a piece of paper, draw out the organizational architecture of the network that Cisco recommends. Go ahead and do that now. As you will see here, on the top layer there's applications and services. On the middle layer there is intelligence solutions, and then structured data and business logic. And on the bottom layer there is the network infrastructure. Finally, see if you can list at least 4 of the essential features recommended by Cisco when considering a network design. At least 4 essential features to be considered. Go ahead and pause the video. Let's see how you did. There's availability, efficiency, functionality, manageability, performance, and scalability. So here's what you've learned. You've learned the design of an ecosystem. You've learned about the modern organization and organizational IT architecture, as well as the organizational policy cycle, which can and does play a role in infrastructure design considerations. All of this you will need to know for your CCDA exam, and I'm confident if you've mastered the material in this video, you're going to do very well in this area. Thank you, and good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about enterprise campus design. Specifically, we're going to go through the questions that you need to ask, or Cisco at least expects you to ask, when you are designing the access, distribution, and core layer. So we're going to work our way up. We'll begin with the access layer. Whenever a network designer is in the process of designing the campus infrastructure's access layer block, the following important questions must be answered, and you may be tested on this in your CCDA exam. What are the current and future needs for end users or node ports in the existing wiring closets of that particular building? What kind of hardware can the company or the client afford? Can it afford modular devices? This will determine the degree of scalability in the access layer, an important factor that will allow the business to grow. Is the existing cabling adequate? Do you have Cat 5 or Cat 6 UTP cabling? Can you afford fiber cabling? If you are moving into a new building, you might consider installing fiber optic cabling, even at the access layer. What are the performance and bandwidth requirements? What level of high availability is needed at the access layer? Generally, in the access layer block, you will not need as much redundancy. A certain degree of high availability might be needed if using modular network devices. What are the requirements to support VLAN, VTP, and STP? In a large enterprise campus design, you might not need to use multiple VLANs. So you can go straight to using layer 3 technologies in the access layer to avoid having multiple broadcast domains and to decrease the complexity of STP. What are the layer 2 traffic patterns for applications? And what multicasting needs and quality of services are necessary at layer 2. Next, we move up to the distribution layer. The distribution layer block combines and aggregates the access layer block components, and it uses layer 2 and layer 3 switching to break up the workgroups or VLANs and isolate the different network segments as failure domains. And it also allows for the reduction of broadcast storms. It acts as a transit module between the access and core layers. Here are some important questions that must be answered before designing the distribution layer block. Should layer 2 or layer 3 switches be used? Cost is a big issue in this decision. The available budget will dictate the hardware that's going to be used. How many total users will you have to support? With a high number of users, such as greater than 500, layer 3 switching will be essential in the distribution layer. What are the high availability needs? Are the distribution layer switches modular and scalable? What type of intelligence services will be used in the distribution layer? You must consider different features that will be implemented in the distribution layer, such as security, quality of service, or multicasting. If any of these features are implemented, layer 3 switching is mandatory. Is the company prepared to manage and configure the distribution layer block? Should training or consultancy be added to the project budget to ensure that this particular block will be properly managed? Will advanced STP features be implemented? You should think about features such as RSTP, backbone fast, or uplink fast when connecting to the backbone block via layer 2. These kinds of features can be found on almost all high-end modern switches and can help optimize and speed up the STP process. If a complete layer 3 switching model is used, you do not have to think about STP or additional features. Finally, the campus backbone block or core layer. The campus backbone design occurs very early in the overall infrastructure design process. As such, what follows are a few important questions you should ask yourself and your customers when it is time to design the campus backbone block. Do you have 3 or more separate locations, that is buildings, in the campus that are connected through an enterprise campus infrastructure? If you only have 2 buildings, you might not need a separate backbone block. A possible solution in this scenario would be to use high-speed fiber connections between the 2 buildings, distribution layers. Based on the present infrastructure, will the solution to the campus backbone be a layer 2 and 3, or just a layer 3 switching solution? In the case of a large enterprise campus, do you have the budget for a full multi-layer backbone solution throughout? Is the organization ready for a high-performance multi-layer switching environment? Things to consider here are training, personnel, budget, applications, support services, and intelligence services. Does the customer want to simplify and lower the number of links between the distribution layer switches and the server farm block edge distribution submodule? If so, you could make changes to or augment the present network infrastructure and redesign the campus backbone. What are the performance needs? The bandwidth needs for all the applications and services should be analyzed. How many high-capacity links or ports are necessary for the campus backbone block? And what are the high availability redundancy demands? Multiple aspects should be taken into consideration, such as redundant connections, modules, and hardware platforms. Obviously, in this video, there's been a lot of questions asked, but all of them are very important questions to ask. We do not design in ivory towers. We must communicate with the customer and understand the needs. All of the questions you've learned today are not only questions you need to know to perform your job well, they could be questions that you would be expected to select if Cisco were to ask you on the CCDA exam, how would you prepare to design the enterprise campus network? Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about the Cisco Hierarchical Network Model. Specifically, you're going to learn about what Cisco calls the core, distribution, and access layers of a campus network. The information is rather straightforward, but it is information you'll need to know very well to do well on your CCDA exam. So let's begin. The most important idea concerning the Cisco Hierarchical Network Model is the step-by-step construction of the network, which implements one module at a time, starting with the foundation. The implementation of each module can be supervised by a network architect, but the details are covered by a specialized team, such as routing or security or voice teams. This modular approach is the key to simplifying the network. Before we cover each module within the network model, let's talk about the main advantages of the Cisco Hierarchical Network Model. There are 8 key advantages: ease to understand and implement, flexibility, cost savings, modularity, it's easily modified, it allows for network growth, it facilitates summarization of networks, and there is also built-in fault isolation. The 3-tier model was created in order to make the construction of networks easier to understand. Cisco has always tried to make efficient and cost-effective networks with a modular structure so they can easily be divided into building blocks. The modular network design facilitates modifications in certain modules after their implementation and makes it easy to track faults in the network. The Cisco Hierarchical Network Model is defined by 3 layers: the core or backbone layer, the distribution layer, and the access layer. Now, if you're working for a small company, these layers might be collapsed. Core and distribution are often collapsed into a single layer, or sometimes all 3 layers are collapsed. That being said, let's dive into each of the layers. The access layer is the on-ramp to the network. So, for the most part, any end user or device that wants to connect to the network will do so via the access layer. As you can see, access layer switches should have redundant connectivity to the distribution layer. This will ensure network connectivity for the hosts even when there is an equipment failure. You could take it another step further and provide redundant connectivity for the host to the access layer switches, but this is the exception to the rule and certainly not the norm. The access layer is comprised of layer 2 switches, workstations, IP telephones, or any other device that requires access to the network. Here are some specific features you should be aware of at the access layer. It should provide high availability and flexible security features. You can also implement authentication, broadcast control, and it's where you would define QoS trust boundaries. In the access layer, you would also implement rate limiting techniques, and it's where you would often program spanning tree protocol, include power over Ethernet for your phones, and configure voice VLAN settings. As you can see, the distribution layer has redundant connectivity to both the access and core layers. The distribution layer is often where the brains of the network resides, since many decisions such as filtering, quality of service, and policy-based routing are performed in the distribution layer. As you can see, the distribution layer has redundant connectivity to the access and core layers. The distribution layer normally has advanced layer 3 switches that can support a wide array of functionality to support the services required from this layer. Here are the attributes of the distribution layer. It gives access control to core devices. It has redundancy to access devices. It's where the boundaries are for routing protocols. Redistribution occurs at this layer, as well as filtering, route summarization, policy routing, and here you will see your security implemented. It provides separate multicast and broadcast domains using layer 2 and layer 3 technologies, and provides routing between VLANs. It is a media translation and provides boundaries for media, and also provides redistribution. There is a lot going on in the core layer. The high-speed switching fabric ensures that all modules which connect to the core are serviced immediately. You rarely will put any programming on these switches that could cause them to slow down processing. For example, no QoS, no ACLs. Rather, you want to keep it so that these high-end switches spend their time processing, forwarding traffic rather than doing anything else. Although it's not always required to have redundancy to and from the distribution and access layers, redundancy is certainly required in the core. As you can see, the core is the hub for the interconnects in the network. It connects to the server farm, to the distribution layer, and then off to the enterprise edge as well. So having a high-performing core is critical. Here are some key features of the core layer that you will want to memorize. The core layer is high speed, it's reliable, it's redundant, it has fault tolerance and load balancing, it has manageability and scalability. In the core layer there are no filters, packet handling, or other overhead that would slow traffic down or the processing of traffic down. It has a limited but consistent diameter, and it can provide quality of service. The Cisco core distribution and access layer hierarchical model is rather straightforward, but that's the point. Cisco wants you to know this by memory and the features of each of the modules in preparation for your CCDA exam. Not only by watching this video are you prepared for your CCDA exam regarding these areas, you're also a much better engineer now that you understand the basic organization of a campus network. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about geographical and application considerations in network design. First, let's begin with geographical considerations. The geographical considerations regarding the enterprise campus network design involve locating the entire campus building blocks and the components of those blocks, and then determining the distance between them. The geographical structures can be broken down into 4 different types of geography. Intra-building, which is inside the building. Inter-building, between buildings. Remote building, which is relatively close, which is less than 100 kilometers away. Or a remote building that is greater than 100 kilometers away. First, let's begin with intra-building design. An intra-building structure can be comprised of a single floor or multiple floors, but it's in a single building. The goal is to connect all the different components, such as servers, workstations, printers, and give all of them access to the network resources depending on their type of system. The access and distribution layers are typically located in an intra-building area. User workstations are connected either to a wiring closet or directly to an access layer switch that is connected to a distribution layer switches, and then ultimately those are connected into the core. Inter-building design, now with this network structure, links individual buildings in the campus or corporate complex using the distribution layer, or it could be at the core layer as well, depending on the size of the organization. The distance between buildings
should range from a few hundred meters to a few kilometers, usually less than 1 mile. The connection between the buildings should provide as high bandwidth and throughput as possible. Now, another issue is ensuring that there is very little environmental interference. So the typical medium used in this case is optical fiber. The optical fiber used can be either multi-mode fiber or single-mode fiber. Multi-mode and single-mode fiber share common characteristics. The cabling uses glass or plastic fibers to move the information from building to building. The cables are made from a bundle of threads, each of which can transmit messages modulated under light waves. Optical fiber has greater bandwidth than copper cables, so it can carry more data, and it is less susceptible to interference. Fiber optic cables are also much thinner and lighter than metal wires, and data can be transmitted digitally, which is the natural way in which computer data moves, rather than through analog signaling. Now, the big disadvantage of fiber optic is that the cables are more expensive to install. They're often more fragile and difficult to split up. But despite these disadvantages, fiber optic cabling is becoming more and more popular for local area networking and telecom provider infrastructure. Let's look at the differences between multi-mode and single-mode fiber. Multi-mode has the following characteristics: specific installation and performance guidelines. It also has specific connectors. Concurrently transports multiple lightweight waves and modes within the core. Used for relatively short distances. Typical diameter is 50 to 62.5 micrometers. Bandwidth is usually up to 10 gigabits per second. Range is 550 meters when using gigabit Ethernet. Used between nodes and between buildings. And it's obviously more expensive than copper. Single-mode fiber has the following characteristics: specific installation and performance guidelines. Carries a single light laser. Typical diameter of a core is 2 to 10 micrometers. Bandwidth is usually up to 10 gigabits per second. Range is up to 100 kilometers when using gigabit Ethernet. But the key to remember is single mode is used between nodes and buildings for longer distances than multi-mode fiber. Next, let's talk about remote buildings. The campus infrastructure can be spread over a metropolitan area or over a larger area than that, so different parts of a city. And if you're dealing with distances within a few miles, you might focus on the physical needs. First, you need to determine whether the company owns any of the copper lines, and if it does, you can build from there. But you also might need to connect an enterprise campus network through the WAN block. Now, if this is the case, you should leverage the existing telecom providers in that specific area. And then you also may want to consider using satellite or various wireless technologies to connect your site as well. But as the distance between the sites grows, the following actions will occur. Connectivity costs increase, required throughput will decrease, and importance of availability will decrease. Next, let's talk about network applications. Another important factor when designing campus switching is considering the network applications that will be used. Once the physical and geographical aspects are clear, the network designer needs to characterize what types of applications will be processed within the network. The first category of applications that must be identified involves the critical or core applications, and the rest of the services fall under the optional intelligence category. The network applications can be divided into 4 types: client-to-client applications, client-to-distributed server applications, client-to-server farm applications, and client-to-enterprise edge applications. So here's what you've learned. You've learned about design considerations, not only for geography, but also for application types. And then you need to know how to break out systematically what type of design challenges are you facing. so that you just aren't trying to design generally, but you're being specific about the geographical issues you're facing, but also the network applications that you need to support. I wish you the best of luck in your studies. Thank you.
Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about Layer 2 technologies and Layer 3 switching. Let's begin first with Layer 2 technologies. Layer 2 technologies relate to the OSI data link layer. Now, today's modern enterprise, which is a distributed networking world of multimedia and client applications, dictates the need for greater bandwidth and a greater degree of control. Over the past 10 years, almost all organizations have replaced their shared networking technology, such as hubs, with switches to create switched technologies. A concept you need to understand is a collision domain and what exactly a collision domain is. A collision domain is comprised of nodes and devices that share the same bandwidth, and this is called a bandwidth domain. For instance, everything that is connected to a switch port via a hub is in the same collision domain. This means there is always the possibility of a collision in the operations of that particular Ethernet. A broadcast domain, on the other hand, represents a collection of devices that can see each other's broadcast or multicast packets. Nodes that are in the same collision domain are also in the same broadcast domain. For example, all devices associated with the port of a router are in the same broadcast domain. And by default, broadcasts do not traverse a router's port interface. When a shared technology is used, such as hubs, all the devices share the bandwidth of the specific network segment. When using switched technologies, each device in the switch port is its own collision domain. However, all the devices are in the same broadcast domain. Now, here's some of the basics. Why LAN switches? Why did they overtake the market? There was a time when bridges were quite popular. Well, LAN switches have quite a few advantages over bridges. Specifically, they have more ports than a bridge would ever be capable of supporting. Micro-segmentation allows individual hosts to be connected to individual ports. They operate at hardware speed using ASICs versus software used by bridges. They support Layer 3 and Layer 4 packet switching by using MLS features. We'll talk about that a little bit later. And finally, probably the most important feature of LAN switching nowadays is the VLANs. So they can use VLANs to create smaller logical broadcast domains on your network. Now, let's just get back to basics here. LAN switching is a form of packet switching, which is used on local area networks. LAN switches provide, and as you already know, they provide much higher port density and at a much lower cost than traditional bridges did. Now there are three main forwarding techniques that can be used by switches: store and forward, cut through, and fragment free. Let's just do a basic drawing here to better understand these concepts. So let me draw out first a frame that is passing through a switch. And then after I draw this frame, I'm going to draw a line here, and that will designate the memory of the switch. So if the frame is passed into memory, we will designate it by going underneath this line. Let's cover cut-through switching first. With cut-through switching, the LAN switch copies into its memory only the destination MAC address, which is located in the first 6 bytes of the frame. The switch looks up the destination MAC address in its switching table and determines the outgoing interface port, and then forwards the frame to its destination through the designated switch port. A cut-through switch reduces delay because the switch begins to forward the frame as soon as it reads the destination MAC address. This is in contrast to store and forward switching. Store and forward switching means that the LAN switch copies each complete frame into its switch memory buffers, and then it computes a CRC check for errors. The CRC check uses a mathematical formula to determine whether the frame is errored. And if an error is found, it's discarded. But if it's error-free, the switch will forward the frame out the appropriate interface port. Finally, there's fragment-free switching, which is also known as runtless switching. Basically, frames that are damaged, which often happen by collisions, are often shorter than the minimum valid Ethernet frame size of 64 bytes. If a frame is smaller than 64 bytes, the switch will discard that frame. Fragment-free is a faster mode than store and forward, but there still exists a risk of forwarding bad frames because you do not have the CRC check. Now, LAN switching can be characterized as either symmetric or asymmetric. Now, symmetric switching provides evenly distributed bandwidth to each port on the switch. And this is typically used in a peer-to-peer desktop environment. Where you see asymmetric switching is when we're talking about endpoints communicating with bandwidth-intensive services such as servers. So this provides unequal bandwidth between ports on a switch. And this is actually the most common type of switching, and it's optimized for client-server environments. You may have a server that demands a 10 gigabit port, where many of your clients obviously don't need that much speed and may only have a 1 gigabit port, or if you have an older switch, a 100 megabit port. Now, in the old days, basic rule of thumb in designing a local area network and wide area network was that 80% of the traffic was going to remain on the local area network. Thus, it was called the 80-20 rule. 80% of the traffic stays local, and you should plan for that. Well, with the advent and with the popularity of the internet and server farms, this has really resulted in the flipping of those numbers. Now we need to design our networks with the idea that probably only 20% of the traffic is going to stay local on the local area network, whereas 80% is going to leave the local area network. So this new paradigm, this new 20-80 rule, places a much greater burden on the network backbone. Next, let's talk about layer 3 switching. Historically, LAN switching typically involves layer 2 switching at the access layer and sometimes at the distribution layer. Layer 2 switches forward information based only on the MAC address, that is, the layer 2 frame address. Layer 3 switching, however, uses the MAC address in addition to the layer 3 address, which is typically, nowadays, an IP address. The following three options exist when considering designing a switched environment. Layer 2 switching throughout the network, a combination of layer 2 and layer 3 switching, and then layer 3 switching throughout the network. Using layer 2 switching, layer 3 switching, or a combination of the two also depends on the available switching platforms, as not all switches support layer 3 technologies. At the heart of a switched network is the concept of VLANs. So what exactly is a VLAN? Well, Cisco says it's a group of end stations with a common set of requirements. Using VLANs allows you to put many different devices in many different locations on the same logical network, on the same layer 2 network. In the past, without VLANs, you would have had to rely upon simple hardware solutions, but a VLAN allows you to virtualize your layer 2 segment. VLANs are usually associated by the same subnet, so normally devices on a VLAN are sharing the same subnet. And with this in mind, they're sharing the same broadcast domain. That is the norm. And then VLANs must be routed to communicate with other VLANs. So it is a true layer 2 segment. A VLAN is not going to be able to communicate with another VLAN unless it is passed through a layer 3 device which can route it. Now, there are two types of switch port types. for VLAN membership that we need to understand. And the first is the access port. Now, access ports can only belong to a single VLAN. Now, when you think of an access port, it's pretty much probably what you think of. It's usually for end devices like a workstation or a server. It is a device that is an end station, and again, access port can only belong to a single VLAN, typically used to connect end devices. And there are two methods to assign ports to VLANs for these access ports. The first, which is by far the most popular, is the static VLAN assignment. So an administrator actually doing it, and then dynamic VLAN assignment, which is done by a server. So let's dig a little bit more into those two concepts. So when we have a static VLAN assignment, the network administrator is actually manually configuring a switch port to be a part of a VLAN. The network administrator is programming the port to say, you are going to be an access port and you're going to be associated with this specific VLAN. Now, you can do this dynamically, and this is not as popular, but there is something called a VLAN management policy server, which can assign a desired VLAN to users connecting to a switch. We don't need to get much deeper than that for your exam, but you do need to know these two methods. Now, there's another type of port that we need to understand the concept of VLANs, and that is trunk ports. And trunk ports are used to carry data from multiple VLANs. So access ports only allow communication from one end device over a specific VLAN. Well, ultimately, if you're hosting many VLANs, this traffic's going to need to be able to communicate throughout your network so that they're not limited by a hardware device. So your VLANs may be spread throughout many floors or maybe even many buildings. Trunk ports allow you to carry data from all these different VLANs between all your different hardware devices. Now, there are some standard VLAN numbers and ranges you should know. Specifically, let's focus on 2 to 1001. These VLANs are created and used and deleted on all Cisco Catalyst switches. And another one that you should really focus in on is the range of 1006 to 4094. These are extended. This is an extended range of VLANs for Ethernet VLANs only. Now, you may be asked about these other ranges, but I would focus in on VLAN ranges 2 to 1001 and 1006 to 4094. VLAN trunks are used to carry data from multiple VLANs, which you already know. Now, there are two methods, two protocols that can be used to build these trunks. And the first is Inter-Switch Link, or ISL. And that's a Cisco proprietary protocol that is used to preserve the source VLAN identification information for frames that traverse trunk links. And then there is, I would say, the more popular 802.1q, which is an open standard. And then it performs a little bit differently than the Cisco proprietary protocol. Now, the reason 802.1q is so popular is you probably understand that for obvious reasons, that if you want to trunk between two devices, one is Cisco and one is non-Cisco, you're able to do that. So this standard works very effectively, and 802.1q is very popular. But you will definitely be asked about ISL, and you will definitely be asked about the differences between ISL and 802.1q. Now, so you've received a lot of information right now. So let's go ahead and kind of draw out some of these concepts that we've been talking about. So when we think of VLANs, we think first of we need to connect, endpoints need to connect on a local area network. So here we have 4 endpoints, and we have one switch. And each of these endpoints need to communicate, and not all of them need to communicate with each other. So let's say we have 2 workstations and 2 servers, and we're going to put this one workstation in VLAN 10, and this other workstation in VLAN 10, and then these two servers in VLAN 2. These two servers are segmented on their own VLAN, and as are the workstations. They cannot communicate between each other, between VLAN 2 and 10, but anything on VLAN 10 can communicate with VLAN 10. Now here's another dedicated VLAN, we'll say VLAN 3, to a dedicated device. Now, and here is a router. So for any of these VLANs to communicate with one another, they need to pass through a layer 3 device. So this workstation that from VLAN 10, if it wants to communicate over to a server, it needs to be routed and go through the router and passed over to VLAN 2. Let's say you want to keep VLAN 3 devices not accessible from the network. You can prevent that. So here we have other devices on VLAN 3, and we'll say, let's say this is a back-end connection between two servers that we have no need to route it. VLAN 3 can be segmented from the entire network. Nobody can reach it. So there's some security built into VLANs as well. Now VLANs can extend obviously over to other hardware platforms. So this router is connected to another switch, and on this switch, let's say that's in a different building, we have another device on VLAN 2, another device, another endpoint on an access port to VLAN 10. And if they want to communicate over to the other building, let's say VLAN 2 or VLAN 10, they simply go over this trunk port, you know that term, goes over the trunk port and can communicate over to the other sites. When designing a full layer 2 environment using VLANs, a router might be used to provide routing between the VLANs. This technique is called router on a stick because only one router interface is used to carry all the VLANs. When exclusively using layer 2 switches and VLANs throughout the network, all the policies, access lists, and quality of service rules will be managed at the data link layer. The policy capabilities are very limited at the data link layer, but they are greatly enhanced in layer 3 switches. Another area in which layer 2 switches are limited is load sharing capabilities used to ensure redundant links, that is, multiple paths throughout the network. This is because layer 2 switches only know about MAC addresses and they cannot perform intelligent load sharing, for example, based on a destination network. Layer 3 switches can do that. Layer 3 switches also support dynamic routing protocols. Therefore, with layer 2 switching, the load can be shared only on a per VLAN basis. In addition, when using layer 2 switches only, the basis of all failures, or the failure domain, will be isolated to the VLAN only. On the other hand, in a multi-layer environment, the failures can be better isolated at the access layer, to the core layer, or even particular network segments. In a layer 2 switched environment, only STP, that is Spanning Tree Protocol, offers convergence and loop control. However, when using layer 3 switching, this feature can also be implemented at the distribution and core layers using routing protocol technologies such as OSPF or EIGRP. And when considering cost, using layer 2 everywhere is the cheapest solution, but this is also much less flexible and much less manageable. Using layer 3 switches throughout the network is the most expensive option, but it's very powerful and flexible. A compromise would be to implement layer 3 switches only in the distribution layer, and then eventually, as the budget allows and the network scales, extend the layer 3 switches into the core layer for full layer 3 switching at the distribution and core layers. So in this video, you've learned about layer 2 technologies and layer 3 switching. And this information will provide you with a solid foundation to do well on your CCDA exam. Thank you. Hi, this is David Voss, CCIE 11372, and in this video we're going to be covering the cable specifications for local area networks.
Specifically, this video is going to review LAN media and its components. We need to identify some of the constraints you should consider when provisioning various LAN media types. Ethernet is the underlying basis for the technologies most widely used in local area networks today. In the 1980s and early 1990s, most networks used 10 megabit per second Ethernet, defined initially by Digital, Intel, and Xerox, and then later by the IEEE 802.3 working group. The IEEE 802.3-2002 standard contains physical specifications for Ethernet technologies up to 10 gigabits per second. The following table is something you should know well for your CCDA exam. It describes the physical Ethernet specifications up to 100 megabits per second. It provides scalability information that you can use when provisioning IEEE 802.3 networks. Of these specifications, the 10-base-5 and 10-base-2 are no longer used, but are included for completeness. Fast Ethernet is preferred over 10-base-T Ethernet. Let's talk about some of the 100 megabit per second Fast Ethernet design rules. IEEE introduced IEEE 802.3U-1995 standard to provide Ethernet speeds of 100 megabit per second over UTP and fiber cabling. The 100 base T standard is similar to 10 megabit per second Ethernet in that it uses carrier sense multiple access collision detect, which you probably know as CSMA/CD. Let's discuss the following specifications for Fast Ethernet. 100 base TX Fast Ethernet. This specification uses Cat5 UTP wiring. Like 10 base T, Fast Ethernet uses only 2 pairs of the 4-pair UTP wiring. If Cat5 cabling is already in place, upgrading to Fast Ethernet requires only a hub or a switch and any network interface card upgrades. Because of the low cost, most of today's installations use switches. The specifications for this standard are as follows: transmission over Cat5 UTP, an RJ45 connector, punch-down blocks in the wiring closet must be Cat5 certified, and 4B/5B coding. Let's discuss now the 100 base T4 Fast Ethernet standard. The 100 base T4 specification was developed to support UTP wiring at the Cat3 level. This specification takes advantage of higher speed Ethernet without recabling to Cat5 UTP. This implementation is not widely deployed, but here are the specifications. It can transmit over Cat3, 4, or 5 UTP wiring. 3 pairs are used for transmission, and the 4th pair is used for collision detection. No separate transmit and receive pairs are present, so full duplex operation is not possible. And the coding is 8B6T. Next, let's discuss 100 base FX Fast Ethernet. This is a specification for fiber. It operates over 2 strands of multi-mode or single-mode fiber cabling. It can transmit over greater distances than copper media. It uses a media interface connector, ST stab and twist, or SC stab and click fiber connectors, defined for FDDI and 10 base FX networks. To make 100 megabit per second Ethernet work, distance limitations are much more severe than those required for 10 megabit per second Ethernet. Repeater networks have no 5-hub rule. Fast Ethernet is limited to 2 repeaters. The general rule is that 100 megabit per second Ethernet has a maximum diameter of 205 meters with UTP cabling, whereas 10 megabit per second Ethernet has a maximum diameter of 500 meters with 10 base T and 2500 meters with 10 base 5. Most networks today use switches rather than repeaters, which limits the length of 10 base T and 100 base TX to 100 meters between the switch and host. Now, the distance limitation imposed depends on the type of repeater. The IEEE 100 base T specification defines two types of repeaters, Class 1 and Class 2. Class 1 repeaters have a latency of 0.7 microseconds or less. Only one repeater hop is allowed. Class 2 repeaters have a latency of 0.46 microseconds or less, and one or two repeater hops are allowed. Now let's talk about Gigabit Ethernet design rules. Gigabit Ethernet was first specified by two standards, IEEE 802.3Z-1998 and 802.3AB-1999. The IEEE 802.3Z standard specifies the operation of Gigabit Ethernet over fiber and coax cable and introduces the Gigabit Media Independent Interface, the GMII. These standards are superseded by the latest revision of all the 802.3 standards included in IEEE 802.3-2002. The IEEE 802.3 AB standard specified the operation of Gigabit Ethernet over Cat5 UTP. Gigabit Ethernet still retains the frame formats and frame sizes, and it still uses CSMA CD. As with Ethernet and Fast Ethernet, full duplex operation is possible. Differences appear in the encoding. Gigabit Ethernet uses 8 Bravo, 10 Bravo coding with simple non-return to zero. Because of the 20% overhead, pulses run at 1,250 megahertz to achieve a 1,000 megabits per second throughput. This chart you will definitely want to know in preparation for your CCDA exam. Let's talk about the Gigabit Ethernet standards in detail. The 1000 base LX, that is the long wavelength Gigabit Ethernet standard, uses long wavelength optics over a pair of fiber strands. The specifications are as follows. It uses long wave on multi-mode or single mode fiber. The maximum lengths for multi-mode fiber are 62.5 micrometer fiber, which is 450 meters, or 50 micrometer fiber at 550 meters. Maximum length for single mode fiber is 5 kilometers. The IEEE 1000 base SX standard uses short wavelength optics over a pair of multi-mode fiber strands. Its maximum lengths are 260 and 550 meters respectively. The IEEE 1000 base -CX standard is for short copper runs between servers. It runs over a pair of 150 ohm balanced coax cables. Maximum length is 25 meters, and this is obviously mainly used for server connections. And then finally, the 1000 base T Gigabit Ethernet over UTP standard. It was approved in June 1999 and now included in IEEE 802.3-2002. This standard uses the 4 pairs in the cable. Maximum length is 100 meters. Encoding defined is a 5-level coding scheme, and 1 byte is sent over the 4 pairs at 1250 megahertz. The IEEE 802.3 AE supplement to the 802.3 standard was published in August of 2002, and it specifies the standard for 10 gigabit Ethernet. It is defined for full duplex operation over optical media, UTP, and copper. 10 gig E has several physical media specifications based on different fiber types and encoding. Multimedia fiber and single mode fiber are used, and if you look at this diagram, this is something you will definitely want to memorize in preparation for your CCDA exam. Now, as noted previously in this video, there are several media types that are used for campus networks, and this chart is one you'll want to remember because it provides a good summary of the information you'll need to know for the different media types and when you may want to use them.
So here's what you've learned. You've learned about campus LAN media types. And this is something you will definitely be tested on in your CCDA exam. You've learned about the different Ethernet standards as well as the different campus transmission media types. And I'm confident if you master the material in this video, you'll do very well in this portion of your CCDA exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about analyzing traffic in preparation for your CCDA exam. First, let's start with analyzing application traffic. One of the first enterprise campus design issues refers to analyzing the application traffic as it relates to the switched network design. The traffic patterns usually fall into one of the following scenarios: local with a segment, module, and submodule, or distant, remote traffic patterns. This implies traversing different segments or crossing submodules or modules in the campus design. Networks were originally designed according to the 80-20 rule, which states that 80% of the traffic is internal, 20% is remote. This concept has changed with the evolution of enterprise networking and distributed server networking in modern campus networks. So the ratio now is 20-80, whereas 20% is for local traffic and 80% is for traffic that crosses between modules and segments. This change occurred as a result of servers no longer sitting in the workgroup areas. Generally, the application and backbone servers are placed in a server farm area. This puts a much higher load on the backbone because much of the traffic from the client side is going to the servers in the server farm through the core layer devices. This changes the way you will analyze application traffic. In order to exemplify the 80-20 rule, consider a workgroup area with various devices connected to a basic layer 2 switch using VLANs. The Inter-VLAN routing is accomplished on the routers that also allow access to an email server. According to the 80-20 rule, 80% of traffic stays within the VLAN, whereas 20% of the traffic is going to the email server. On the other hand, for example, in the modern 20-80 rule, consider a situation in which there are multiple logical departments using common resources with applications distributed throughout the organization. This means there are no dedicated servers located within the department, for example, database or file servers. All the data is stored in the server farm block. The end user's devices connect to a series of layer 2 or low-end layer 3 switches before reaching the distribution layer block, where the high-end layer 3 switches with high availability are located. The data flow finally reaches the server farm block consisting of modern database servers such as email, applications, databases. In this example, the traffic distribution reflects the 20-80 rule, meaning 20% of the network traffic stays local, while 80% of the traffic is moving across the distribution layer and backbone of the network. This is the reason you want your distribution and core layer links to be highly available and fast in order to move data across the enterprise quickly. The diagrams presented here represent a single building, but in large campus enterprise you would have multiple buildings connected by the network backbone module. The network backbone is connected to the edge distribution submodule in order to provide external access from the network. Next, let's discuss analyzing multicast traffic. With the incredible advances of collaboration tools using the World Wide Web and the Internet, it is very likely that the organization will have to support multicast traffic. The process of multicasting opposed to the process of broadcasting or unicasting has the advantage of saving bandwidth because it sends a single stream of data to multiple nodes. The multicasting concept is used by every modern corporation around the world to deliver data to groups via the following methods: corporate meetings, video conferencing, e-learning solutions, webcasting information, distributing applications, streaming news feeds, and streaming stock quotes. Multicast data is sent as a multicast group, and users receive the information by joining that group using IGMP, or Internet Group Management Protocol. Cisco multicast-enabled routers can be used running multicast routing protocols such as PIM, Protocol Independent Multicast, so that they can forward the incoming multicast stream to a particular switch port. Cisco switches effectively implement multicasting using two main protocols: CGMP, which is Cisco Group Management Protocol, and IGMP snooping. CGMP allows switches to communicate with multicast-enabled routers to figure out whether any users attached to the switches are a part of any particular multicasting groups and whether they are qualified to receive the special stream of data. IGMP snooping allows the switch to intercept the multicast receiver registration message, and based on the gathered information, it makes changes to its forwarding table. IGMP snooping works only on Layer 3 switches because IGMP is a Layer 3 protocol. Next, let's discuss analyzing delay-sensitive traffic. If using multicasting or web streaming, e-commerce, e-learning solutions, or IP telephony, the traffic involved in this process will be delay-sensitive, and QoS techniques might be necessary to ensure that this type of traffic is treated with priority. In Layer 3 applications, such as frame relay environments, using EIGRP, OSPF, or BGP as routing protocols with the ISP, it is very common to use QoS techniques to shape and control traffic at the IP layer. You can also use QoS at Layer 2. When using QoS or analyzing or controlling delay-sensitive traffic at Layer 2, there are 4 categories of QoS techniques as follows: tagging and traffic classification, congestion control, policy and shaping, and scheduling. As you can see in this diagram, you'll see that tagging and traffic classification happen between the end user nodes through the access layer and up to the distribution layer. This is where packets are classified, grouped, and partitioned based on different priority levels or classes of service. This occurs by inspecting the Layer 2 packet headers and determining the priority of the traffic based on the traffic type. In this way, the traffic can be tagged and classified. The next 3 techniques, congestion control, policy and traffic shaping, and scheduling, occur in the distribution layer block and the edge distribution layer submodule, primarily on Layer 3 switches. You want to avoid applying any QoS technique at the core layer because you want as little overhead as possible on the backbone so that they can successfully achieve their goals, which is fast connectivity, high availability, and reliability. Congestion control involves the interfaces of the access layer switches and the queuing mechanisms configured on them. Queuing techniques are used in order to deal with the congestion of packets coming into and out of the switch ports. This method ensures the traffic from critical applications will be forwarded properly, especially when using real-time applications. So let's summarize what you've learned. In this video, you've learned about the different types of traffic that can traverse a switched network and how to handle that traffic. And some of this information is been at a higher level, such as QoS. But that being said, this is what Cisco expects you to know for the CCDA exam, with the understanding that things will get quite a bit more granular in the follow-up videos, but also as you work your way up to CCDP. This is a good foundation for you to begin, and I wish you the best of luck in your studies. Thank you. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about network resiliency and fault domains in preparation for your Cisco CCDA exam. Specifically, you're going to learn about network, device, and operational resiliency, and also the concept of fault domains. So let's go ahead and begin. There are three major resiliency requirements which encompass most of the common types of failure conditions. Depending on the LAN design tier, the resiliency option appropriate for the role and network service type must be deployed. There is network resiliency, which provides redundancy through physical link failures, such as a fiber cut. Device resiliency, which protects the network during abnormal mode failure triggered by hardware or software. And then operational resiliency, which enables resiliency capabilities to the next level, providing complete network availability even during planned network outages. We'll talk about all of these in this video. First, we'll talk about network resiliency. The most common network fault occurrence in the LAN network is a link failure between two systems. Link failures can be caused by issues such as a fiber cut, miswiring, line card module failure, etc. In the modular platform design, the redundant parallel physical links between distributed models in two systems reduces fault probabilities and can increase network availability. It is important to remember how multiple parallel paths between two systems also affect how higher layer protocols construct adjacencies and loop-free forwarding topologies. Deploying redundant parallel paths in the recommended borderless campus design by default develops a non-optimal topology that keeps the network underutilized and requires protocol-based network recovery. In the same network design, the routed access module eliminates such limitations and enables full load balancing capabilities to increase bandwidth capacity and minimize application impact during a single path failure. To develop consistent network resiliency service in the centralized main and remote campus sites, the following basic principles apply. Deploying redundant parallel paths is a basic requirement for network resiliency at any tier. It is critical to simplify the control plane and forwarding plane operation by bundling all physical paths into a single logical bundled interface, such as Ether channel. Implement a defense in-depth approach to failure detection and recovery. An example of this is configuring the UDLD protocol, that's unidirectional link detection, which uses a layer 2 keep alive to test that the switch-to-switch links are connected and operating correctly, and acts as a backup to the native layer 1 unidirectional link detection capabilities provided by 802.3z and 802.3ae standards. Ensure that the network design is self-stabilizing. Hardware or software errors may cause ports to flap, which creates false alarms and destabilizes the network topology. Implementing route summarization advertises a concise topology view of the network, which prevents core network instability. Next, let's talk about device resiliency. Another major component of an overall campus high availability framework is providing device or node level protection that can be triggered during any type of abnormal internal hardware or software process within the system. Some of the common internal failures are software triggered crash, power outages, line card failures, etc. LAN network devices can be considered as a single point of failure and are considered to be a major failure conditions because recovery may require a network administrator to mitigate the failure and recover the system. The network recovery time can remain undeterministic, causing complete or partial network outage depending on the network design. Redundant hardware components for device resiliency vary between fixed configuration and modular Cisco Catalyst switches. To protect against common network faults or resets, all critical borderless campus network devices must be deployed with a similar device resiliency configuration. Let's talk about the basic redundant hardware deployment guidelines at the access layer and collapse core switching platforms in the campus network. Redundant power system. So redundant power supplies for network systems protect against power outages, power supply failures, and so on. It is important not only to protect the internal network system, but also the endpoints that rely on power delivery over the Ethernet network. Redundant power systems can be deployed in the following two configuration modes. Modular switch. This is where dual power supplies can be deployed in modular switching platforms such as the Cisco Catalyst 6500 or 4500E series platforms. By default, the power supply operates in a redundant mode, offering 1+1 redundant option. In modular Catalyst and Nexus switching systems, the network administrator must perform overall power capacity planning to allow for dynamic network growth with new line card modules. The other option is fixed configuration switch. Depending on the switch that you're running, fixed configuration switches offer a wide range of power redundancy options. Cisco Stack Power can be one of them, especially in the Cisco Catalyst 3750X series platform. To prevent network outages on fixed configuration Catalyst switches, they must be deployed with power redundancy. Next, redundant control plane. Device or node resiliency in modular Cisco Catalyst 6500E or Nexus 7000, 4500E in Cisco StackWise Plus platforms provides 1+1 redundancy with enterprise class, high availability, and deterministic network recovery time. The following subsections provide high availability design details as well as graceful network recovery techniques that do not impact the control plane and provide constant forwarding capabilities during failure events.
So, to minimize the amount of time the network is unavailable to users, following a switchover from a primary to a secondary device. The main goal is to continue forwarding IP packets after the route processor switchover. NSF is supported by a wide variety of dynamic routing protocols. If a router is running one of these protocols, it can detect the internal switchover and take the proper steps to continue forwarding network traffic using and leveraging the forwarding information base while recovering route information from its peer devices. Cisco NSF with SSO is a mechanism of supervisor redundancy that is part of the iOS software and provides extremely fast supervisor switchover at layer 2, 3, and 4. SSO allows the standby route processor to take control of the device once a hardware or software fault occurs on the active route processor. SSO synchronizes the following parameters: startup configuration, startup variables, the running configuration, layer 2 protocol states for ports and trunks, layer 2 and layer 3 tables, access control lists, and QoS tables. Next, let's talk about operational resiliency. Designing the network to recover from failure events is only one aspect of the overall campus nonstop design. Converged network environments are continuing to move forward, requiring true 7x24x365 availability. The borderless campus network is a part of the backbone of the enterprise network and must be designed to enable standard operational processes, configuration changes, and software and hardware upgrades without disrupting network services. The ability to make changes and upgrade software and/or replace or upgrade hardware becomes challenging without a redundant system in the campus core. Upgrading individual devices without taking them out of service is similarly based on having internal component redundancy. The Cisco In-Service Software Upgrade ISSU and Enhanced Fast Software Upgrade EFSU leverage NSF SSO technology to provide continuous network availability while upgrading critical systems. This helps to greatly reduce the need for planned service downtime and maintenance. Next, let's talk about fault domains. Each network tier can be classified as a fault domain, with the deployment of redundant components and systems increasing redundancy and load sharing capabilities. However, this introduces a new set of challenges, namely
higher costs, and increased complexity in managing a greater number of systems. Network reliability and availability can be simplified using several Cisco high availability and virtual system technologies such as VSS, which offers complete failure transparency to end users and applications during planned or unplanned network outages. In this sense, minor or major network failures are considered broad terms that include several types of network faults, which must be taken into consideration in order to implement a rapid recovery solution. Cisco high availability technologies can be deployed based on whether platforms have critical or a non-critical role in the network. Some of the high availability techniques can be achieved in the campus network design without making major network changes. However, the critical network systems that are deployed in the center of the network to provide global connectivity may require additional hardware and software components to offer non-stop communication. So here's what you've learned. You've learned about network, device, and operation resiliency. This is a key part of your CCDA exam. And then you also learned about the terminology of fault domains. And again, this is something you could be asked on your exam. So now that you've watched this video, I'm confident if you're asked any questions regarding resiliency or fault domains on your CCDA exam, you'll do very well. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're going to be covering high availability introduction and the Cisco supported protocols to ensure a highly available environment. Now, this term high availability is considered a very broad and general term. Let's get more specific as to how it applies to the devices that we'll be supporting. Availability is calculated mathematically and is often expressed in percentages. Surely you have seen some of these calculations in your place of work. Percentages are often calculated from failure rates and repair times. So different types of high availability include service level high availability, system level high availability, and network level high availability. Let's first understand what reliability and serviceability are, because these help us understand the calculations that are used to understand if we have a highly available environment. Reliability measures the ability of a system or a solution to function without interruptions. And the most common measurement you've probably seen regarding this is mean time before failure. Serviceability refers to the time it takes to restore a system to service following a failure. A commonly used metric that you've probably seen for this is mean time to repair. Let's start talking about some of the specific protocols that Cisco supports on the devices to provide highly available environments. HSRP is a Cisco proprietary first-hop redundancy protocol. Two versions of HSRP are supported on iOS software. Version 1, and this is the default HSRP version. And this restricts the number of configurable HSRP groups to 255. I don't expect you should be exceeding that anytime soon. And then there's version 2. Some updates to version 2. It uses a new multicast address, among many other things that you can see here. Finally, HSRP authentication gives you the option of plain text or MD5 authentication. MD5 authentication can be configured with or without keychains. When implementing HSRP, two or more routers are configured with a standby IP address on a broadcast interface, usually an Ethernet segment. So while they will each have a local IP address, in this case .2 and .3, a passive election is held to determine the active router, which is actually answering for the gateway IP address .1. The active router answers ARP requests for the standby IP address with a virtual MAC address, so that the host sends packets to the gateway IP address, winds up sending it to the active router. Now, if the active router dies, then another election is held. And in this case, traffic would go out the .3 interface, even though traffic would still be pointing to the virtual .1 IP address. So let's configure HSRP in a lab. First, we're going to assign an IP address to the interface. Then we're going to assign the virtual IP address. This is the IP address that will answer as the gateway between the devices that are running HSRP. Then you can manually set the version number, so we'll run HSRP version 2. And then the timers, so the hello interval, this is how often a packet will be sent to notify the other routers or devices participating in HSRP that this device is active. And then after 30 seconds, it would be declared down. And we can set priority if we'd like, and the higher the priority number, the more likely it will take over as the active router in HSRP. If we set it to 1, it's really going to be the gateway of last resort, only after the other devices have failed. And then finally, you can set up authentication for HSRP to make sure that communications are secure between the devices while it's running. VRRP is an open standard first hop redundancy protocol which elects a virtual router master and then virtual router backups. You can configure up to 255 virtual routers on an interface. That is, if your system is capable of handling it. The default VRRP priority value is 100, and that's important to note because the lower you set it, the less likely it's going to take over as the master. The higher you set it, the more likely it will be. The virtual router master is in charge of sending advertisements to the other routers in the same group. And VRRP, it should be noted, can support both plain text and MD5 authentication. So let's say we have 3 switches with VRRP, which is non-proprietary. In VRRP, one router is elected as the virtual router master, and the other routers are acting as backups in case the virtual router master fails. So in this case, the master has been elected. .3 and .4 will serve as backups to .2. .2 will answer to the virtual IP address, and if it were to fail, then a backup device would take over. In this example, that would be the .3 device. And if the .3 system failed, then the final backup system, .4, would take over. So let's configure VRRP in a lab. First, we'll set an IP address on the interface. And then next we'll set the virtual IP address. Next we'll configure the advertise timers. So this configures the interval between successive advertisements by the virtual router master and a VRRP group. The unit of interval is in seconds. The default interval is 1 second, and all routers in the VRR group must use the same timer values. Then we set the priority. The default priority is 100, but we're going to knock that down a bit so that this device does not take over unless absolutely necessary. And then finally, you can configure authentication. Next, let's cover GLBP. GLBP allows multiple gateways in the same GLBP group to actively forward traffic. So instead of just one device forwarding traffic, you can have multiple. Gateways communicate via hellos messages that are sent by default every 3 seconds. The GLBP group members elect one gateway to be the AVG. Now the AVG answers all ARP requests to the virtual router address and assigns a virtual MAC address to each member of the GLBP group. GLBP has many other features, but you should really focus on the fact that GLBP does provide load sharing and many different load sharing methods, host dependent, round robin, and weighted. And it does support plain text and or MD5 authentication. But the big advantage, and the question you're most likely to get regarding GLBP, is when would you use it? And you would use it if you would like to load balance between devices. GLBP provides a standby IP just as HSRP, but it also provides multiple virtual MAC addresses. So when a host on the connected network sends an ARP request, one of the routers answers with the virtual MAC address. Now this does allow for load balancing. You can load balance across multiple systems instead of just relying on one system to serve all the traffic. In this case, we're going to load balance 50% to router 1, 20% to router 2, and 30% of the traffic to router 3. This can be done because you're using virtual MAC addresses, which take turns answering traffic requests. If a router were to fail, the other remaining routers could take over for all the traffic. Here's an example of GLBP programming. As you can see, an IP address is assigned to the interface, and then a virtual IP address 10.0.1.1. The timers, hello timer, is set to 10 seconds, and after 30 seconds, this device would be considered down and no longer participating. Then also note that the load balancing configuration as well, which is weighted. Now remember, there's many different types of GLBP load balancing. The key to remember is that that is one of the advantages of GLBP. Should you be asked on the CCNP switch exam, load balancing is a key feature of this protocol. And then finally, as you can see, you can set up authentication. IRDP allows hosts to locate routers that can be used as a gateway to reach IP-based devices on other networks. When the device running IRDP operates as a router, router discovery packets are generated. When the device running IRDP operates as a host, router discovery packets are received. IRDP uses ICMP router advertisements and ICMP router solicitation messages to work effectively, and it eliminates the need for manual configuration of gateway addresses on the network. In this specific example, we have 3 routers: router 1, router 2, and they're given certain priority levels of 190. And we have a third router brought online, which queries the network. It receives responses from the other IRDP routers, notifying the new router that they are available to route traffic. They are put in the local table for that router, and the router then forwards the traffic to the appropriate gateway. Should router 1 fail, then traffic would be forwarded over to router 2. All of this is done without manual configuration for gateway IP addresses. So here's what you've learned. You've received a basic introduction to high availability, and then you've also learned about the specific protocols that Cisco supports in order to ensure a highly available environment. This is a solid foundation for you as you prepare to pass your CCNP switch exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to receive an introduction to wireless LANs. Specifically, we're going to do an overview of wireless LANs, talk about wireless LAN components. We'll talk about the 802.11 standard in the OSI model, how it fits in the OSI model. Then MAC sublayer coordination, how that applies to wireless, 802.11 frame types, and finally, wireless LAN standards. So wireless LANs provide network connectivity almost anywhere. Surely you use wireless LANs. If you're in technology, surely you're using them, whether it's your mobile phone or your laptop, whether you're at a coffee shop or at your place of business doing BYOD. Wireless LANs typically can be implemented at much less cost than traditional wired LANs. The wired infrastructure is, of course, based on the 802.3 standards, but a wireless network uses radio waves to transmit data and to connect devices. So as you surely know, a wireless network uses radio waves to transmit data and connect devices. Wireless LANs are defined by the 802.11 standards. Now, some additional advantages of wireless LANs over wired LANs include the following: monetary cost, flexibility, that you allow users to roam in places where they normally cannot, or use their devices in places they always wish they could. Load distribution, and finally redundancy. And we'll get into this in a little bit, but using these wireless access points, multiple wireless access points in one area, can provide redundancy and load distribution at a much more affordable cost than wired LANs. Now, there are certain components that make up wireless LANs, and let's start with the client, specifically you or any of our customers. Clients are basically an appliance that interfaces with the wireless medium. Now, again, that could be a mobile device, it could be a laptop, it could be a tablet, it could be a PC, but it's basically a device that operates as an end user device. An access point functions as a bridge, basically, between the endpoints and the existing network backbone. So the access point is what the endpoints are actually communicating with. And as they roam, they may change access points throughout the building, but the access points are actually what are getting them access to the network. As you can see in this picture, access points come in many different shapes and sizes. These are just a few examples of access points. The distribution system plays a key role in communications between the customer who's trying to get on the wireless network and the major wireless LAN components that are actually routing the traffic. The distribution system allows for the interconnection of the APs of multiple cells. Think of your organization. If you have one area that's considered a lab and it's a wireless lab, and that ultimately needs to communicate with marketing on the 8th floor, you're going to need a distribution system to communicate between those two locations. The wireless distribution system allows you to connect multiple access points. So with wireless distribution systems, APs can communicate with one another without wires in a standardized way. Now, that being said, distribution could be wired or integrated. But this capability of communications between access points is absolutely critical in providing a seamless experience for roaming clients and for managing multiple wireless networks. It can also simplify the network infrastructure by reducing the amount of cabling required. Another concept you need to understand is the basic service set. The wireless architecture divides the system into cells, referred to as basic service set. And it's controlled by a base station, or more commonly, an access point. Now, an extended service set is a set of connected BSSs. And then there's the independent basic service set, which is a wireless network consisting of at least 2 endpoints and no distribution system. So let's draw this out so we can get a better understanding of what we learned thus far. So in any wireless implementation, you're going to have endpoints that need to connect. So for example, here's a laptop that is connecting to the wireless network. It connects to the wireless network through an access point. The access point is sending out the radio waves, which are being received by the laptop. The laptop endpoint then connects onto the wireless network, assuming it has the proper security configurations, and it can then reach the network. Now, access points can communicate not only with laptops, but again, mobile phones. And you can think of this as a basic service set. Now, let's say in a different area, we have another access point, which is also serving customers or users. And this again could be a server, it could be a workstation, could be a printer. But regardless, it's servicing endpoints. It's a different implementation, different part of the building or a different building altogether, but this is another basic service set. So how do these two basic service sets communicate? Well, they use, as you have already learned, they use a distribution system. These two DSs can uplink in many ways via wireless, or in this case that we're looking, here's a wired connection. This is the distribution system that is allowing these two separate wireless implementations or basic service sets to communicate. Now, if we look at the big picture, both of these basic service sets and the distribution system, the big picture, this is the extended service set. This includes all of the wireless equipment and any equipment used to connect the wireless equipment together. The IEEE 802 standards define two separate layers for the data link of the OSI model. As you know, these two layers are the LLC and the MAC sublayers. The 802.11 standards cover the operation of the MAC sublayer and the physical layer. The 802.11 frame consists of a 32-byte MAC header, variable length, and a frame check sequence. There are two types of coordinated functions used to ensure collision-free access on a wireless network. First, distributed coordination function. The MAC sublayer technique employs the well-known CCNA to avoid collisions. It's used to manage access to the radio frequency medium, and it's composed of the following two main components: interframe spaces and random backoff. And then there's point coordination function, and the PCF is used by the AP to coordinate communications with the wireless network. The 802.11 standard uses three main types of frames: control frames to control access to the medium, management frames to enable stations to establish and maintain communications, and then data frames sent by any endpoint. And these contain higher layer protocol information or data. Now, there are many 802.11 standards, but you should definitely know of these, and you probably already do know many of them. These standards have been rolled out over the years, and you've been on many of these networks, whether it's in your home or at your local coffee shop or at work. The initial 802.11 standard was serviced up to 2 megabits per second. At this point, we're at the 802.11n standard, which theoretically can provide up to 600 megabits per second of bandwidth. So here's what you've learned. We've done a wireless LAN overview. We've talked about wireless LAN components and how the 802.11 standard works with the OSI model. We've talked about MAC sublayer coordination and how that applies to wireless, 802.11 frame types, and finally, wireless LAN standards. Good luck with your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about the Cisco Unified Wireless Solution. Specifically, you're going to learn about access points, lightweight access points and lightweight access point protocol, wireless LAN controllers, discussing both the modes that it operates in and the interface types, and then mobility groups. So plenty to cover, and let's begin.
The Cisco Unified Wireless Network concept includes the following elements. Wireless clients, this includes laptops, workstations, etc. Access points, this provides access to the wireless network. Network management, this is accomplished through Network Wireless Control System. It's a centralized management tool that allows for design and control of wireless networks. Network unification, the wireless LAN system needs to be able to support wireless applications by offering unified security policies such as quality of service and RF management. So the WLCs, or wireless LAN controllers, offer this unified integration functionality. And then network services. Wireless network services are also referred to as mobility services and include guest access or voice services, location services, and even threat detection and mitigation. Standalone access points are also known as autonomous access points. They're obviously very easy to install, but the thing is they can be difficult to manage in large deployments. They're not as desirable as the lightweight access points from Cisco because they must be managed individually. In addition, different parameters must be configured manually on each device, including SSID, VLAN, and security features. The Cisco Unified Wireless Network introduced the concept of lightweight access points and wireless LAN controllers. That's LWAPs and WLCs. These two types of wireless devices divide responsibilities and functionalities that an autonomous access point would normally perform on its own. This technology adds scalability by separating the wireless LAN data plane from the control plane into a split MAC design. Lightweight access points focus only on the actual RF transmissions and the necessary real-time control operations, such as beaconing, probing, and buffering. Now, wireless LAN controllers manage all non-real-time tasks, such as SSID management, VLAN management, access point association management, authentication, and quality of service. When using lightweight access points, all RF traffic they receive must first go to the wireless LAN controller device that manages the specific access point. This changes the way in which traditional wireless LAN communication works, even for hosts associated to the same access point. The RF communication between lightweight access points and wireless LAN controllers is handled using the lightweight access point protocol. The lightweight access point tunnel can operate in either layer 2 or layer 3 mode. In layer 2 mode, the access point and wireless LAN controllers share the same VLAN, subnet, and functions with the lightweight access point, receiving 802.11 frames and encapsulating them inside Ethernet toward the wireless LAN controller. When the lightweight access point tunnel operates in layer 3 mode, the lightweight access point receives 802.11 frames and encapsulates them inside of UDP toward the wireless LAN controller. So this implies that the wireless LAN controller can be anywhere as long as it is reachable by the access point. The Cisco Lightweight Access Point Protocol can operate in the following 6 modes: local mode, REAP or Remote Edge Access Point mode, monitor, road detector mode, sniffer mode, and bridge mode. Every 180 seconds, the access point spends 60 milliseconds on channels on which it does not operate. During the 60 millisecond time period, the access point performs noise and interference measurements and scans for intrusion detection events. The REAP mode allows the lightweight access point to reside across a LAN link and still be able to communicate with the wireless LAN controller and provide the functionality of a regular lightweight access point. REAP mode is not supported on all lightweight access point models. Monitor mode is a special feature that allows lightweight access point enabled APs to exclude themselves from dealing with data traffic between clients. Instead, they act as dedicated sensors for location-based services, rogue AP detection, and for IDS. In RD mode, the lightweight access point monitors for rogue APs. The goal of this rogue detection of APs is to see all the VLANs in the network because rogue APs can be connected to any of those VLANs. Sniffer mode allows the lightweight access point to capture and forward all the packets on a particular channel to a remote machine that is running packet capturing software. And finally, bridge mode typically operates on outdoor APs that function in a mesh topology. This cost-effective high-bandwidth wireless bridging connectivity mechanism includes point-to-point or multi-point bridging. Wireless LAN controllers have the following three components: wireless LAN, interfaces, and ports. The wireless LAN is the SSID network name. Every wireless LAN is assigned to an interface in the wireless LAN controller, and each wireless LAN is configured with policies for RF, QS, and other LAN attributes. The interfaces are logical connections that map to a VLAN on the wired network. Every interface is configured with a unique IP address, default gateway, and physical ports. Wireless LAN controllers support the following 5 interface types: the management interface, which is used for in-band management or connectivity to a AAA server; an optional service port interface for out-of-band management that is statically configured; the access point manager interface used for layer 3 discovery and association; dynamic interfaces, these are the VLANs designated for wireless LAN client data; and virtual interfaces used for layer 3 security authentication, DHCP relay, and management of mobility features. One of the main features of a wireless LAN solution is the user's ability to access network resources from different areas. End users most likely move from one location to another, so designers should scale the wireless network carefully to allow for client roaming. Wireless roaming can be divided into the following 2 categories: intra-controller roaming or inter-controller roaming. Intra-controller roaming occurs when a client moves its association from one AP to another AP controlled by the same wireless LAN controller. Inter-controller roaming can operate in either layer 2 or layer 3 mode. In layer 2, inter-control roaming moves users from AP to AP and from WLC to WLC, but they remain in the same subnet. Layer 3 intercontroller roaming is more difficult to implement because users can move from AP to AP and WLC to WLC from subnet to subnet as well. In this scenario, the wireless LAN controllers must be configured with mobility groups. Now, speaking of mobility groups, you may be tested on the following communication ports for mobility groups: the Lightweight Access Point Protocol Control UDP 12223, Lightweight Access Point Protocol Data UDP 12222, Wireless LAN Controller Exchange Unencrypted Messages UDP 16666, and Wireless LAN Controller Exchange Encrypted Messages 16667. So here's what you've learned. You've learned about access points, lightweight access points and lightweight access point protocol, wireless LAN controller modes and interface types, as well as mobility groups. This gives you a good foundation for the wireless portion, at least for unified wireless solutions, and your Cisco CCDA exam. Good luck in your studies.
Hi, this is David Voss, CCIE 11372, and in this video we're covering wireless LAN design. We're first going to learn about redundancy and the importance of redundancy in wireless design. Then you'll learn about RF groups, and then we'll also talk about mesh design. So let's begin. Wireless LAN controllers can be configured for dynamic or deterministic redundancy. For deterministic redundancy, the AP is configured with a primary, secondary, and tertiary controller. This requires more upfront planning, but allows for better predictability and faster failover times. Deterministic redundancy is the recommended best practice. N plus 1, N plus N, and N plus N plus 1 are examples of deterministic redundancy.
With N+1 redundancy, a single wireless LAN controller acts as the backup of multiple wireless LAN controllers. The backup WLC is configured as the secondary WLC on each AP. One design constraint is that the backup WLC might become oversubscribed if there are too many failures of the primary controllers. The secondary WLC is the backup controller for all APs and is normally placed in the data center. With N+N redundancy, an equal number of controllers back each other up. For example, a pair of WLCs on one floor serves as a backup to a second pair on another floor. The top WLC is primary for AP1 and AP2, and the secondary for AP3 and AP4. The bottom WLC is the primary for AP3 and AP4, and secondary for AP1 and AP2. There should be enough capacity on each controller to manage a failover situation. With N+N+1 redundancy, an equal number of controllers back each other up. Plus, a backup WLC is configured as the tertiary. N+N+1 redundancy functions the same as N+N redundancy plus a tertiary controller that backs up the secondary controllers. The tertiary WLC is placed in the data center or network operations center. Here is a summary of wireless LAN controller redundancy. It would be good to memorize this in preparation for your exam. Next, let's talk about radio management and radio groups. The limit of available channels in the ISM frequencies used by IEEE 802.11b, G, and N standard presents challenges to the network designer. There are 3 non-overlapping channels, channels 1, 6, and 11. The recommended best practice is to limit the number of data devices connected to each AP to 20, or not more than 7 concurrent voice over wireless LAN calls using G711. An RF group is a cluster of WLC devices that coordinate their RRM calculations. RF groups are formed with the following process. APs send out neighbor messages over the air. The message includes an encrypted shared secret that is configured on the WLC and pushed to each AP. APs sharing the same secret are able to validate messages from each other. The members in the RF group elect an RF group leader to maintain a master power and channel scheme for the RF group. Similar to performing an assessment for a wired network design, RF surveys are done to determine design parameters for wireless LANs and customer requirements. RF site surveys help determine the coverage areas and check for RF interference. This helps determine the appropriate placement of wireless APs. The RF site survey has the following steps. Define customer requirements such as service levels and support for VoIP. Determine devices to support. Obtain a facility diagram to identify the potential RF obstacles. Visually inspect the facility to look for potential barriers to the propagation of RF signals. Identify user areas that may be intensively used, such as conference rooms, and areas that are not heavily used, such as stairwells. Determine preliminary AP locations, which need power, wired network access, cell coverage, and overlap, not to mention channel selection, mounting locations, and antennas. Let's talk about wireless mesh for outdoor wireless. Traditionally, outdoor wireless solutions have been limited to point-to-point, point-to-multipoint bridging between buildings. With these solutions, each AP is wired to the network. The Cisco Wireless Mesh Networking solution eliminates the need to wire each AP and allows users to roam from one area to another without having to reconnect. The wireless mesh components are shown here. The WCS, the WLC, the RAP, and the MAP. The following are Cisco recommendations for mesh design. There is under 10 millisecond latency per hop, typically 2 to 3 millisecond. For outdoor deployment, 4 or fewer hops are recommended for best performance, with a maximum of 8. For indoor deployment, 1 hop is supported. For best performance, 20 MAP nodes per RAP is recommended. Up to 32 maps is supported per RAP. Throughput 1 hop 14 megabits per second, 2 hops 7 megabits per second, 3 hops 3 megabit, and 4 hops 1 megabits per second. As you can see here, you have 5 primary design items: number of APs, placement of APs, power for APs, number of WLCs, and placement of WLCs. The following points summarize wireless LAN design. An RF site survey is used to determine a wireless network's RF characteristics and AP placement. Outdoor wireless networks are supported using outdoor APs and Cisco Wireless Mesh Networking APs. Campus wireless network design provides RF coverage for wireless clients in the campus using LWAPs. Each AP should be limited to 20 data devices and a data wireless LAN. So here's what you've learned. You've learned about wireless redundancy, RF groups, and mesh design. All are key points on the CCNA exam that you will need to know and be able to answer, not only on your exam, but of course if you support wireless in your own network. Good luck in your studies.
In this lesson, we will discuss the cloud terminology. Virtualization. Virtualization is the creation of a virtual rather than actual version of something, such as operating systems, servers, storage devices, or network resources. In this figure, we can see many virtual servers created by 3 physical servers. By using virtualization, we can achieve cloud computing. Virtualization shares hardware resources among different virtual machines or servers. Cloud computing uses virtualization and shares virtual servers with multiple users. Location is no longer a constraint. In this figure, we can see that we can access cloud computing resources from any device. The main advantage in cloud computing is we can add or remove resources at any given point of time. In cloud computing, ownership of physical servers resides with one organization, and users are billed for their usage. Cloud computing means the sharing of pooled computing resources over the internet. Now we will look at types of cloud computing. Software as a Service, or SaaS. This type of cloud computing provides answers to desktop needs for end users. Software as a Service is a software distribution model in which applications are hosted by a vendor or service provider and made available to customers over a network, typically the internet. Platform as a Service. This type of cloud computing enables developers to create and test software without investing in expensive hardware. In the figure, we can see Platform as a Service is a way to rent hardware, operating systems, storage, and network capacity over the internet. The service delivery model allows the customer to rent virtualized servers and associated services for running existing applications or developing and testing new ones. Infrastructure as a Service. This type of cloud computing enables applications to run in the cloud instead of using their own infrastructure. In the figure, we can see that infrastructure as a service is a provision model in which the organization outsources the equipment used to support operations, including storage, hardware, servers, and networking components. The service provider owns the equipment and is responsible for housing, running, and maintaining it. The client typically pays on a per-use basis. Now we will take a look at different types of cloud computing resources. These are all the cloud computing resources an organization can use: email accounts, servers, virtual machines, data storage, websites, and data backup. In this lesson, we came to know the cloud terminology. In the next lesson, we will discuss the characteristics of cloud computing. Thank you. In this lesson, we will discuss the characteristics of cloud computing. According to the National Institute of Standards and Technology, the cloud computing services consist of the below attributes: elasticity, on demand, pooled computing resources at the provider's site, monitored and measured service usage, and broad network access. In this figure, we can see that cloud computing has 5 major characteristics. They are measured service, on-demand self-service, broad network access, resource pooling, and rapid elasticity. Now we will discuss all of these characteristics individually. Elasticity. This attribute enables us to add or remove the cloud computing services or users at any time based on the client's business activity. On demand. The users can access the services from anywhere, anytime, and at any location. This will increase the availability of cloud computing services. Pooled computing resources at the provider's site. The cloud computing provider has to invest its money in proper hardware, configuration, and maintenance. The provider has to keep an eye on physical infrastructure usage. Monitored and measured service usage. Mostly, cloud computing services will come with monthly subscription and usage fees. Cloud service providers will charge by usage of measured resources, like disk space and processing capability, with respect to time. Broad network access. The client can access the services from any device, for example, smartphone, tablet, laptop, or desktop computer, over the Internet. In the picture, we can see that cloud services can be accessed from anywhere on any device. In this lesson, we learned the characteristics of cloud computing. In the next lesson, we will discuss virtualization and cloud computing in an organization. Thank you.
Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about network programmability. Specifically, we're going to talk about Cisco's implementation of SCN, Cisco ACI, and we'll discuss its benefits and its attributes. All of this you should know for your CCDA exam. So let's go ahead and begin. IT departments and lines of business are looking at cloud automation tools and software-defined networking architectures to accelerate application delivery, reduce operating costs, and greatly increase business agility. Cisco Application-Centric Infrastructure, or Cisco ACI, is a comprehensive SDN architecture. This policy-based automation solution supports a business-relevant application policy language, greater scalability through a distributed enforcement system, and greater network visibility. These benefits are achieved through the integration of physical and virtual environments under one policy model for networks, servers, storage, services, and security. Through Cisco ACI, customers are reducing application deployment times from weeks to minutes. It also dramatically improves IT alignment with business objectives and policy requirements. Cisco ACI is built on the application-centric policy based on Cisco Application Policy Infrastructure Controller, or what is known as APIC, the Cisco ACI Fabric, which is based on the Cisco Nexus 9000 series switches, and the Cisco Application Virtual Switch, and the Cisco ACI Partner Ecosystem. ACI provides a network that is deployed, monitored, and managed in a way that benefits different teams in the IT organization, including SDN network, cloud and DevOps, and security. It supports rapid application change by reducing complexity with a common policy framework that can automate provisioning and resource management. You can facilitate rapid systems integration and customization for network services, monitoring, management, and orchestration. Cisco ACI is a comprehensive SDN solution, making the application the focal point. It is delivered in an agile, open, and highly secure architecture, and its application-based policy model offers speed through automation, reducing errors and accelerating application deployment in IT processes from weeks to minutes. Application-based policies decouple high-level application connectivity needs from the complicated details of network configuration. This results in automated IT processes that simplify operations. ACI provides transparent support of heterogeneous physical and virtual endpoints, such as bare metal servers and virtual servers on any hypervisor, with layer 2 to 7 network services using consistent policy. This provides faster troubleshooting through increased visibility of the entire infrastructure. Cisco ACI supports open APIs, open source, and open standards to optimize customer choice and flexibility. In fact, Cisco contributes technology specifications to open source and standards communities. The open integration with existing data center management tools and comprehensive open partner ecosystem helps to ensure flexibility while decreasing costs and increasing innovation. Provisioning applications has become easy with programmable infrastructure, yet onboarding them is still difficult. Cloud architects have to know what infrastructure design will support frequent application changes to performance, security, availability, and scale. DevOps has to work with both application and admin teams to understand how numerous application changes affect the configuration of switches, ports, VLANs, firewalls, security appliances, load balancers, and other application delivery functions. All changes must work within a shared production infrastructure without affecting existing tenants and applications. Cisco ACI introduces a simple application-level policy-based approach. Application intentions are automatically translated to infrastructure design without requiring knowledge of devices or the effort to translate to configurations. This helps to enable policy-aware resource orchestration, real-time governance, and open choice in cloud software. Cisco ACI and the APIC SDN controller allow for security policies down to the individual tenant, application, or workload. They provide protection that meets the most stringent business and compliance requirements. The whitelist model permits the communication only where explicitly allowed, helping to ensure that policy omissions do not leave security vulnerabilities. Through Cisco ACI, all security device provisioning and configuration can be automated according to the centrally managed application policies and requirements. This simplifies IT security tasks and accelerates application deployments. The Cisco Nexus 9000 series switches bring new industry-leading performance, power, port density, and open programming innovations. The products that support Cisco ACI are the Cisco Nexus 9000 series. In addition, the Cisco Application Virtual Switch, which provides a consistent virtual switch infrastructure between ACI fabrics and the Cisco Nexus 1000V virtual switch. The Cisco Application Policy Infrastructure Controller, which programmatically automates network provisioning and control based on application requirements and policies. And the Cisco Application-Centric Infrastructure Security for data centers solves many complexities in customer environments. It treats firewalls as a pool of resources and intelligently stitches them according to application network policies. ACI Security offers full acceleration dynamically in hardware and directly integrates into Cisco ACI. When considering Cisco ACI, it's important to define desired business outcomes and plan each stage of the journey. Then you'll want to know how to accelerate the benefits of ACI while mitigating the risks. You need to develop an ACI adoption strategy based on business and technology needs. You need to provide a migration strategy and operational readiness. You need to deploy proof of concept to gain experience and reduce the deployment risk. And then design application-centric data centers based on the ACI fabric pods and policy templates. So here's what you've learned. You've learned about Cisco's deployment of software-defined networking, which is Cisco ACI. This you'll need to know for your CCDA exam, but more importantly, you will need to know this if you're going to work in the future of network engineering. Good luck in your studies.
Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about designing quality of service. Specifically, we're going to be going over the following categories of quality of service: classification, congestion management, link efficiency mechanisms, and then traffic shaping and policing. Let's talk about quality of service at a higher level, and then discuss the quality of service concepts that Cisco wants you to know for the CCDA exam. Quality of service is a tool for managing a WAN's available bandwidth. Now, quality of service does not add bandwidth, but it helps you make better use of what you have. If you have chronic congestion issues, quality of service should not be the primary answer to resolving that problem. You need to add more bandwidth. However, by prioritizing traffic using quality of service, you can make sure that your most critical traffic gets the best treatment and available bandwidth in times of congestion. One popular quality of service technique is to classify your traffic based on a specific protocol type or matching access list, and then giving a policy treatment to that specific class. You can define many classes to match or identify your most important traffic classes, for example, video or voice. And then the remaining unmatched traffic then uses a default class, which is the traffic that can be treated as best effort. So let's begin with classification. For a flow to have priority, it must first be identified and marked. Both of these tasks are referred to as classification. The following are popular technologies which support classification: NBAR,
It's a technology that uses deep packet content inspection to identify network applications. So an advantage of NBAR is that it can recognize applications even when they do not use standard network ports. Also, it matches fields at the application layer. Before NBAR, classification was limited to layer 4 TCP and UDP port numbers, but NBAR has changed that. Next is CAR, committed access rate, and uses an ACL to set precedence and allows customization of the precedence assignment by the user, source or destination IP address, or even application type. Next, let's talk about congestion management. There are two types of output queues that are available on routers, hardware and software. The hardware queue simply uses FIFO, first in, first out. But the software queue schedules packets first and then places them in the hardware queue. Now keep in mind that the software queue is only used during periods of congestion. The software queue uses quality of service techniques such as priority queuing, custom queuing, weighted fair queuing, class-based weighted fair queuing, low latency queuing, and traffic shaping and policing. Let's go through each of one of those. Cisco does not expect you to know each of these in detail. Again, that would be later in your CCDP studies. But that being said, they want you to understand what each of these are. Priority queuing is a queuing method that establishes 4 interface output queues that serve different priority levels, which are high, medium, default, and low. Unfortunately, priority queuing can starve other queues if too much data is in one queue, because higher priority queues must be emptied first before lower priority queues. Next, there is custom queuing. It uses up to 16 individual output queues. Byte-sized limits are assigned to each queue so that when the limit is reached, it proceeds to the next queue. The network operator can customize these limits, and custom queuing is obviously fairer than priority queuing because it allows some level of service to all traffic. But this is really a legacy solution because there are improvements in the queuing methods, which we'll talk about next. Weighted fair queuing ensures that traffic is separated into individual flows or sessions without requiring that you define access lists. Weighted fair queuing uses 2 categories to group sessions, high and low bandwidth. Low bandwidth traffic has priority over high bandwidth traffic, and high bandwidth traffic shares the service according to assigned weight values. Please know that weighted fair queuing is the default quality of service mechanism on interfaces below 2 megabits per second. Weighted fair queuing is not the best option in every scenario because it doesn't provide enough control in the configuration. But it is far better than the first in, first out approach because interactive traffic flows that generally use small packets do get the priority they need in the software queue. As you can see in this diagram, the different weighted fair queue traffic flows are placed into different queues before entering the weighted fair queue scheduler, which will then allow them to pass to the hardware queue based upon the defined logic. If one queue fills, the packets will be dropped, but this will also be based on the weighted fair queue approach. That is, lower priority packets are dropped first, as opposed to the first in, first out approach of tail dropping. Next is class-based weighted fair queuing. It extends weighted fair queuing capabilities by providing support for modular user-defined traffic classes. Class-based weighted fair queuing lets you define traffic classes that correspond to match criteria, including ACLs, protocols, and input interfaces. Traffic that matches the class criteria belongs to that specific class, and each class has a defined queue that corresponds to an output interface. So after traffic has been matched and belongs to a specific class, you can modify its characteristics such as assigning bandwidth, maximum queue limit, and weight. As you see in the picture here, certain classes receive higher priority than other classes. As you can see here,
Class-based weighted fair queuing logic is based on the class-based weighted fair queue scheduler that receives information from queues defined for different forms of traffic. The traffic that does not fit any manually defined queue automatically falls into the class default queue. These queues can be assigned minimum bandwidth guarantees for all traffic classes. Class-based weighted fair queuing offers powerful methodologies for controlling exactly how much bandwidth these various classifications will receive. If it contains more than one traffic type, each individual queue will use the first in, first out method inside the hardware queue. So the network designer should not combine too many forms of traffic inside of a single queue. Considering the inefficiency of class-based weighted fair queuing when using VoIP, another quality of service technique was developed, and that is low latency queuing. Adding a priority queue to class-based weighted fair queuing will not lead to starvation because this queue is policed so that the amount of bandwidth guaranteed simply for voice cannot exceed a particular value. Since voice traffic gets its own priority treatment, the remaining traffic forms will use weighted fair queuing based on bandwidth reservation values. Unlike priority queuing, low latency queuing provides for a maximum threshold on the priority queue, and this will prevent lower priority traffic from being starved by the priority queue. Now that we've talked about queuing, let's talk about traffic shaping and policing. Traffic shaping and policing are mechanisms that inspect traffic and then take action based on the traffic's characteristics, such as DSCP or IP precedence bits set in the IP header. Traffic shaping slows down the rate at which packets are sent out an interface by matching certain criteria. Traffic shaping uses a token bucket technique to release the packets into the output queue at a pre-configured rate. So this helps eliminate potential bottlenecks by throttling back the traffic rate at the source. Traffic shaping is used on larger networks to smooth the flow of traffic going out to the provider. This is desirable for a few reasons. In provider networks, it prevents the provider from dropping traffic that exceeds the contracted rate. Now, policing is a little bit different because it tags or drops traffic depending on the match criteria. Generally speaking, policing is used to set the limit of incoming traffic into an interface, and then it will drop traffic that exceeds what the settings were. One example of using policing is to give preferential treatment to critical application traffic by elevating to a higher class and reducing best effort traffic to a lower priority class. The best way to compare shaping with policing is to remember that shaping buffers packets. Policing does not. It can be configured to drop packets. Our final topic is link efficiency. Within Cisco iOS, there are several link efficiency mechanisms available, as you can see here. There's LFI, which is used to reduce delay or jitter on slower speed links. Multi-link PPP, which bonds multiple links together between two nodes, which can increase available bandwidth. And then RTP, real-time transport header compression, which provides increased efficiency for applications that take advantage of RTP on slower links. So here's what you've learned. You've received a high-level overview of quality of service, and then you learn about quality of service functions such as classification, congestion management, link efficiency mechanisms, and then traffic shaping and policing. And I wish you the best of luck in your studies.
Cisco Express Forwarding and Planes of Operation. Now actually Planes of Operation isn't really specified in the CCNA syllabus, which is a little bit bewildering because they mention Cisco Express Forwarding, which is what we call CEF for short. It's just a little bit strange. But here's a diagram. There's different planes of operation on routers, and some of it depends on the platform you're using. So this particular diagram isn't set in stone, but this is a concept for you to be aware of. And you'll hear people mention data plane, control plane, management plane. So the control plane, you can consider the brains of the router. This is where all the routing, ARP and ICMP takes place. The data forwarding plane is where the switching of packets takes place, and you can see that at the bottom of the diagram here. And then you've got the management plane. This is where we manage the device over the network, and we've already discussed connecting to devices using Telnet, SSH, and managing them using SNMP. So just something for you to be aware of and to put things into perspective. So packet switching, there's different types of, or different ways to switch packets. Process switching, which is defunct now really, the CPU is used for every packet forwarded, which, as you can imagine, on high-speed links and links of heavy utilization, is just very inefficient. So this was replaced by fast switching, where the path is cached and the cache is actually used repeatedly rather than the CPU referenced every time. And then there's Ceph, Cisco Express Forwarding, where there's tables built with all the relevant information that's needed in order to switch the packet. So speaking of Ceph, it's proprietary to Cisco, and what it does is create a forwarding table based upon the routing table. Now, information is stored in hardware, which, as you know, or probably do know, is much faster than doing it in software, far faster. There's a FIB, forwarding information base, built. This is a map of the next hops and the next networks. And there's an adjacency table built. This keeps track of layer 2 addresses for the next hop, so there isn't the continual problem with sending and receiving ARP requests. So it makes things a lot quicker. You've got accelerated and distributed Ceph. This fixes the issue of having one hardware dealing with all layer 3 functions. Accelerated Ceph sends some of the FIB to powerful cards. This is on high-end switches, which we don't cover in the CCNA, and you kind of touch upon in the CCNP switch module. We talk about cards going on to the switches, the higher end switches. DCEF has multiple Ceph tables and distributes across multiple line cards. Configuring Ceph, it's actually on by default, so you wouldn't need to configure it. There's no command to enable a Ceph. If you want to enable Ceph because it's been turned off for whatever reason, you just go to config T and type IP Ceph. For distributed Ceph, it's IP Ceph distributed. Just worth remembering those commands in case they ask you about them, and also just bear in mind the different types of tables that are used by Ceph. But I'll just bring all this up because it's one of the CCNA syllabus exam topics. Alright, that's all. Thanks for listening.
Hi, this is David Voss, CCIE 11372, and in this video we will be covering troubleshooting virtual LANs. So here's what you're going to learn. We're going to do a basic VLAN review as a refresher. We'll talk about troubleshooting VLANs, how you do that, and some of the commands that you would run to troubleshoot. And then finally we'll give you a challenge to see how you do as you prepare for your CCNP troubleshooting exam. A switch network can be partitioned to create multiple distinct broadcast domains, and the reasons for this are many, but let's just focus on the fact now that you can break up your network into broadcast domains, and each of these domains are considered a virtual LAN. Now, packets are then forwarded only within this virtual LAN unless you have a router. If you have a router or a layer 3 device, you can then pass packets between these virtual local area networks. Let's just draw this concept out to make sure you got it. I know you probably do, but let's make sure we're all on the same page. So Here we have 4 computers. 2 of them are in VLAN 1, 2 of them are in VLAN 2. They all connect to the same switch. So the computers on VLAN 1 can only communicate with one another, and the computers on VLAN 2 can only communicate with one another. The switch is basically broken out into 2 separate broadcast domains. These computers between VLAN 1 and VLAN 2 cannot communicate to each other. So they are truly segmented. Now, as the network grows, you still want to have other computers communicating throughout your network. So we have another 2 computers on VLAN 1 and another computer on VLAN 2. And they can communicate from switch to switch as they need to. Again, computers on VLAN 1 and 2 can communicate with one another. And here we have a trunk link. So VLAN 1 and 2 are allowed over the trunk. Now, let's say we want to communicate between VLAN 1 and VLAN 2. We would need a routed device. Now, in the old days, you would just do a router on a stick, connect a router to a switch. VLAN 1 would go up to the router would then route over to VLAN 2. And things have obviously changed in the past 10 years, and a more popular option now is to use switched virtual interfaces, basically turning the switch into a layer 3 device, enabling IP routing. VLAN 1 sends it to the default gateway SVI to the VLAN 2 SVI, and then you can communicate that way. Now on this trunk, you can filter out VLAN. So here, let's filter out VLAN 2. And what happens here is now these 2 computers on VLAN 2 are basically segmented, and this other computer is basically isolated. These computers on VLAN 2 can't communicate from switch to switch. So let's talk about troubleshooting VLANs. Now, when troubleshooting an issue where 2 points are trying to communicate in the same VLAN, just consider 3 simple points when troubleshooting, actually in this order as well. Take a look at the local VLAN configuration. Are the ports in the correct VLAN? Then verify the switch path, first by checking to make sure the MAC address is actually on the switch, and then finally check trunk configuration. Let's talk about these. Basically, you want to keep it simple. Just verify that the switch ports are actually in the proper VLAN. And then actually understand how a frame should flow through a layer 2 portion of the network, starting with the port itself. So if the switch has not learned the MAC address of the sender, you know you found your problem right there. You check your hardware and your software upstream from the switch or even on the endpoint. And then if it has learned the MAC address, then work your way along the layer 2 path. And when you work your way along the layer 2 path, you're going to bump into trunks. Now, switches are often interconnected using an Ethernet trunk, and a trunk has a unique capability to carry traffic from multiple VLANs over a single link. So what you'll want to do on trunks is you want to make sure that the configurations are correct, that the same trunking encapsulation is on both ends, make sure that they have a common native VLAN, and then make sure the VLANs in question have not been excluded on a trunk by manual programming. Let's draw out this concept of troubleshooting. Let's say we have 2 devices, both in VLAN 10, on different parts of the network connected to different switches. And let's say that they cannot communicate and you're given a call to try to fix this problem. Let's actually expand this network to 4 switches. And let's say we've got a 3rd device on VLAN 10 somewhere else in the network, and none of them can communicate with one another. The first thing you want to do is make sure that the MAC address for each of these devices is actually known by the correct port. So under Fast Ethernet 01 and 03 and 04, make sure that the MAC address is actually showing up on the switch itself. Then you want to make sure that the ports are in the correct VLAN. So you'll check a manual configuration, making sure that Fast Ethernet 01, 03, and 04 are all in the correct VLAN. And finally, is VLAN 10 allowed over trunking ports? Is VLAN 10 filtered anywhere on the network? And if it is, then you've found your problem. So you want to start actually with the end device and then work your way forward. So here are some important troubleshooting commands you need to know. Clear MAC address table dynamic. This will actually clear the learned MAC addresses from a switched MAC address table, and it can help you determine if a previously learned MAC address is actually relearned and that the host is still alive. The next command is show MAC address table, which displays the MAC addresses learned by a switch, along with the associated port and VLAN of that MAC address. Next, show VLAN, which simply shows which ports of the switch belong to which VLAN. The next command is show interfaces trunk, which displays which VLANs are permitted on a trunk. And this is helpful as you troubleshoot downstream. And then show interfaces switch port, a command a lot of people don't use, but it's actually very effective because it displays summary information for the ports on a switch, including VLAN and trunk configuration information. And then finally, traceroute MAC source to destination. So this uses CDP information, and it produces a list of switches that are transited for traffic traveling from one MAC address to another. Again, a command a lot of people don't know about, but certainly should. So let's start off with some basic troubleshooting. You've received a call from the help desk, and they're stating that none of the desktop users can print, and the printer seems to be working fine, and all they know is that the printer is connected to a switch Fast Ethernet 024. And they're looking for some help because they think it might be a network issue since the printer seems to be working fine. But nobody on the floor can print to this printer. So you've logged into the switch, and you're going to take a look. Now, remembering the commands you've learned thus far, you're going to run the simple command show VLAN. And once you do that, see if anything stands out to you based on the information you have so far. Take a look at what VLAN Fast Ethernet 024 is in. Now, the only complaint we've gotten is that the desktops can't print to this printer. It should probably be in VLAN 10. And here we can see Fast Ethernet 024 is actually in VLAN 20, which is a server VLAN. So what we're going to do is go ahead and resolve the problem. Log in. We're going to configure Fast Ethernet 024. Change the VLAN it is associated with to VLAN 10. And let's take a look at show VLAN one more time. And here we can see Fast Ethernet 024 is now in the desktop VLAN. Let's move on to another issue. In this issue, we have two desktop computers who cannot communicate over the network. Both computers are in VLAN 10. One computer is connected to switch 1, port 01. The other computer is connected to switch 3, port 010. And then we have a trunk between them on port 18 and 15. Now, as you look through the show commands, I will tell you that there are going to be two issues in this problem. So I won't tell you exactly what's wrong, but keep your eye out for the two problems that need to be resolved. So we've logged on to switch 1. And the first command we'll run is simply show VLAN. And let's take a look at Fast Ethernet 01 and see if it is in the correct VLAN. Do you see that it is, or is it not? Then let's log on to switch 3, and let's do the same thing. Remember, we're starting at the host ports. Show VLAN, looking at port 010. Is it in the correct VLAN, or is it not? And now that we've verified the endpoints, both computers are in the correct VLAN. The ports assigned are in the correct VLAN. On switch 1, let's take a look at the trunking configuration. Do you see any issues
with the programming on the trunk for Fast Ethernet 018. Does anything stand out to you? Which VLANs are allowed? Which encapsulation is set? What is the status? And let's go over to switch 3 and check the same thing. Which VLANs are allowed? What is the encapsulation? So hopefully now 2 issues, not just one, but 2 issues are standing out to you. 2 things need to be resolved. If you look at Fast Ethernet 015, the trunk port, we can see that the encapsulation is .1Q, which is fine, but it's not allowing VLAN 10. We need to allow VLAN 10 on 015. That way, this VLAN will be passed over the trunk. So we're going to add VLAN 10, and while we're at it, we're also going to remove VLAN 20. You can see here the encapsulation is 802.1Q. Now if you noticed on switch 1, the encapsulation was actually ISL. So we have a mismatch in the trunk encapsulation. Regardless of what VLANs we allow over this trunk, nothing is going to pass until we resolve that. And let's go ahead and go with the industry standard and make the change on switch 1, changing the trunk encapsulation to 802.1Q. So here's what you've learned. We've done a basic VLAN review to make sure we're all up to speed on that. We've talked about how you can troubleshoot VLAN connectivity. Then we also went into depth on VLAN troubleshooting commands. And then finally, we gave you a couple challenges that will help you prepare for your exam, but also make you a better engineer. I wish you the best of luck in your studies. Thank you. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about troubleshooting Inter-VLAN routing in support of your CCNP troubleshoot exam. So here's what you're going to learn. We're going to do a basic VLAN routing review, and then we'll talk about routing using a switch versus a router, understanding the control and data plane, which will help you in your troubleshooting, and then VLAN routing troubleshooting and commands. And finally, we'll give you a VLAN routing troubleshooting challenge. So let's start with the basics. A VLAN is a switched network that is partitioned to create multiple distinct broadcast domains. So packets can only flow within a VLAN, and if you need to get a packet from one VLAN to another, they must be routed. Now you can route packets using a switch or a router, but there's some pretty big differences. But there's also a few similarities as well. Let's take a look at this chart. Here are some similar characteristics between layer 3 switching and routing. Both can maintain a routing table, and both make packet forwarding decisions based on layer 3 information from that routing table. And here are a few of the major differences. Routers in general support a wider selection of interface types. Switches leverage application-specific integrated circuits for faster throughput, or as you probably know them, ASICs. And then the iOS running on routers typically supports more features than an iOS version running on a layer 3 switch. So to summarize, although a router provides you with more features and modules in routing, as far as performance goes, the layer 3 switches actually boast of better performance in routing packets than routers do. Let's go ahead and draw some of these concepts out. So we have two switches, and let's say we have a VLAN 10 and a VLAN 20. And VLAN 10 and 20 endpoints are dispersed throughout our enterprise. Over the trunk link, we're allowing VLAN 10 and 20 so that all devices on VLAN 10 and 20 throughout the enterprise can communicate within their respective VLAN. Now note, there's no routing device yet. 10 and 20 can't communicate with each other. And in the old days, what would happen is they put a router on a stick. You connect a router directly to the switch. You can still do that now. If VLAN 10 wants to communicate to VLAN 20, the router will then forward the packet. But now what's actually more popular, it's actually a layer 3 option of the switch, but you create a switch virtual interface at an IP address. That becomes the gateway. And then a device on VLAN 10 can communicate to the SVI on VLAN 10 over to VLAN 20. So you don't need to deploy a specific router. You can enable the layer 3 function as well. And again, if VLAN 20 wants to communicate over to VLAN 10, it uses the switch virtual interface. Here's something that both switches and routers have in common that you should be aware of to help you in your troubleshooting. Many routers and layer 3 switch operations can be categorized as control plane or data plane operations. The control plane handles the routing protocols, and the troubleshooting commands are actually identical on both a layer 3 switch and router platforms. But on the data plane, that handles the forwarding of the data. And the troubleshooting commands on the data plane vary because layer 3 switches and routers really have fundamental differences in the way traffic is handled. Here's another concept you need to be aware of, and that is Ceph. Ceph creates a couple of tables that reside on the data plane, and that is the FIB or the forwarding information base and the adjacency table. When troubleshooting inter-VLAN routing, you should first check control plane operations with commands such as show IP route. And if the observed traffic behavior contradicts information shown in the out pane of control plane verification and commands, then you would look at the data plane. And that is verifying information contained in the router FIB and adjacency tables. Here's a command that can help you do that. Show IP Ceph. This will display the router's layer 3 forwarding information in addition to multicast, broadcast, and local IP addresses. And then there's the show adjacency command, which verifies that a valid adjacency exists for a connected host. Now these are commands you probably haven't run very often, but they're important to note not only to be a stronger engineer, but for your exam. Now let's embrace this concept of SVI or switch virtual interface. Make sure we fully understand what it is. On an SVI, you configure the IP address for a collection of ports belonging to a VLAN under a virtual LAN interface. So for example, if you had a bunch of ports on VLAN 10, on the SVI, you could configure the gateway IP address for VLAN 10 on the SVI. If you had a host that was 10.10.10.10, the gateway could be put on the SVI on the switch, the default gateway of 10.10.10.1. And therefore your switch is acting as a layer 3 router. Another way you can use a switch as a router is to actually assign a routed port. And this is actually specifically assigning an IP address to a physical port. Now, you need to keep in mind the distinctions between SVIs and routed ports when you're troubleshooting. A routed port is considered to be down if it is not operational at both layer 1 and layer 2. An SVI is considered to be down only when none of the ports in the corresponding VLAN are active. And it's important to note that a routed port does not run switch port protocols such as STP or DTP. So let's just do some basic troubleshooting to get started with inter-VLAN routing troubleshooting. So last night, a network engineer rolled out a new subnet 10.10.100.0 for users on a new VLAN 10. But the problem is, as soon as you got in this morning, you received a call from users on that subnet saying that
They can share files between each other, but they cannot share files outside of their subnet. They can't reach servers, they can't print, they can't do anything. They can't reach their email, and they can't browse the internet. So you know two things. They can reach each other locally on VLAN 10, but they cannot get beyond VLAN 10. Using one user as an example, we'll go ahead and first take a look and log on to the switch that the user is on. And this user is connected to Fast Ethernet 024. And the first thing we'll do is we'll just look at Fast Ethernet 024 to make sure that this new VLAN and subnet were rolled out correctly. And as we can see here on Fast Ethernet 024, everything's programmed correctly. The port is correctly assigned to VLAN 10. The next thing we want to do is take a look at the SVI. And let's see how the SVI is programmed. And as you can see here, it appears we found our problem. That when the engineer implemented the SVI for VLAN 10, they put in the incorrect subnet. Now I realize this is a very straightforward problem and one that's easy to resolve. But the important point I wanted you to take from this is how to resolve inter-VLAN routing problems. Generally speaking, you still want to honor the troubleshooting techniques of starting as close to the problem as possible. And so you want to start with the hosts. Just make sure they're assigned to the correct VLAN, which we did. And then the next step with inter-VLAN routing is you want to go ahead and check the SVI interface. Make sure that it has the correct IP address. Make sure that it is in fact up and that there are no programming errors. In this next troubleshooting session, I just want you to get focused on using control and data plane troubleshooting. As engineers, normally we just focus on control plane troubleshooting, which is checking IP routing. Well, we have a routing issue here that I want you to use control and data plane troubleshooting to tell if a switch is having a problem or not, to isolate a problem. So we've received a call that users cannot connect to 172.16.1.0/24 from switch 1 or switch 3. Users are connecting to that network using the layer 3 capabilities of these two switches. They both have SVIs for VLAN 10, and they each have an IP address assigned to their SVI. So what we want to do is we're going to start with switch 1, and let's see if we can isolate the problem on switch 1, or if we can confidently say that switch 1 is not the problem and isolate it to switch 3. Let's use control and data plane troubleshooting to do that. So on switch 1, let's just check the VLANs, and we see that VLAN 10 is supporting desktops, and we have 2 ports in VLAN 10. Next, let's check the control plane by doing a show IP route. We see that we have a valid static route, 172.16.1.0, pointing over to switch 3's SVI. We also see that we are correctly supporting the 10.10.100.network locally. So now that we've checked the control plane, let's check the data plane to see if there are any issues on this switch. So we'll check the Ceph table. Do we have a valid entry? Take a look and you tell me. Do we have a valid entry for this network that we're trying to troubleshoot? And in fact we do. 172.16.1.0 pointing over to the SVI of switch 3. We check the adjacency table, again, data plane troubleshooting, and we see here we have a valid entry. Now notice here the number in the parentheses is the number of entries this network has in the fib table. And now that we know that we have a valid route to 172.16.1.0 on this switch, and we've checked the control plane and the data plane, the next step is to start looking external to the switch. So let's test connectivity over to the next hop, which is 10.10.100.2 over the trunk we have between switch 1 and switch 3. And we can see here there's no connectivity to our next hop. Let's take a look to make sure that the SVI on switch 1 is actually up and running. And here we can see that it is. So now we need to focus on,
is this a trunk problem? So let's take a look at the trunk on switch 1. And we can see on the trunk that we have 802.1q programmed and that VLAN 10 is allowed. So far so good. It appears to be correct. Our SVI is up. We do have a route for it on the control and data plane on this switch. So switch 1 appears to be working just fine. The next step is to go on to switch 3. And now let's take a look at the trunk on switch 3. And you tell me, do you see any problems with the switch 3 side of the trunk? And everything looks fine here. It's 802.1q. And again, the VLAN being allowed is VLAN 10. So before we move on to control and data plane troubleshooting on switch 3, let's do the same thing that we did on switch 1 and just check to make sure that the SVI is programmed correctly and up and running fine. So let's take a look at the SVI on switch 3. And here we can see the SVI for VLAN 10, and here we see our problem. The SVI has been administratively shut down. So we went through this in a logical progression, and we were able to isolate the problem. And the easiest way to isolate a problem is to rule out devices in your network. And the only way you can really rule out a device in your network is to check control and data plane operations. We've done that on switch 1, and we were confident by the time we left switch 1 that everything was working fine there and that the problem had to have been on switch 3. And again, we did not move into control and data plane troubleshooting on switch 3 until we verified that the trunk that connected switch 1 and switch 3 were working fine and that the next hop was reachable. And we immediately found the problem once we checked that. So there's a logical progression in troubleshooting, but the main point of this exercise was that you don't just do a show IP route, that you actually, because if you just do show IP route, you're just checking the control plane. If you move on from a switch, you really have not verified that in fact that switch is not the source of a problem. What we did with our troubleshooting commands in this exercise is that we made sure that switch 1 was not the problem by using control plane and data plane troubleshooting. So here's what you've learned. We've done a basic VLAN routing review. We've talked about routing on a switch versus a router, the similarities and differences. You now understand control and data plane troubleshooting, and that helps you with VLAN routing troubleshooting. And then finally, we gave you a couple challenges to help solidify some of this information. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we will be covering BPDU. And in this video we're going over some basics of spanning tree. And if we're talking about the basics of spanning tree, you need to talk about bridge protocol data units and also port states. So that's the goal of this video. We'll talk about BPDUs, port states, and then finally we will discuss the importance, or just an understanding, what the bridge ID is and how it's important to spanning tree protocol. STP is defined in the IEEE 802.1d standard, and its primary purpose is to make sure that your network is loop-free. It operates by making the following assumptions: that all links are bidirectional, and that they can in fact send and receive BPDUs, and that the switch itself is able to regularly receive, process, and send BPDUs. Now, all switches that reside in the same STP domain regularly exchange these bridge protocol data units, these messages, with one another. And ultimately, the network uses the information from these data units to determine the network topology and the flows of traffic. The topology of an active switch network is determined by the following three variables.
the unique MAC address or the switch identifier associated with each switch, the path cost to the root bridge associated with each port on the switch, and the port identifier. All of these play a big role in the decision making of how traffic will flow on a network. Some basic facts. BPDUs are sent to the STP multicast destination address, as you see here. And by default, they are sent every 2 seconds. Now, there are 2 types of data units that we should know of: configuration BPDUs and TCNs, or topology change notification BPDUs. Now, switches determine the best configuration BPDU based on the following criteria, which is lowest root bridge ID, which is based on root bridge ID, root path cost to the root bridge, sender bridge ID, and sender port ID. Before we can continue, we should really understand how things work in spanning tree regarding just the ports themselves. So spanning tree ports. So in a typical environment, we're going to have one root switch, and we have 3 switches connected here, switch 1, 2, and 3. And switch 1 is the root. And this is going to help us understand how spanning tree designates ports. So in spanning tree, the root never has root ports, because root is always the forwarding port that is closest to the root bridge. So this root only has designated ports. Switch 2 and switch 3 both have root ports. That is the forwarding port that is closest to the root bridge in terms of path cost. And then switch 3 has a designated port. This is one forwarding port on each LAN segment. And then switch 2 is the alternate port. This is the best alternate path to the root bridge on that very same segment. Next to switch 3, we're going to connect switch 4. Switch 3 is going to have a designated port, but it's going to also here have a backup port. A backup port is a backup redundant path to a segment where another bridge port already connects. The backup port applies only when a single switch has 2 links to the same segment. Now we can better understand the following slide. At the completion of configuration BPDU exchange, the following results. A root switch is elected for the entire spanning tree domain, and a root port is elected on every non-root switch in the spanning tree domain. As you will remember, a root port is a forwarding port that is the closest to the root bridge in terms of path cost. A designated switch is elected for every LAN segment, and a designated port is elected on the designated switch for every segment. And if you will remember, a designated port is a forwarding port for every LAN segment, the chosen forwarding port. And then finally, based on all of this information and all of these calculations, loops are avoided in the network. Now, topology change BPDUs play a key role in handling changes in the active topology. They are proactively originated by any switch and sent upstream toward the root bridge, providing information that would be key to keeping the network loop-free. Next, let's talk about spanning tree port states. 802.1d has 5 different port states: disabled, blocking, listening, learning, and forwarding. Let's talk about each of these in depth. When a switch port is in blocking mode, the port is not transmitting or receiving data, and it's prevented from transmitting BPDUs. Packets arriving on the port are not learned by the bridge's filtering database. A block port, though, can receive BPDUs and is included in the spanning tree algorithm calculation. So ultimately, it could be used to transfer data, but it's not. It's blocking at this point. Next, let's talk about the port state of listening. A listening port is not transmitting or receiving data, and packets on the port are not learned by the bridge's filtering database. But it can transmit and receive BPDUs and is included in the spanning tree algorithm calculation. The listening state is a transitional state that will change to the learning state after a settable time of period, which we know as the forward delay timer. Next, let's talk about the learning state. In a learning state, the port is not transmitting or receiving data, but it can receive and transmit BPDUs. It is included in the spanning tree algorithm calculation, and the packets arriving on the port are in fact learned by the bridge's filtering database. This also is a transitional state that will automatically change to a forwarding state after a settable period of time, which is called the forward delay timer. And as appropriate, let's move on to the forwarding state. The forwarding state is the only state in which data is being transmitted and received by the port. It can receive and transmit BPDUs and is included in the spanning tree algorithm calculation. The packets arriving on the port are learned by the bridge's filtering database. Finally, let's talk about the disabled port state. A port is disabled or in a disabled state when the port is not transmitting or receiving data packets or BPDUs and is not considered in the spanning tree algorithm. So as you can see, once a port is enabled by a network administrator or through initialization, it goes through a process or these different port states. The port will move into a listening and learning and ultimately a forwarding state if the spanning tree algorithm has chosen it as a root port or a designated port. If spanning tree has not chosen the port as a root or designated port, it will put the port into a blocking state. You know that also as an alternate port or a backup port. Now, spanning tree uses the bridge ID to uniquely identify each switch, and it's actually used to assist in the election of a spanning tree root bridge, unless, of course, the root bridge has been manually configured. In the 802.1d standard, each VLAN requires a unique bridge ID. So let's take a look at some of these basics with regards to spanning tree. Here we are on a switch. And what we'll do is let's just do a basic show spanning tree. Here you can tell that this switch is in fact the root. There are many ways you can tell which is the root, but the most obvious way is that it says this bridge is the root. The second way you can tell that it's the root bridge is that you notice that the root ID MAC address and the bridge ID MAC address are both the same. Another way you can tell that it is in fact the root bridge is that none of the interfaces for VLAN 1 are set up as a root port. The role is all designated ports, which you will normally find on the root bridge. Now, you'll see here on VLAN 20 that VLAN 20 is not in fact root, and I knew that initially not by looking at the root ID or bridge ID, but actually at the interfaces. I can see on Fast Ethernet 07 that it is a root. Now you can see here the status of the interfaces are forward, blocking, forwarding, which obviously you know from what we've gone over already that root ports and designated ports are in forwarding state, alternate ports and backup ports are in a blocking state. Now, let's take a look at a transition of an interface as it goes through the process, through each of these port states. And what we're going to do is we're just going to check on VLAN 1. So let's take a look at Fast Ethernet 07 and watch it transition. Let's go ahead and shut it down. And now you can see Fast Ethernet 07 has gone down, and now you can see that Fast Ethernet is now you can see that Fast Ethernet 07 is no longer showing up. But watch, because we know that there are set timers with 802.1d, we're going to be able to see it transition as the port comes up and spanning tree calculates. We'll see it transition and going through the certain steps, ultimately getting to its role as a designated port on the root switch. So watch this. And what we'll do here, it's not up yet. There it is. It's listening. And we should be able to see it go through 3 stages here. Now it's learning. And now it's forwarding. So we saw it go from it went from a disabled state to a listening, learning, and forwarding state. So here's what you've learned. You've learned the basics of spanning tree protocol 802.1d. You've learned the importance of bridge protocol data units. You also better understand port states and the importance as well that bridge ID plays in the entire process of spanning tree protocol. All these things together build for you a really solid foundation as you move forward and learning about spanning tree and different variations of it. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're covering spanning tree port types, cost and priority, as well as timers. So we'll discuss root bridge election, cost and priority, root and designated ports, and also we'll talk about alternate and backup ports as well. So spanning tree root bridge election, following initialization, all switches initially assume that they are root, but the switch with the highest bridge priority is elected the spanning tree root bridge. Now, all things being equal, if nothing's been configured and all things are set to default, then the root bridge is chosen by the lowest order MAC address. During root election, no traffic is forwarded over any switch in the same spanning tree domain until things are stabilized and there's a loop-free topology. Spanning tree uses cost and priority values to determine the best path to the root bridge. In the 802.1d specification, it assigns a 16-bit default port cost values to each port. Now, note this before we dig into the actual port values. The port cost is globally significant and is included in all propagated BPDUs. By default, the lower number, the lower costs are more preferred. So you're going to see this in a second as we draw this out. But in the event that multiple ports have the same path cost, then spanning tree will consider the port priority. The default value is 128. But you should note that the port priority is locally significant and not included in spanning tree protocol BPDUs. So the spanning tree protocol default port cost, it depends on the interface speed. And you'll notice here from this chart that the higher the speed, the lower the cost. And this comes into play when spanning tree is actually trying to calculate the best path to root. So, for example, let's draw out a network with 5 switches. And we're going to bring each of these switches online and let spanning tree decide which is the best path and which ports should be root, which ports should be designated ports. So they are all interconnected. And let's pretend we are powering them all on. Now, let's say the switches aren't all of the same speed. So, for example, we have a 10 megabit switch, a 100 megabit switch, and we'll just say all the interfaces on the switch are that speed. A 1 gigabit switch, a 100 megabit switch here, and a 1 gigabit switch. So as you remember from the chart, these numbers should start to look familiar. The cost of 2 is assigned to a 10 gigabit interface, cost of 4 a 1 gigabit interface, cost of 19 a 100 megabit interface, and a cost of 100 to a 10 megabit interface. And Spanning Tree will calculate, as you can see it's doing right here, Spanning Tree is calculating best path to the root. And let's say we've assigned the 1 gigabit switch as our root. We've manually set it. Spanning Tree would then calculate, and as you can see here, from the 10 megabit switch through the 100 meg over to the 1 gig, it's 100, and the total cost is 123. And then the other path, the total cost is 119. That's the lower cost. That would be the root port, because that would be the preferred path. So as you know, we've already talked about some of these ports, but Spanning Tree elects 2 types of ports that are used to forward BPDUs, and that's the root port. Now note, the root switch never has any root ports because this is the port that provides the best path to the root bridge. So every other switch is going to have 1 root port. That's the best path to the root bridge. The root bridge will not have a root port for obvious reasons. The root path cost is calculated based on the cumulative cost to the root. The designated port actually points away from the Spanning Tree root, and it sits in a blocking state. All ports on the root are designated ports because the root path cost will always be 0. The designated port is the best port on a segment. So for example, on a segment you will have, on a segment where there is no root switch, you will have 1 designated port, and all the other ports will be either alternate or backup ports. We talked quite a bit about BPDUs in video lesson 3, module 1, but let's build upon that further. BPDUs include several timers that play an integral role in the operation of the protocol, and the modification of these timers should always be made at the root bridge. There are 3 configurable Spanning Tree timer values, which is hello, forward delay, and max age. The hello time is the time between each BPDU that is sent, and as you know, it is 2 seconds by default. Forward delay is the time that is spent in the listening and learning state, and you definitely learn about those states, or if you haven't learned it already, go back to lesson 3, module 1 video, but you learned about those states in that video. And the forward delay time is 15 seconds by default. And then max age is set in the BPDU by the root bridge, which is 20 seconds by default. And if you'll remember, the max age timer controls the maximum length of time that passes before a bridge port saves its configuration BPDU information. Although it's 20 seconds by default, you can of course tune this time to be between 6 and 40 seconds. So let's jump into the lab and show spanning tree is obviously going to be one of the most popular commands we're going to run if we want to verify. You can see there's a lot of options here on how to view your spanning tree environment. Let's take a look at spanning tree for VLAN 1. And as you can see here, this bridge is the root. Now you know from what you've learned so far how do you know this is the root. There's many indicators. It says it's the root and there are no root ports. They're all designated ports. Now as we jump on a different switch, as expected, there is one root port on this switch, and there are 2 alternate ports and 2 designated. So let's take a look at who the root is for each of the VLANs. And you can see that by simply doing show spanning tree root. You can see the root ID. Well, I tell you what, sometimes you simply don't want to wait for spanning tree to tell you who root is going to be. You actually want to set who root is going to be. we want to make this root. And you do this by typing spanning tree VLAN 1 root primary. And as you can see, we've now taken over, DLS1 has now taken over as the root. Usually you like to set in your network who the root is. And you can see here, show spanning tree root. It shows that we are in fact the root. And you can see the default hello, max age, and forward delay timers. Now let's go ahead and reconfigure some of these timers. So we type in spanning tree VLAN 1. Let's change the hello time. We want to send out BPDUs more frequently. Let's change it from the default 2, and we're going to change it to, from the default 2. And then let's change another timer. We're going to change the max, and then we're going to change max age to 40. Finally, we're going to adapt the forward time to 30 seconds. And now we can show the results of what we've done. So here's what you've learned. You've learned about root bridge election. You've learned about port cost and priority, root and designated ports, and finally spanning tree timers and how to adapt them. Good luck in your continued studies. Hi, this is David Voss, CCIE 11372, and in this video we're going to be covering Rapid Spanning Tree Protocol. We'll do an overview, review BPDUs, look at port states, port roles, and port types, and finally we'll talk about some of the enhancements of Rapid Spanning Tree Protocol over its predecessors. Now, the 802.1d standard was designed at a time when network recovery was not expected to be immediate, and times certainly have changed, and thus the 802.1w standard Rapid Spanning Tree Protocol significantly reduces the time taken for Spanning Tree Protocol to converge when a link failure occurs. Now, network failure to an alternate path can occur in sub-second time frame, so it performs better than traditional Spanning Tree Protocol with no additional configuration. And note, the 802.1w BPDU is similar and backward compatible with the 802.1d. BPDUs are sent every hello time interval, which is 2 seconds by default, and it's the non-root bridges which generate these BPDUs. Topology change notification BPDUs, or TCNs, originated by a switch are relayed up to the root bridge, which then propagates them to all of the other downstream switches. These are some of the most important concepts that you'll need to grasp as you prepare for your CCNP switch exam. Now please note that 802.1d may have had 5 different port states, but 802.1w has 3: discarding, learning, and forwarding. And you can count on the fact that you'll be asked about that in your exam. In 802.1w, there are port roles. There's the root port, defined as the port that receives the best BPDU from the root bridge. It provides the shortest path to the root bridge. And then there's the designated port, which is an active forwarding port that actually points away from the root bridge and toward the edge of the network. It sends the best BPDU on a segment. There's the alternate port, which is the non-forwarding blocking port that backs up a root port. And then there's the backup port, which receives better BPDUs from the same bridge rather than from a different bridge. It's a non-forwarding blocking port, and it backs up a designated port on the same segment. It's much easier to draw these out so we can get a better understanding of what these ports are actually doing and what they actually look like on the network. So here we have our network, and we have 3 switches all interconnected, and our first switch is our root. We'll call it switch 1, then switch 2, and switch 3. So switch 1 is the root, and again they're all interconnected. So the designated port on the root is going to be both links. There's no root port on a root because remember, root ports, as you see here on switch 2, are the ports that have the best path back to the root. And switch 3 has a root port and then a designated port. Now remember, a port is designated if it can send the best BPDU on the segment to which it is connected. On a given segment, there can only be one path toward the root bridge, and if there are 2, there's a bridging loop in the network. Therefore, there is one designated port between switch 2 and switch 3. Now you see the alternate port. Alternate port and backup ports have something in common. They are both blocked ports. The alternate port is simply the alternate path for that segment. It's not the designated port for the segment, so it's moved into a blocking or alternate port status. An alternate port receives more useful BPDUs from another bridge, so therefore it is port blocked. Now a backup port receives more useful BPDUs from the same bridge it is on, and it is port blocked. What makes 802.1w perform so well is that the rapid transition feature allows RSTP to place ports in a forwarding state without having to rely on any timer configuration. Now, in order to achieve fast convergence on a port, the protocol relies on 2 new variables. These are edge ports, which are generally connected to endpoint devices, workstations. This immediately goes into a forwarding state by using the port fast feature. Next, there's link type. RSTP supports 2 different link types. Point-to-point, and that's a port that operates in full duplex mode, and shared on a port that operates in half duplex mode. There's some other enhancements you need to be aware of with 802.1w. First, uplink fast. Uplink fast provides fast convergence using uplink groups in the network access layer. So an uplink group is actually, it consists of the root port, which as you know is forwarding, and then a set of block ports. And it provides an alternate path in case the currently forwarding link fails, and it does so immediately. Backbone fast provides faster convergence in the network backbone after a spanning tree topology change occurs. So backbone fast detects indirect link failures, and when the switch receives inferior BPDUs from its designated bridge, and when it does that, it indicates that the designated bridge has lost its connection to the root bridge, and it immediately chooses another path back to root. Let's go ahead and jump into the lab and enable rapid spanning tree protocol, and also program uplink fast and backbone fast. So we log into a switch, and we type spanning tree mode, and then we choose rapid PVST. And quite simply, that's all you need to enable it. So that's enabled on the switch now. And we are going to go ahead and show. Now you can see that rapid spanning tree protocol is enabled for all of our VLANs. You also see the hello time, max age, and forward delay timers are set to their defaults of 2, 20, and 15. We are going to let's make this switch the root, and we do so by spanning tree VLAN 1 root primary, and we're going to make it the root for VLAN 1 and 10. And by doing so, we allow ourselves to be root for certain VLANs, but not all VLANs. And as you can see here, the bridge is the root. There's some other designations that you can tell that this is root because we're not going to have any root ports. And you will see here we have no root ports as well in VLAN 10. Also, the MAC address for root ID and bridge ID match, so that's another way you can tell that your bridge is in fact root. Let's go ahead and enable uplink fast. And as you can see, it's quite simple. We just type spanning tree uplink fast, and that's enabled on the switch. It's as simple as doing that for backbone fast as well. And to monitor uplink fast and backbone fast, you simply type in show spanning tree uplink fast. And then you can also do show spanning tree backbone fast. So here's what you've learned. You've received an overview of RSTP. You've learned about RSTP BPDUs, port states, port roles, port types, and the enhancements. We also jumped into the lab and programmed RSTP. We enabled it and then enabled uplink fast and backbone fast. And we also took a look at ways you can monitor it as well. This is a great foundation for you for RSTP, and good luck in your future studies. Thank you. Hi, this is David Voss, CCIE 11372, and in this video we're covering multiple spanning tree protocol. So in this video we'll dig down deep into MSTP. We will look into the BPDU format, look at MST regions and region components, internal spanning tree, and multiple instance spanning tree. MSTP is an IEEE standard. It combines the best aspects of PVST Plus and 802.1q. Several VLANs can be mapped to a reduced number of spanning tree instances, since most networks do not need to know more than a few logical topologies. That being said, it's more complex than typical spanning tree protocol, and interaction with legacy bridges will be a challenge. MST uses RSTP for rapid convergence. Therefore, each switch must be capable of processing RSTP BPDUs in order to support MST. Here you can take a look at an MST BPDU format in detail, and you can see the obvious indicators that this surely is an MST BPDU. You need to understand MST regions if you're going to understand MST at all. An MST region defines a boundary within which a single instance of STP operates. MST employs the use of regions because not all switches in the network might run or support MST. Therefore, different kinds of spanning tree protocols divide the network into STP regions. A collection of interconnected switches that have the same MST configuration comprises an MST region. Specifically, the MST region name, configuration revision number, and VLAN to instance mapping. An MST region consists of two separate components. An edge port, which is simply a port that connects to a non-bridging device such as a network host, and then a boundary port, which connects an MST region to a single spanning tree protocol region running RSTP 802.D, 802.1D, or any other MST region with a different MST configuration. So let's talk about MST region components, and the best way to do that is actually to look at this diagram. Here we have MST region 1, 3 switches interconnected. The hosts are connected to edge ports. So remember, there are two types of ports, edge or boundary. The hosts are connecting into edge ports. And the MST region then communicates with other domains or regions using boundary ports. So switch 3 and switch 4 are communicating via boundary ports. Even though they're both running MST, they are running two separate regions and therefore will not share that VLAN information. And then there's 802.1W and 802.1D domains as well. Multiple spanning tree establishes and maintains the following two types of STP instances: internal spanning tree and multiple instance spanning tree protocol. Now, regarding internal spanning tree, the MST region sees the outside world via its internal spanning tree interaction only. The IST presents the entire MST region as a single virtual bridge to the outside world. BPDUs are exchanged at the region boundary only over the native VLAN of trunks, as if a single CST were in operation. IST is the only instance that sends and receives BPDUs. The IST connects all the MST switches within a region. When the IST converges, the root of the IST becomes the IST master. And the IST master election process is similar to that of traditional spanning tree protocol root bridge election. Initially, all switches in a region claim to be IST master, but switches within the region then exchange BPDUs and finally elect an IST master. Now, multiple instance spanning tree protocol represents spanning tree protocol instances that exist only within the region itself. MISTP does not interact directly with the CST outside of the region. Instead, MISTP conveys STP information for each instance within the region. Cisco Catalyst switches support up to 16 MISTPs on a single switch. So let's jump into a lab and configure MST. First thing we're going to do, we're going to set the spanning tree mode to MST, and then we go into MST configuration, and we go into basically revision 1 or instance 1, and we name this region A. So this is our first region. And in this region, we are going to allow VLAN 1 and 10. And here, as you can see, you can set priority if you want the switch to become root or non-root as well. This is another popular command for dictating spanning tree and who becomes root in the region. Now, this is the advantage of MST. We can create a second instance supporting VLAN 20 and 30, and we can set a different priority, even though it's on the same switch, a different priority on this switch for whether it should be root or non-root. So the point being, you can have your switch take over root for certain regions, but not all regions when you roll out MST. Now, if you want to show your current MST status, just type show spanning tree MST, and we'll do 1 and 2. Those are our two regions. And you can see here the bridge ID and priority. you can see the status of each of the interfaces and which VLANs are allowed. So here's what you learned. You got a good solid introduction to MSTP. You saw the BPDU format. You learned about the regions and the components within those regions, the importance of internal spanning tree, and then also learned about multiple instance spanning tree. This provides a really solid foundation for you. You should be able to answer most questions regarding MST at this point. Thank you and good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're going over EIGRP concepts. So we're approaching EIGRP from a 20,000 foot view, a high level view, so you can understand the basics of EIGRP and the concepts of it, so when we get into the labs in future videos, you know exactly what we're talking about. So we're going to do a high level EIGRP overview in this video. And then we're going to talk about the EIGRP components. You're going to see this constant theme of these four components. So first, there are EIGRP messages that are unique to EIGRP. There's a unique EIGRP algorithm. There are tables that are, again, unique to EIGRP that you need to know about. And then finally, you need to know that EIGRP supports independent modules. So there's multiple support for multiple different network layer protocols. Now, the way we're going to approach this is, again, it's a high-level overview of concepts that are unique to EIGRP. So we all know that EIGRP can support VLSM, for example, but many routing protocols can. So we're not going to dig into VLSM and EIGRP. We're going to talk about things that are unique to EIGRP. Now, for to understand EIGRP, we first need to understand IGRP. IGRP came out in 1986. It is an interior gateway protocol that was once very popular. Distance vector routing protocol. And it used four key attributes to develop this distance information on how to choose the best path. So it looked at the link, and then it said how much available bandwidth is there, how much delay, how much load, and how much link reliability is there on this link path or on the multiple links to my path. Well, EIGRP is still an interior gateway protocol. And it is still a distance vector protocol, although many times in the past it had been referred to as hybrid, but those days are pretty much gone. Distance vector is what it's classified as, but it has improved convergence in operations. So it uses the dual diffusing update algorithm, and I'll show you about that in a few minutes. And then again, it has multiple unique tables to EIGRP, which assists in the operations and enhances the operations. And then again, it supports multiple network layer protocols. So how does EIGRP actually work? Well, I tell you what, let's go ahead and open up the hood and take a look underneath. EIGRP has four basic components, and these should already start looking familiar to you. It has messages. So messages flow to and from neighbors, EIGRP neighbors. There's 5 different types. We'll dig into that in a little bit. EIGRP has the dual algorithm. The dual algorithm takes the information from those messages and then processes best path and possible best path. Then all the information from the messages and the algorithms get put into tables. So these EIGRP tables hold the data from the algorithm and the messages. And then finally, the modules. These protocol-dependent modules support a variety of network layer protocols. So we're not limited. EIGRP is not limited to just IP. So with regards to messages, there are different types of packet formats. There's 5 different types of packet formats. First, there's the hello message. A hello message is basically a query out to anybody who'll listen, asking if anybody's out there. So a router running EIGRP sends hello packets by default, and it will send those packets out and hope for a return reply. And when it gets a return reply, it'll get that update. And that update contains all of the messages or all of the routes that want to be shared via EIGRP. Update messages are messages with a lot of routing information in them. And then there's the acknowledgement message, which surely you know about from other protocols, but it's simply acknowledging that, yes, I've received your message. And that's key to the reliable nature of EIGRP, which we'll talk about in a minute. There's a query message. So if EIGRP loses a route and does not know how to get there anymore, it will query its neighbors saying, do you have any information about this route? Because I'd like to get that information. And then if a router does have information on that route or on that path, it will reply back saying, yes, I do have information, and here it is. So these 5 messages can be broken out into 2 categories, some that are reliable and some that are not reliable. The reliable messages use Reliable Transport Protocol, and this is unique to EIGRP, but RTP basically makes sure that packets get to where they're supposed to go in order. So an unreliable packet is a hello message. That message is not reliable, but the update message from an EIGRP router does use RTP. So it is sequenced and there are acknowledgements. So there is an acknowledgement to that message, but the acknowledgement itself is not reliable. Then there's the query message. Remember, the query is to ask, do you have information about this route? And that uses RTP, and the response to that query, the reply, also uses RTP. So 3 different types of messages use RTP: the update, the query, and the reply. And I think that's critical to know for your exam. Now let's talk about the EIGRP algorithm, which is dual. Now, to understand dual, you need to understand what successor and feasible successor routes are. When you think of successor, just think of success. That's the best path. So if EIGRP loses connectivity to the best path, it will then run the dual algorithm and ask, is there a feasible successor? Is there a second best path? And if the dual algorithm states, yes, there is a feasible successor, a second best path, it will then promote that second best path to the best path. So that becomes the successor. Once it's the successor, it is then installed into the routing table. So for example, it would be installed into the IP routing table. And then the router would begin to use that new path. So this chart gives you an overview a high-level overview of how the dual algorithm runs. But it's important to know these concepts of successor and feasible successor as you move forward with EIGRP and how dual uses that information. Now, EIGRP uses specific tables to help make it run, and one of the tables that EIGRP uses is called a neighbor table. Now, a neighbor table is exactly what you think it is. It's a table that is comprised of a listing of all the EIGRP neighbors. So, for example, we have a hub and spoke design here. We have router A, router B, and router C. And router A and router B are both running EIGRP. Router A sends out a hello packet, and router B responds back as well, and they've established a neighbor relationship, and router A sends out a hello packet. Router C does the same, and they've established their EIGRP neighbor relationship. So once that happens, router A begins to build out its neighbor table by identifying each neighbor by IP address. So, for example, router B is 172.16.1.1, and he gets placed into the neighbor table. And then router C is 192.168.10.2. and he is placed in the router table as well. So router A now has 2 neighbors, and they are both listed in its neighbor table. But there's also other information in the neighbor table as well. And the router A also wants to know what interface are these routers off of. So router B is off of serial 1, router C is off of serial 2. So should I need to forward them traffic, or I know exactly which interface they will be exiting. And then finally, there's other information that is entered into the neighbor table. There's quite a bit actually, but for the sake of this high-level overview, let's just talk about hold time, because this is a key concept. When you program hold time on a router, it's not local. You're not changing the hold time locally. That information is actually forwarded over to your neighbor routers. So here we have router C, who's changed his hold time to 10 seconds. He forwards that over to router A. And here we have router B, and let's say he's going to change his hold time. This information that they're changing from the default, it gets inserted into the neighbor table on router A. And remember, hold time is basically telling the router, if you don't hear from me in this amount of time, consider me down and flush the routes that you receive from me. So it's important to remember, hold time is configured on router C and router B, but the actual numeric change occurs on router A in the neighbor table. Now there's definitely other attributes that are in the neighbor table, and we will definitely go over those in future videos, but on a high-level overview of EIGRP, you need to know about the IP, the interface, and the hold time counter. And just remember, hold time defaults is 180 seconds for low bandwidth links and 15 seconds for T1 or higher. So that'll come up again and again, and you'll probably be asked about that as well. But there are other EIGRP tables that you should also be aware of. And a key table to know about is the topology table. Topology table contains all destinations advertised by neighboring routers. This includes, remember, the successor and feasible successor routes, the best path to a destination and the next best path, respectively. So topology table is key for EIGRP to run. Now remember, within topology table, you can see the route tags. So in EIGRP, you can actually perform route tagging. And all you really need to know for now is that you can identify routes by their origination, which allows for custom routing. So you can tag those routes with a manual entry. So that's all you really need to know for now. But getting back to EIGRP tables, now here's an example. We have, again, a hub and spoke design, router A, router B, and router C. Now router A is going to build out, as soon as it enables EIGRP, it's going to build out these EIGRP tables. And one of the tables, again, is going to be this topology table. The topology table is going to contain critical information for EIGRP to run and make the choices upon what the best path is going to be. So in the topology table, it's going to insert routes that it learns from router B and router C. And then it's going to ask, now that I know about this route, which neighbor did I learn it from? And then finally, it's going to say, all right, I know the route, I know the neighbor I learned from, what metric should I assign to it? Which way should I send traffic or forward traffic? So in this example, the route itself, let's say we'll do a 10.1.1.0/24. And let's say we learn this route from both router B and from router C. So this topology table is filled out with 2 entries for the same route. Again, this is not the routing table yet. This is the topology table. And it has a metric, so let's keep it simple. So the metric to router B is 10, and the metric to router C is 20. So for this simple example, let's just say that the router now realizes that the successor route, the best route, is going to be the path through router B. Now, once the dual algorithm has run and it realizes this, it then takes that route or that path and it places the successor route into the routing table, in this case the IP routing table. So now we know the successor is to router B and the feasible successor path is to router C. So as we can see, it's going to choose the path out to router B. Now, what happens if this route information is lost and router A no longer learns about this route from router B or from router C, and it gets flushed? Well, router A, what he's going to do is he's going to send a query to router B and to router C asking, do you know about this route? Because I've lost it and I'm hoping you have information on it. And the neighbors will respond back, but specifically, let's say in this case that router C is the only one that knows about it. Router C will respond, yes, I'm aware of it, and it will send the information over, and router A will say thank you very much, and router A will then insert it into the topology table. It will become the successor, and once it's the successor, it will be placed into the routing table, and then router A will then begin using the path through router C to reach that subnet. And last but certainly not least, we have protocol-dependent modules. So EIGRP and the dual algorithm function in a way that protocols can run and use EIGRP independently of one another. So IP builds out its own neighbor and topology tables. IPX and AppleTalk, they all build out their own neighbor and topology tables, and dual can work with any and all of them. So you've learned a lot today, as you can see. And again, although it was high level, these concepts are really key in moving forward with EIGRP as we begin to really get hands-on. So you've learned about the messages and the algorithm and the tables and these modules. And I hope you've learned a lot. I know that you're going to need the information not only for the labs that we do, but especially for the tests that you take. So thank you very much, and good luck in your studies. Hi, this is David Voss, CCIE 11372, and today we'll be going over OSPF Concepts. So approaching OSPF from a high level to learn some concepts that you'll need to know as you approach the lab or your studies. It's just it's a generic overview that's going to really help you move forward. So OSPF has these administrative areas. We'll talk about that, these different types of areas, and these virtual links that connect some of these areas, and what exactly a virtual link is. We're going to talk about router types. There's different types of routers within OSPF doing different functions. And then we'll talk about designated routers and backup designated routers, what that terminology is all about. The neighbor exchange state, so the different states that the routers are in the OSPF process of communication. And speaking of that, obviously messages, link state advertisements, that's how OSPF routers communicate. We'll talk about that. And then finally, using all that information, the OSPF router chooses the best path. And we'll talk about how that happens. So let's start with administrative areas. So let's start from the basics here. Autonomous system is a network under a common network administration. Now, I'm sure you know that. But in OSPF, an autonomous system is broken out into areas. So areas are a group of routers that share a same area ID. And these different areas, these different groupings have different functions, and they know different types of information. So you have backbone area, standard area, etc. And each of these areas perform different functions. So let's talk in detail about what some of these areas know and maybe what some of these areas do not know, but also how OSPF is designed around these concepts of areas. So remember, we're talking at a higher level here, but as a good rule of thumb, your backbone area in OSPF, if anybody ever refers to area 0, you know they're talking about the backbone area in OSPF. And this is probably the most well-known area because it is required. And all other areas must connect to the backbone area. So if for area to area communication, let's say you have an area 1 communicating to an area 3, Both of those areas must connect to the backbone. So let's start here with a standard area. Now, a standard area, what does that really mean? Well, standard areas can be thought of as equal opportunity employers, I guess you could say, because they know about every route in the autonomous system, in the OSPF network. And they share their routes, but they also learn all their routes from other areas through the backbone. And this is just fine. All of this route sharing is just fine if routers are high powered enough to store every route, but also to run these complex SPF calculations. But just know the standard areas contain LSAs of type 1, 2, 3, 4, and 5. Now next, if you think of a stub area, which we'll talk about next, if you think of a network, you have leaf nodes on networks. Well, that's what kind of a stub area is. It's handy if devices are lower powered, routers are lower powered, or simply do not need to know about every route. A stub area is similar to a standard area, but routers in it are not aware of externally sourced routes directly. And in terms of LSAs, that means that type 5 LSAs are not permitted in a stub area. Stub areas use a default route to exit. For traffic to exit a stub area, it uses a default route. Now, next would be a totally stubby area. And let's take this stub area concept one step further. In a total stubby area, in addition to the lack of type 4 and 5 LSAs, type 3 LSAs, which carry information about internal routes, are also prohibited. The concept of an injected default route still applies here, just like a stub area. So all traffic leaving the area does so using the default route. And then finally, let's go over this concept of not so stubby areas. So, this is an interesting, I guess you could say, concoction, because not so stubby areas can connect to non-OSPF networks that are not a part of this autonomous system, and they can receive routes from those non-OSPF networks or networks that are not participating in the autonomous system. And it will receive those routes through redistribution, and then it can turn those type 7 LSAs and kind of, basically it's going to mask them and make them appear as type 5 LSAs, and then begin sharing them onto the network. So there's your ideas of networks and areas, but all areas in an OSPF autonomous system must be, as you know, physically connected to the backbone area. Well, what if you can't do that? What if you can't connect an area to area 0? So let's draw out this concept of a virtual link. Let's imagine we have a company on the East Coast, and in this company we've deployed OSPF already. So we have our backbone area 0. And then we have other areas that have to obviously connect into this backbone area. So let's say we have an area 1 in the Boston area, and then an area 2, let's say in Florida. But let's focus in on area 1. So in the Boston area, we have area 1 in Boston, and we acquire another company in that area. And it's easy enough for us to connect this new company into our Boston resources. So we're going to connect them into our Boston router. Very simply. The problem is that even though this company that we've acquired, maybe they're already running OSPF, and we convert them to OSPF Area 3 to work within our autonomous system, we still need to meet the requirement of OSPF where an area must connect into Area 0. So OSPF allows for what is called, as you know, the virtual link. We will create this virtual link between Area 3 and Area 0. It's passing through Area 1, and this allows us to meet that design requirement of OSPF. So route to Area 3 and Area 0 see this as a direct connection, and things will work just fine thanks to the virtual link. So there are many different OSPF router types that you need to be aware of. There's the area border router, which connects one or more OSPF areas to the backbone area. There's the ASBR, or Autonomous System Boundary Router, which will be located between an OSPF autonomous system and a non-OSPF network. And then you have your backbone router, which is pretty straightforward, a router with at least one interface connected to area 0. And then another easy concept, an internal router, a router with all interfaces in one area. Let's draw this out real quick, let's just to drive it home. So let's draw out our area 0. And in area 0, you know already, is the backbone. So a router within area 0 is a backbone router. And then we connect to another area, let's say area 1. This is an area border router. Pretty straightforward concept. There's your ABR. And let's say we have another area we're connecting to. There's another ABR. But we are also connecting an ASBR here because we have a non-OSPF network that we're going to be injecting routes from into our OSPF process. So we are injecting routes in through an ASBR, converting type 7 LSAs to type 5, and those are being forwarded on to the network. And then you have, last but not least, internal routers, which have all interfaces in the same area. Pretty straightforward. So in order for two OSPF routers to communicate, they need to go through this process of exchange states. So you need to understand a basic concept of what these are. Here's the following states. There's the init state, where a hello packet has been sent by a router, it's waiting for a reply. Then the establishment state, where there's the discovery of that hello, and then the election of a DR in multi-access networks. The XStart stage, where a master-slave relationship is started between two routers. The router with the higher router ID becomes the master and starts the exchange, and as such is the only router that can increment the sequence number. Then there's the exchange state, where the slave acknowledges the master's packets, and this information in this state is only LSA headers, and it describes the contents of the entire link state database. Then there's loading, where there's a request for more information. In this state, the actual exchange of link state information occurs. And then there's full synchronization, and in this state, routers are fully adjacent with one another. All the router and network LSAs are exchanged, and the router's databases are fully synchronized. Now, a designated router in OSPF is a key concept that you need to know, because on multi-access networks, a designated router will establish adjacencies with all other routers on the multi-access network, learn all of their routes, and then share all of their routes with all the other routers. And then the BDR, the backup designated router, will fill in should the DR fail. And you can set the DR and the BDR manually, and actually you should do it this way. You should set it using the priority command in OSPF. So understanding OSPF priority is key because you can manually set who the DR is and who the BDR is. Now, it's easy to talk about this and look at a PowerPoint, and you may not fully appreciate how important this concept really is. So let's actually draw it out. So on a typical multi-access network, let's say we have 5 routers and you want to establish adjacencies in OSPF to share routes between them. If they did it that way, where they're all neighboring with one another and communicating with one another, you're going to see that all of these adjacencies are going to add up pretty quickly. And that's going to tax the resources on the routers themselves, but it's really unnecessary. We can share this information in a much more efficient manner. So what we're going to do is we elect a DR in OSPF. Again, it has this built in within the OSPF design itself, where on multi-access networks you can elect a DR, and then the DR establishes an adjacency with all the other routers on the multi-access network. It learns all of their routes and then shares all of their routes. So now we just have 4 adjacencies required. Now, if the DR fails and those adjacencies fail, the BDR would take over. Now, regarding link state advertisements, what you really need to know, at least just for now in OSPF, is that a link state advertisement is a packet that contains all relevant information regarding a router's links and the state of those links. Now there are many different types, and I've listed the key types for you here. And we're going to dig into detail on these different types as we get into the labs. But just for now, know that these are informational packets that have information on a router's links and the state of those links. So now that OSPF has gathered all this information, it needs to know what to do with it. It needs to choose the best path. So it puts all the information in a topology table. And then OSPF, the metric for OSPF is cost. So cost is 10 to the power of 8 divided by bandwidth, and lower costs are preferred. So the best way to understand cost is actually for us just to draw this out to see how it works. So let's draw out a 6 router network. And let's say we have router 1, which ultimately wants to communicate with a network off of router 6. And it will have 2 choices, 2 paths it can possibly take. It can go via router 2 or via router 4 to this network. We'll say 192.168.10 network/24. Which is hanging off router 6. Now, router 1 then calculates using OSPF the cost for each and every link in this path. And it's going to do the same for the path from router 2 and 3 to 6. And then what OSPF is going to do is add up the entire cost to get to router 6. So from going via router 4, that path has a total cost of 20. And going via router 2, that path has a total cost of 25. And we know that OSPF uses the lower cost to make its decision on which path to take. So the total cost of 20 wins out, and we will choose router 4. Now that being said, let's say a new network is introduced that has higher bandwidth links. And even though we have more routers or more hops through this network, let's say there are 4 hops. If the cost is low, and for this case we'll say 5, 5, 1, 1, and 1. If the total cost here is just 13, even though there's more hops, OSPF is going to choose this path because it's more efficient. So that's cost basically explained. That's cost in a nutshell. But we'll get into details in the additional videos that you watch. So here's what you've learned. You've learned a lot, and you need to know all these concepts as you move forward. And I look forward to working with you on future videos as we really dig into the nuts and bolts of OSPF. Thank you. Hi, this is David Voss, CCIE 11372, and in this video we're going to be going over BGP concepts. So here's what you're going to learn. First, we're going to do a BGP quick overview, learn some of the basics of BGP. Then we're going to talk about BGP path attributes, which are key in decision making in BGP. Specifically, the AS path attribute. We'll focus in on that. Then we'll talk about eBGP versus iBGP, and private versus public autonomous system numbers. And then we'll also discuss BGP updates, how routers share information, what information they share, and how they advertise those routes to one another. So let's go ahead and start with BGP basics. BGP is an exterior gateway protocol that uses autonomous system numbers. Uses TCP 179 to communicate between neighbors, And it really is a protocol that requires manual configuration for almost everything. It doesn't really do anything unless you tell it to do it, which I really like about the protocol. Now, it uses path attributes, which are key in decision making on choosing best route. So path attributes define information about a path, but also this information can be used to help decide upon the best path. And we will draw that out in a minute here so you can understand that better. Now, regarding BGP path attributes, there are some that you absolutely have to know and memorize for your CCNP route exam. The first is weight. Weight influences a best route for the local router, and obviously it's manually configured. Local preference influences the best route for all routers in an autonomous system, so this is a shared attribute. AS path lists the number of autonomous system numbers in the path, and this can be manipulated. Origin is a value implying if the route is from an IGP or an EGP. And then finally, the MED, which can influence the best route for routers in another AS. So you can influence traffic flows into your AS by sending out the MED to other routers. So here you can see we have two routers that are in autonomous system 700. And then upstream, we have another router in autonomous system 140 and autonomous system 87. So here you see there are 4 hops. But as far as BGP is concerned, it's just counting ASs. So it counts 1, 2, 3 ASs. The AS path is 700, 140, and 87. Why is this important to know? Because here's another flow that has 2 routers in AS700 and then 1 router in AS87. Now, according to this path, there's just 2 ASs. That would be the preferred path. It's critical to understand that BGP is concerned about AS path and not so much about hop count. AS path is a key attribute to understand. Now, internal versus external BGP. iBGP is something you would run basically interior to your company. It's BGP connectivity within the same autonomous system. In this, routers do not update AS path. Normally they should never have to because you're running the same autonomous system. And in iBGP, things should always be meshed. Routers should always be fully meshed. And there are ways you can get around this, and we'll talk about that in a little bit. Now, eBGP is external connectivity to other ASs. And routers do update the AS path in those cases. So let's say we have an autonomous system 200, and in our company we're running iBGP full mesh between all routers. And let's say we have connectivity to 2 upstream providers. One is Autonomous System 301 and the other provider is Autonomous System 450. Now, between ourselves and our providers, we are running eBGP because it's 2 different ASs. And internally, we are running iBGP because we are communicating between the same AS. Now, configuration between iBGP and eBGP is quite similar. The main difference is you're choosing to communicate with the same AS or a different AS. Now, let's say we want to communicate to a web server over the internet, and we have a certain amount of hops. Now, let's say one of those paths through AS450 takes us through quite a few more hops, but it takes us through fewer ASs. So let's just say, for example, we go through AS900 and then AS100. So that's 450, 900, and 100. Those are the 3 ASs we traverse in order to reach that route. Now let's say on this flow through Autonomous System 301, we go through fewer hops but more ASs. Now, even though there's fewer hops, because there are more ASs, we're not going to prefer this route. There are 5 ASs in this path. That is not going to be preferred to the other path, which has only 3 ASs. So we're going to choose that path. We'll choose the 3 AS path. Now let's say we're running a web server inside of our company, and we're running iBGP between these 3 routers, and we're connecting to 2 upstream providers using eBGP. And let's say we have users on the internet who are trying to get to this web server. We can manipulate the AS path attribute in BGP to make them prefer one path over the other. And the way we do that, and let's say our autonomous system is 50, we can manipulate the AS path attribute by adding to the AS path on one of our links. So, for example, the users know that they can reach the web server via one AS. Well, we're going to increase that on the top router, and we're going to manipulate it manually and add our AS over and over again to the AS path attribute. And the users, as far as BGP is concerned, that now is a longer path, and therefore the users will prefer the bottom path because it's only one hop, one AS hop. Now, if that router were to fail, users would then prefer the other path. So you see, you can manipulate traffic flows that way. Now, you need to understand the concept of public and private ASNs, and this shouldn't be foreign to you because you understand public and private IP addressing. So autonomous system numbers are chosen from this pool, and you can use them for private use or public use as need be, but you should be aware of that chart. Now, regarding BGP updates that we receive from neighbors, you can receive from your provider a default route only, which many people do. Or you can receive a full BGP routing table. That is literally every route that's available on the internet. Or you can receive just partial updates, and that is maybe the provider knows about certain routes via a better path than most other providers. You can just receive a partial update from your provider. So you should know that you can receive those 3 different types of updates. That should be known for your CCNP route exam. Now, regarding advertising routes, advertising BGP routes can be done 4 ways, either through the manual network command, redistribution of BGP into IGP, or propagation of existing BGP routes, or again, manually using the aggregate address command. Maybe the best way to explain these is to simply draw it out. Now imagine we have a router with an iBGP connection and an eBGP connection to an upstream provider. So there's our eBGP connection, here's our iBGP connection, and we're autonomous system, let's say 400. So on a router, we can advertise in 4 different ways. We can manually specify the network we want to advertise by literally typing it in, network 10.10.10.0 or network 198.110, and we can forward that via iBGP and or eBGP. The other way is we can learn routes via BGP and redistribute that route into, let's say, an interior routing protocol. Let's say if we're running OSPF, we can take the routes we learn from our eBGP neighbor and redistribute them. The other way is to simply pass the routes we're learning from our eBGP neighbor via BGP internally to our iBGP neighbor. So that's just forwarding the information on. And finally, we can again manually set an aggregate address on the router, and that's a manual configuration to aggregate some of the routes. And again, that can be advertised out either way. So the rule of synchronization in BGP, you should simply know this, that BGP will not advertise a route unless it knows about that route via an IGP. That's what you really need to know for the exam. Now you can disable this by typing no synchronization on your router, and then it will simply forward routes that are not in the IGP. So here's what you've learned. You've learned about the BGP basics, path attributes, the AS path, eBGP versus iBGP, public versus private ASNs, how BGP updates work, and you got an idea of how you advertise routes within BGP. This is a good foundation for you as you move into the more detailed videos coming forth. Thanks. Hi, this is David Voss, CCIE 11372, and in this video we will be covering network address translation. Network address translation, or NAT, allows private IP addresses, which are RFC 1918, to be translated into Internet routable IP addresses. So this video will examine the operation of NAT, and then also a variant of NAT known as PAT, which is Port Address Translation. And then finally we will discuss NVI, or NAT Virtual Interface. The first thing you need to understand when we talk about NAT are the different types of NAT IP addresses. So I created this simple chart for you, which hopefully will help you memorize each of these address types. Now, when I referred to inside or outside, inside is inside a network, and outside would be outside of your network, such as the internet. So inside local is a private IP address. And when I say private, I mean RFC 1918. So it's a private IP address referencing an inside device. Inside global is a public IP address referencing an inside device. Outside local is a private IP address referencing an outside device. And then outside global, a public IP address referencing an outside device. As a memory aid, just remember that inside always refers to an inside device, outside always refers to an outside device. When you see the word local, think of that as private, that is private IP address that is not routable on the internet, and global, that should remind you of the internet, because global addresses are IP addresses that are routable on the internet. Now, an inside local address can be randomly assigned an inside global address from a pool of available addresses, or it can be specifically assigned an address from a static configuration. Now, whatever you choose will determine what type of NAT, or network address translation, you're using. There are two approaches to NAT. The first is dynamic NAT. Now, dynamic NAT occurs when an inside local address or addresses are automatically assigned to an inside global address from a pool of available addresses. And then there is static NAT, or SNAT, and you might want to statically configure the inside global address assigned to a specific device inside your network. So an example of that might be, let's say you have an email server that is inside of your company, and you want other email servers on the internet to send email messages to your server, but they need to point to a specific IP address, not one that's randomly selected. So in this case, you would choose SNAT, or static NAT, and specifically assign a global IP address to represent that mail server. Now, there are many books out there that will show you diagrams of inside local, inside global, outside local, outside global. And I'm not going to beat a dead horse with showing you that. The best thing I can do is actually get you in the lab so you can see from an actual running lab configuration how inside local and inside global, outside local and outside global all work together in NAT. Because specifically, Cisco will be testing you not just on these concepts, but more importantly, on how they are actually applied. So how to configure NAT, and then they may even ask you, what is the inside local address? How do you find out what the outside local address is? What command do you run? So let's go ahead and go into the How to Network Lab. We're going to be working on router 2, 1, and 4. 1 is going to be our device that we're going to configure NAT on. Router 4 will be our inside device. And then router 2 will be we'll say an internet device. So router 4 will be trying to communicate to router 2, and then router 1 will be NATing that traffic. And again, we're going to do everything on router 1 today. So whether it's NAT, PAT, or NAT virtual interface. So let's begin. So the first thing we're going to do is configure dynamic NAT. So on router 4, let's just take a look at the interfaces so you understand where we're starting from. Fast Ethernet 00 is assigned an IP address. And you can see, just check the routing table as far as any static routes we've added. Our default gateway is going to point to router 1. Now router 1's Fast Ethernet interface is 10.1.1.100. Again, pause this video if you need to set up your lab correctly. Here's router 2 serial interface. This is the public IP address, 192.168.100.2. That serial interface is connecting over to router 1. There's no need to add any static routes to get this working. And then router 1, you'll see the IP address set up on router 1. And you'll see the Fast Ethernet interface is 10.1.1.0, 10.1.1.100, and the public facing interface 198.51.100.1. So Fast Ethernet 00 connects over to router 4, serial 000 connects over to router 2, and you can see we do have one route in place because we want to set up a static route over to router 4's for their loopback address. So we're not using any IGPs, but we do want to set in one static route because we're going to initiate some packets from the loopback interface of router 4 as well. Now let's take a look at the NAT setup on router 1. And you will see here on Fast Ethernet 00, which is the inside interface, we simply have IP NAT inside. That is all you need as far as the NAT configuration on Fast Ethernet 00, which is the inside interface. Then take a look at the outside interface. This is the public facing interface, and very simply it's IP NAT outside. And again, that's self-explanatory. Now let's take a look at the NAT configuration that we have placed on router 1. You can see here we've set up an IP NAT pool. We've named it ISP pool. So any of these IP addresses, 198.51.100.3 through 14, could be or would be assigned to devices, to flows requesting network address translation. Then we state IP NAT inside source list 1, so we're referencing an access list, and then we're referencing a pool. Now the pool we've just created, but what is that access list? You'll see here access list 1. These are the devices that we are permitting NAT for. Only devices that have source IP addresses from these subnets will be NATed. So, for example, if there is a flow coming from 10.1.2.200, that will not be NATed. The traffic will simply be dropped if it's trying to access internet devices. So, but any traffic sourced from 10.1.1.0/24 or 10.1.4.0/24 will be NATed from inside to outside. Again, using the pool, ISP pool, which we've already defined. So any traffic coming from those 10 dot addresses will then be assigned a 198.51.100.3 through 14 address accordingly as the flows come in. So let's go back to router 4. Let's go ahead and just ping the public IP address on router 2. Let's go ahead and ping 198.51.100.2. And it succeeds. Again, we're sourcing it from a private IP address. Take a look at show IP NAT translation on router 1, and you can see here that the inside global address is 198.51.100.3. That is the IP address that is routable on the internet, but is referencing an inside device. That inside device is the inside local address 10.1.1.101, which we know comes from the router 4 interface. Now notice here the outside local and global address is referring to the destination address that we're trying to reach,
198.51.100.2. Now, back on router 4, let's go ahead and initiate another ping sequence. This time, let's do it from the loopback interface. And that's successful as well because we've permitted it, remember, in access list 1. And now take a look at show IP NAT translation. And you can see here the inside local address. It is sourced from 10.1.4.100. Now it is assigned 198.51.100.3 because that IP address, although it was used previously by 10.1.1.101, that has since been released. So that was available for use again. Now let's go ahead and initiate some additional pings off of router 4, and then you will see that now we have multiple inside global addresses being used. 198.51.100.3, 198.51.100.4, and again that would go on all the way up into our allowed pool up to .13. We would continue to hand out IP addresses every time we sent an ICMP packet, or I mean, even if we tried to browse or telnet, again, it would not be selective. All it cares about is where the traffic is coming from, the way we have it programmed right now. So that was dynamic NAT. Now let's do static NAT. Now remember, static NAT is used when you need to have a specific IP address assigned to a specific internal IP address. So let's say, for example, a mail server. And on router 1, what we're going to do is we are going to create a static NAT. And here's the command, IP NAT inside source static. And we're saying anything that comes from 10.1.4.100 that needs to be represented by 198.51.100.5. So anytime we go out to the internet from 10.1.4.100, it's going to show up with a source as 198.51.100.5, and the reverse is true. If someone on the internet connects to 198.51.100.5, that will be routed to 10.1.4.100 every time. So again, using mail as an example, that would be a good way to host a mail server internally on a private IP address, but use NAT to allow it still to function and other mail servers to communicate with it. Now you'll see if we do a show IP NAT translation, it's already showing up even though we have not initiated any traffic either way. But when you do a static NAT, it's automatically going to show up. This is committed. The inside global address, the inside local address have already been statically assigned. And if we go ahead and ping from the loopback interface on router 4, and then we take a look at show IP NAT translation, you will see that specific flow show up. And again, the outside local and outside global are showing up as our destination IP address. Next is port address translation. And PAT addresses a limitation of NAT. And the problem with NAT, well, it's not really a problem, it's just a limitation, is that it does have a one-to-one mapping of inside local addresses to inside global addresses. But what if you're in a situation where you only have one IP address to use? One IP address assigned to your firewall, one public IP address, but you have 100 users that need to get out to the internet. They can't each wait to use that IP address. So what PAT does, it allows multiple inside local addresses, your private IP addresses, to share that single inside global address. And it uses port numbers to keep track of separate communication flows. So let's go ahead and go into the lab and see how that is configured. So on router 1, what we're going to do is we're going to get rid of all the static and dynamic NAT configurations. So we've entered in no IP NAT inside source,
no IPNet inside source static. We've gotten rid of this command, no IPNet pool. We've eliminated all of that because we just want to do pat now. So here's the command, IPNet source list 1. So remember, access list 1 is allowing any traffic from router 4, whether it's the interface itself, fast Ethernet interface, or the loopback address. Anything that is sourced from those IP addresses destined for the internet will use serial 000 IP address, and then you use the overload command, which basically is saying I can support as many flows as possible using this single IP address by using separate ports for each flow. And let's go ahead and hop on router 4, and let's go ahead and start initiating some flows. So we'll go ahead and we initiated the initial flow, and you'll see here that it's working. Now let's go ahead and kick off additional flows from the same device, router 4. And we'll also initiate some flows from the loopback address as well. And now we take a look at router 1, and you can see all of these different flows are supported, all using the same inside global address but different port numbers. So PAT is a really useful thing for small offices, home offices, where you have multiple users and only one IP address available. It's a common, PAT is a commonly used configuration for such sites. Next, let's take a look at NAT virtual interface, and here's what Cisco wants you to know. They want you to know that NVI allows you to do a NAT configuration without needing to specify a specific interface as being inside or outside. So what it does is it performs an additional routing operation. It makes an initial routing decision, then it performs address translation, and then it performs another routing decision based on the translated address. Cisco wants you to understand those 3 steps. The only other thing that appears from the studies that Cisco wants you to know regarding NVI is how to enable it, and it's very straightforward. And what you simply do is you remove the IP. You don't need to use IPNet inside or IPNet outside. So we're going to remove that from Fast Ethernet 00. You just need to type in IPNet enable, and that's how you enable NVI. And it appears from the study books that that's what Cisco wants you to know for the exam. We don't need to go much farther than that. So here's what you've learned. You've learned about network address translation, and then you've performed network address translation in a lab, then port address translation and its purpose, its function, and its use, and then finally NAT virtual interface, what you need to know for your exam. So not only do you need to know these things for your CCNP route exam, but you definitely need to know them if you're going to be a strong engineer. So I hope they're of use to you as you continue in your craft. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're going to be defining the concept of IP multicast to lay the groundwork for the next set of videos on multicast. In this video we're going to first define IP multicast, discuss traffic types. In order to understand what multicast is, you need to understand what the other traffic types are, such as unicast or broadcast, so that we can compare and contrast the advantages and the disadvantages of multicast. We'll then discuss multicast goals, and then we'll talk about the disadvantages of multicast and how to address those disadvantages. So let's begin and let's talk about IP multicast. Now this may be a refresher, or let's just lay a foundation here for the rest of the videos on multicast. As you can see in this diagram, the receivers, which are the designated multicast group, are interested in receiving the video stream from the source. The receivers will indicate their interest by sending a message, an IGMP host report, to the routers in the network.
These routers will then be responsible for delivering the data from the source over to the receivers. The routers are going to use PIM, and now PIM you're going to learn more about in later videos. But PIM allows for there to be a dynamic creation of a multicast distribution tree. This video data stream will then be delivered only to the network segments that are in that path between the source and the receivers. So it would be helpful for you to understand that multicast is based on the concept of groups. A multicast group is a group of receivers that expresses the same interest in receiving a specific data stream. Now, the group does not have to have a geographical boundary. It probably doesn't, nor a physical boundary. Therefore, the hosts that are requesting could be located anywhere, such as anywhere on the internet or anywhere on the campus network. Hosts that are interested in receiving data flowing to a particular group must join using, as we've stated before, IGMP. And you'll learn more about IGMP in this video, but especially in the follow-up videos as well. Hosts must be a member of the group to receive the data stream for that group. Enterprise network architecture should support the transfer of all kinds of content and data, that is voice or video. But a traditional IP backbone is not efficient when sending the same data to many locations. This is because the specific data stream must be replicated to all the different destinations, and this involves utilizing many resources, especially bandwidth. With the incredible advances in collaboration tools using the World Wide Web and the Internet, it is very likely that organizations will have to support multicast traffic. Multicasting implies taking a single data packet and sending it to a group of destinations simultaneously. This behavior can be considered a one-to-many transmission as opposed to other types of communication, such as unicast, which is one-to-one transmission, broadcast, one-to-all transmission, or anycast, one-to-any transmission.
The first traffic type you will learn about is unicast. Most network traffic is unicast in nature, meaning that traffic travels from a single source device to a single destination device. As you can see in the figure below, the video server is sending traffic to a specific destination 172.31.1.1. Now, only 172.31.1.1 endpoint is receiving the traffic. You use unicast all the time when you connect to web pages. If you connect to howtonetwork.com, for example, your connection is going to go from your IP address to howtonetwork.com web server IP address. The second type of traffic is broadcast. Broadcast traffic flows from a single source to all destinations on a specific subnet. When the traffic is sent this way, it's being sent from a single endpoint to what is known as the broadcast domain. Please note that broadcasts are not used in IPv6 networks, so this type of communication is only used on IPv4 networks. As you can see in the diagram provided on your screen, the video server is sending traffic to a broadcast address. Now, you may think that all devices on any network would receive that, but that's not the case. Only the devices on the same subnet will receive the broadcast from the device originating that traffic. So as you can see, endpoints 172.31.1.1, 1.2, and 1.3 are receiving the broadcast message from the video server. The next traffic type you will learn about is multicast. Multicast provides an efficient mechanism for a single host to send traffic to multiple yet specific destinations. For example, imagine a network with 3 users. 2 of those users want to receive a video stream from a video server. With a unicast solution, the video server would have to send 2 individual streams, one stream to each recipient.
And with a broadcast solution, the video server would only have to send the video stream once, but the stream would be received by every device on the local subnet, even devices not wanting to receive it. Even though those devices do not want to receive the video stream, they would still have to pause what they're doing, take time to check each of the unwanted packets. So multicast is the ideal solution so that only the endpoints who need the traffic receive it. They are part of a multicast group. So imagine if you had a network of 500 nodes and only 100 nodes needed to receive the multicast stream. Think of the performance impact of using multicast versus broadcast or unicast. So multicast is primarily used on larger scale networks for that very reason, for that performance enhancement. The final traffic type you'll learn about is anycast. As you can see in the diagram, an IPv6 address can be assigned to multiple devices. Anycast traffic will forward traffic to the nearest host while not sending it to the farthest host. Please note that this feature is not used in IPv4 networks. So the 6-to-4 IPv6 translation protocol, for example, uses anycast. 6-to-4 gateways announce their presence on a specific IP. Clients looking to use the 6-to-4 gateway, send traffic to that IP, and trust the network to deliver the connection request to a 6-to-4 router. So I created these diagrams to help you with your studies. It's a simple way to memorize traffic types. First, you see unicast. It is one-to-one communication. Then there's broadcast, which is one-to-many communication. Multicast, one-to-many, or actually many-to-many communication. But for the simplicity of this drawing, we're showing one-to-many. And then anycast, many to few. The intent of this diagram is to show you that there are multiple possible destinations. Only one will be chosen.
With the unicast one-to-one transmission process, network resources could suffer because a packet would be generated for each destination, and this would result in a heavy network load and device CPU utilization, as illustrated in this figure. Senders in unicast transmissions must know the addresses of all the receivers. When using multicast, traffic can be sent to the multicast address, so there is no need to know specific address information for the receivers. In addition, the router processing of the packets is dramatically reduced in multicast environments. Broadcast transmissions could also create issues because devices that do not need the packets still receive them, as illustrated in this figure. When a device receives an unwanted packet, that specific device must stop running its processes and analyze the packet received, even if it was not destined to the device. This behavior affects device functionality, so sending unnecessary broadcast packets should be avoided, as they interrupt normal device functionality. This behavior can be avoided by using multicast transmissions, because devices that do not subscribe to a particular group do not receive packets in the specific stream. The process of multicasting, as opposed to the process of broadcasting or unicasting, has the advantage of saving bandwidth because it sends a single stream of data to multiple nodes. The multicasting concept is exercised by most modern corporations worldwide to deliver data to groups in the following ways, such as corporate meetings, video conferencing, e-learning solutions, webcasting information, distributing applications, streaming news feeds, and streaming stock quotes. The main goals of using multicasting are as follows: reduce processing on network devices, reduce bandwidth consumption, and reduce processing for the receiving host if it is not interested in the transmission. Multicast generates a single feed for all the devices that are interested in receiving it, and the source sends out the data as illustrated in this figure. The routers along the multicast tree make the forwarding decisions. This behavior of radiating information away from a source is completely different from the behavior of unicast transmissions, where information is sent to a specific destination. Multicast behavior is actually called reverse path forwarding, RPF, as packets are forwarded along a reverse path. IP multicast does use UDP in its operations, as UDP has a connectionless behavior. This results in several disadvantages to using multicast technology. It's a best effort behavior. There's a lack of acknowledgement process, lack of a congestion avoidance process, possibility of duplicate packets existing that arrive at a particular destination, and the possibility of out-of-order packets. These disadvantages can be easily managed using the multicast software that is running on the hosts. The actual multicast applications can sort out these unreliable communication issues that occur when using the multicast approach. So here's what you've learned. We've defined and laid a foundation for IP multicast. We've talked about all the different traffic types so that you can compare and contrast what multicast can do and what it can't do. Then we talked about multicast goals, and then finally the disadvantages of running multicast and how to address those disadvantages. All this information you will need to know for your exam, but obviously especially you'll need to know it if you're rolling out this technology on your enterprise network. Good luck in your studies. So here's what you're going to learn. We're going to do a quick troubleshooting command review with some of the basic commands that you maybe take for granted. Then we'll dig deeper into span and rspan, which are key for troubleshooting and analyzing issues. And then SNMP, which you know about, but again, it's important for troubleshooting. We'll dig into it. And finally, NetFlow. So let's go ahead and begin. Now, here are some commands you probably are aware of regarding hardware troubleshooting, but you need to absolutely be reminded of, and there's probably a few details here that you did not know. So ShowProc CPU can provide 5-second, 1-minute, and 5-minute CPU utilization statistics. Show memory very basically displays summary information about processor and I/O memory, and then it follows with a more comprehensive report of memory utilization. Show interfaces obviously goes into detail regarding actual errors and drops and other issues, which can indicate anything from cabling problems to duplex mismatches. Show controllers displays statistical information for an interface. Now let's say you're working with Cisco TAC to troubleshoot an issue, and they want a file containing the output from the show tech command. You can do that by redirecting the output of the command to an actual file. And note that when you direct output to a file, it suppresses the on-screen output, and thankfully in the case of show tech support, you don't have to scroll through all of that information. Now, if you wanted both, you could do that. But for example, if you just wanted to send the information to a file, you would enter in the following command: show tech support pipe redirect to your TFTP server, whatever that may be, and then the file you want it to output to. And that way you're not having to view all of the information on your screen, and you can actually create a file that you can send to Cisco. And more importantly, you create a file you can keep for your own records as well. Now, certainly you understand what the ping command is, but it's important to note all of the different attributes of a ping. You can tailor the ping accordingly. So for example, you can set the size of the ping, which specifies the number of bytes per datagram. Repeat, which specifies the number of ICMP echo messages sent. The default is 5. Timeout, which specifies the number of seconds to wait for an ICMP echo reply. Source, which specifies the source of the ICMP echo datagrams. And then DF bit, which sets the do not fragment bit on the ICMP echo datagram. And that last one was worth noting because perhaps you suspect that an interface has a non-default maximum transmission unit. You could send ICMP echo messages across that interfaces with the DF-PIT and size options of the ping command, and then specify the size of the datagram to be sent. So the DF-bit option instructs the router to drop the datagram rather than fragmenting it. So you can get a very good idea if a configuration, an MTU configuration on an interface, is in line with the policy of your network. Another troubleshooting tactic is to actually telnet. And by telnetting, you're not just telnetting to an IP address, you can telnet to an actual port. So if the response of open comes from the destination, that indicates that, in fact, that service is running on the device you're attempting to connect to. So a methodology you will definitely want to use when troubleshooting your network is to set up span ports. Span ports, and let's say for example we have a server communicating with a client and they're having trouble communicating and you want to analyze that traffic. A span port will allow you to capture that traffic that is flowing from the server to the client and from the client back to the server. Either direction you can capture, or both. You simply connect your network capturing device or your packet capturing device. Usually it's a specialized software on a laptop, and you create a span port on the switch, which then duplicates all the traffic going from the client to the server and sends it to your laptop or whatever computer you have connected to your network. Then you can analyze the information and specifically look at each packet. If it's dropping, you can do a detailed analysis of what exactly is in each packet, and then you can also store all of that data as well. So you can store it for future analysis as well. So span allows you to not only view traffic but to save it as well. Let's actually configure a span session on a router. And basically what you do is you set up monitor session, and you can do up to 2 sessions on a single device. So we will select session 1, and then you select your source port and destination port. So the source port is going to be the port of where the traffic is going to be coming from, the traffic you want to analyze. And you can set multiple source ports or VLANs. So for example, you can set even you can set the fast Ethernet here, or even a port channel itself. And then you would set the destination port. Now this is the interface where all of that traffic is going to be dumped onto a port where you have your network, where you have your packet analysis station connected. Here's an example configuration. Monitor session 1 source interface is fast Ethernet 01. That's where the traffic is coming from or to that we want to monitor. And then all that traffic is going to be dumped over to fast Ethernet 010, where we have our packet analysis station. We can capture all that traffic on our laptop and take a look at each packet. That's a rather basic configuration, but you get the idea, and it's certainly enough you need to know for your CCNP troubleshooting exam. Obviously, configuring span ports plays a big part in troubleshooting. Now, remote span, or RSpan, is helpful in a distributed network. So again, if you have a client and server who are communicating and you want to analyze that traffic, you do not have to create a span port directly on that switch that they're connected to. If you have a centralized location where you have an analysis device or a specialized software such as Sniffer or Wireshark, You can view this traffic using RSPAN as long as this data is trunked over your network. You can then, using RSPAN, have this information sent to your remote device. So that's what makes RSPAN unique. You do not need to connect to the local switch. You can have a centralized location or a distant location for your monitoring device. Now please note, we're not going to go through the step-by-step process of configuring RSPAN. It's very similar to SPAN, but you'll want to note the differences on, just go to Cisco's website. The differences aren't that many, but it is worth noting. The next important tool you can use for troubleshooting is SNMP. Now SNMP is pretty straightforward. Let's say you have a router on your network that you would like to monitor. You would like to receive updates from that router as well regarding performance, up-down time, interfaces up and down, and also you just like to monitor for CPU or memory utilization using SNMP. Basically what SNMP allows you to do is to have a network management station communicate with the router using SNMP, and the router can respond using SNMP as well. And all of the data on the router health can be monitored from the NMS. And again, that ties back to any network device. Any device connecting to a corporate network nowadays certainly is capable of SNMP communications and can be monitored. Let's go ahead and configure SNMP on a device. So here we set SNMP server, and the first thing we want to do is we're going to set the community string. So you can see there are a lot of options for us, but for now we just want to set community string so that this device can begin to communicate with the network management station. And the community string we'll set is CCNP win. Now that being said, let's say we want to send traps to the network management station. We need to know where to send those traps to. So we configure SNMP server, and the host of the network management station is 192.168.1.2, and we'll say we just want to send traps to that network management station to let it know when we have problems on this device. And that network management station is running version 3, so we're going to use SNMP version 3, and then you can set authentication as appropriate. Next, let's just configure some basic information on this switch that can be passed on to the network management station. For example, if we want to set who the contact would be if there's a problem with this switch, it's just SNMP server contact. We'll put David and then a phone number. And of course, you can do other basic information like SNMP location, and it's in Richmond. This is obviously helpful on the network management station as you pull reports. This type of information like chassis type, location, contact information, that's obviously very useful to have when you're pulling it up from a network management platform such as SolarWinds. It's nice to have that at your disposal instead of being required to log into the device. And here you can see our basic configuration of SNMP. Needless to say, the Cisco platforms support the full array of SNMP offerings, and obviously SNMP plays a big part in troubleshooting. Next, let's talk about NetFlow. NetFlow gives you different capabilities than SNMP. And let's say, for example, we have a web server and an IP phone, and they're connected to a switch. Now NetFlow, as we build out this network, NetFlow is something that would run on the router that supports all of these devices, that would analyze the communications going to and from them. So here's our UC server. And here's our collection server, our data collection server. NetFlow is going to analyze the specific flows between, let's say, the phone and the unified communications server, or out to the web. You can get very granular and look at traffic, and it will help you make decisions on your network, which could include quality of service configurations. So here's what you've learned. You received a basic refresher on some basic troubleshooting commands, and then we went into SPAN and RSPAN and their purpose and how to configure them, SNMP, and then finally NetFlow. You'll need to know all of these for your CCNP troubleshooting exam, and I'm confident that this video will have you well on your way to passing your exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video, you're going to learn how to troubleshoot device management. Specifically in this video, you're going to learn how to troubleshoot SNMP, SPAN, and logging. Now, please note, we're going to focus in on the troubleshooting commands that Cisco specifically wants you to know for the CCNP troubleshooting exam. But that being said, these commands obviously can be used in the field very effectively, which is why they want you to know them. So let's go ahead and begin with SNMP. Now, this video assumes you have a knowledge of SNMP. If you do not, then I ask that you go back to the Cisco CCNP routing videos and watch the video on SNMP so you have a good solid foundation of what SNMP is. And the first thing that is a typical issue is mismatching community strings. So for the network management system to read or write from an agent, the read community string or the read write community string, it must match between the agent and the NMS. The next most common issue when troubleshooting SNMP issues is the access lists. Now, often these can be incorrect, and if you're using ACLs to define which NMS server is allowed to retrieve objects from the MIB, the ACL has to be accurate, obviously. So you must, when you're troubleshooting SNMP, it's inherently expected that you're going to be troubleshooting access lists as well to make sure the configuration is correct. And also, to prevent index shuffling and to guarantee that there is index persistence during reboots or upgrades, you would use the SNMP server if index persist command. So, but the key point here is that you just understand that you can be proactive about preventing index shuffling. Now, if your agent is configured to send traps or informs, you need to verify the following. First, verify that obviously traps are enabled and that the correct host, that is the NMS IP address, is specified, that you have the correct SNMP version specified, and obviously the correct community string specified as well. And finally, just remember this, the default is for traps to be sent. Now, SNMP offers major improvements over SNMP version 2C, specifically when it comes to security. But that being said, with all this enhanced availability, there's also can be more opportunities for issues. So, although it offers improved authentication and encryption, you need to keep the following items in mind when you troubleshoot SNMP version 3. First, with SNMP version 3, note that you're creating users with authentication and encryption parameters, and these are nested into groups. So you need to make sure that the nesting of users and views and groups are done correctly. Otherwise, SNMP version 3 will not function as you would expect. Also, SNMP version 3 supports 3 security levels: no auth, no priv, auth, no priv, and auth priv. So the security level specified for the group and the users
And also traps has to match what is used on the server as well. So make sure that you do not have the wrong security level specified. The next issue to be concerned about is the wrong hashing algorithm or encryption algorithm, and making sure that passwords are correctly defined. So these algorithms must match, and obviously the password must match as well. The wrong OID specified in the view, so the views identify objects within the MIB that the NMS will be able to access, and if the wrong objects are identified, obviously SNMP version 3 is not going to provide you with the results you're expecting. Next is the correct configuration of notifications. If your agent is configured to send traps or informs, then actually just hop back to the previous slide, because you'll want to verify all of those items to make sure it's working correctly, specifically making sure traps are enabled, the host IP address is specified, and etc., which we covered in SNMP version 2. And then also another issue in SNMP version 3 could be that indexes are shuffling, and again, that's the SNMP server IF-index persist command. The key point there, again, is to note that you can be proactive about handling that issue. So let's log into the How-To Network Lab. We're just going to jump on router 1, and we're going to take a look at the SNMP programming on this router. And this is something that you would typically look at when you're troubleshooting SNMP. Now, there are many things here for review, but some of the key things that you may want to look at is making sure that you have the same version of SNMP running and the same authentication. As you'll see here, it's set to priv. The next thing you'll want to check for is on the access list. You'll see here it's access 99. Is that you'll want to ultimately pull up that access list and verify that it's the exact IP you would expect to be communicating with. Now, although you can look at the SNMP groups programmed by looking at the running config, an easier way to do that, and a command that Cisco wants you to know about, is verifying the SNMP groups with the show SNMP group command. So as you can see here, the group is NMS read only. The security model is version 3 priv, which is auth priv. And the associated read-only view is MIB access. And only servers in access list 99 will be permitted to read the OIDs in the view. Now, another command that Cisco wants you to be aware of is show SNMP user. To verify configured SNMP users, you do so with the show SNMP user command. Here you can see we have a user NMS server, and the authentication protocol as well as the encryption protocol is listed. And the user is associated with the group NMS read only. To verify where traps or informs, basically your notifications, are being sent, you'll want to use the show SNMP host command. As you can see here, the notifications are being sent to the network management station at 10.1.100.100, and it's using UDP port 162. The specific notifications are traps, and the username that will be used for authentication and encryption is NMS server. And again, you can see the security model here as well, which is version 3 priv. And the final command you should be aware of is show SNMP view to view all OIDs that are included in all of the views. The next topic is logging. Now, if you want to know about logging in detail, please go to the CCNP routing videos. But how do you troubleshoot routing? Well, it's pretty straightforward. Rather than actually explain this, I'm just going to run the command, and maybe you can tell me some information about what you see here just by entering in the show monitor command. So the administrator calls to complain that they're not receiving any information on their monitoring station. The monitoring laptop, which has Wireshark on it, is connected to gig 948, and they're asking what the problem is. And obviously it's rather straightforward. You can see here the source port is gig 946. The destination port for that traffic is 947. So either they're going to have to switch their Wireshark laptop over to gig 947, or you can simply reprogram this router to forward traffic on the destination port to gig 948. Now, here are some typical logging issues that Cisco wants you to know about. Now, certainly there can be many issues that can go wrong with logging, but just focus in on these for now. These are things that you might be asked about. First, just note that by default, console, monitor, and buffer logging display messages with severity level of debugging and lower. Now, by default, logging to a server is disabled, but please note that when enabled, all severity levels will be sent to the server. And when you enable logging to a server, you obviously need to make sure that you have the correct IP address specified, that IP address is reachable, and that port 514, UDP port 514, is allowed through the entire path. So if you have a firewall blocking, obviously that would cause an issue. Now, another common problem is that buffers fill up and you aren't able to read all the logging messages you would like. So note that the default buffer size is 8,192 bytes. This rarely is large enough, so you can either send your logging to a server or increase the size of the buffer to solve that problem. To troubleshoot logging, the command you'll run is show logging, and as you can see here, it brings up a lot of information, almost everything you need to know about your logging setup. Here you can see you're logging to a server 192.168.1.100 using port 514. A logging source interface has been specified as serial 000. But again, anything you program with logging is going to show up in your show logging command and will be very easy to understand. So actually, troubleshooting logging should not be that difficult. Usually, when you're having logging errors, it's either an issue with blocked traffic or just a configuration error. So here's what you've learned. You've learned about troubleshooting SNMP, troubleshooting span, and logging. All of these seem pretty straightforward, and they generally are, but as a good reminder, you've seen some of the key commands you need to know to pass your CCNP troubleshooting exam. I wish you the best of luck in your studies. Thank you. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn how to troubleshoot IP SLA. So here's what you'll learn. First, we're going to do an IP SLA overview and cover IP SLA configuration, and then we're going to dig into IP SLA troubleshooting commands. Now please note the focus of this video obviously is going to be on troubleshooting. And if you need to learn about IP SLA and you don't really understand what it is in the first place, I suggest you go to the CCNP route videos, find the IP SLA video, view that first, and then come to the troubleshooting section. Because when we do an overview in this, the overview assumes that you have a knowledge of IP SLA, and the overview is really just a few minutes of a refresher. So IP SLA measures network performance, and it tests network availability. And it does this by generating a reliable probe or simulated traffic. And it's continuous and in a very predictable manner. And you can collect information about such things as application performance, server response time, jitter, network availability, and you can even test voice quality as well. IP SLA consists of a source, which is actually sending the probes onto the network, and a responder, which is replying. Now, please note you don't require both a source and a responder. The source is required, but a responder is needed usually when you're trying to get granular details, granular statistics, and often for services that are not offered by any specific destination device. So in that case, the responder would be given the ability to respond back to the source with accurate measurements. When troubleshooting IP SLA, Cisco recommends that you focus in on the following 3 points, and this will capture most of the issues you're having
with IP SLA and how to fix them. The first is to make sure that your source and destination IP addresses are correct. The destination IP needs to be reachable and obviously correctly defined, but the source IP address also needs to be reachable from the destination and obviously correctly defined as well. Next, another popular problem is entering in port numbers that are inaccurate. So you need to verify that if you are using port numbers that they are correctly identified. And then finally, another popular reason why IP SLA isn't working, it's somewhat of an obvious reason, but people often forget to start it. It's one thing to program IP SLA, as you will see in the lab, but you also have to remember to kick it off. And if you need to use it, and if you need it to start working immediately, you need to make sure you designate that you want it to start immediately. So let's jump into the How-To Network lab. We're going to work on router 1 and router 2 over the point-to-point connection, on the serial connection. And we're going to configure IP SLA. Now note, router 1's serial interface is programmed as 192.168.1.1. Router 2's serial interface is programmed as 192.168.1.2. On router 2, we've added a loopback address, 10.1.1.1 to loopback 100, and then quite simply on router 1 we created a static route pointing to that 10.1.1.0/24 network. We simply point a static route over to router 2's serial interface, and then we have connectivity from router 1 over to router 2's loopback address. That's all we need for this lab. It'll give us enough to do the IP SLA troubleshooting that we need to do. So you can learn how to do some real quick refresh on the programming, but more specifically we can look into the troubleshooting commands. So let's configure 2 instances of IP SLA on this router, on router 1. In the first example we're going to do, we're going to create a router. We're going to create the first process. So it's IP SLA 1. And what we want to do is we want this probe to send an ICMP echo ping, basically, to 10.1.1.1, which is the loopback address. And we want to use the local source address of 192.168.1.1. And then we want to send this probe every 30 seconds. And then we want to go ahead and start it. And we're going to schedule it to run perpetually. That is, have it never expire. And we want to go ahead and kick it off. So we're going to have this probe sent every 30 seconds, and we don't want it to expire, and we're going to start it right now. So there's your first refresher. Now obviously IP SLA can get a little bit more complex than that. So let's use another one, another example. This will be our IP SLA, our second instance. Again, you want to assign a unique number. This probe is going to be testing UDP jitter over to the loopback address of router 2 using port 6500, and the source IP will be our serial interface, and we're going to send 30 probe packets for each test. The data size of each of these packets is going to be 200 bytes, and we are going to repeat this every 60 seconds. And again, we have to remind ourselves to schedule this. We're going to go ahead and start this probe immediately and set it to never expire. Now, if you want to verify the operation supported on the platform you're on, and also how many operations are actually configured, you can run the show IP SLA application command. And as you can see here is the supported operation types that we can perform on this platform. And then you can also see that we have 2 active entries. And as you know, you've programmed 2 of them.
And so obviously that's the number we would expect. Now, if you want to verify the configuration values for each of the IP SLA instances we programmed, as well as the default values that we didn't modify, we can do a show IP SLA configuration command. And we will see in this case, we're going to look at instances number 1 and number 2. Both will show up. And we can verify for each of them the type of operation that is being performed, the timeout, the source and destination address, and the frequency that it's run, among many other things that you see here. This is obviously important. Instead of, performing a show run, if you're tested on this, Cisco isn't looking for you to perform a show run. They want you to understand how to run these commands and what each of these commands offer. In their preparation materials, it appears that these are the ones they're focusing on as commands you would most likely run that would be the most beneficial for you to run. And speaking of commands, another excellent command to run, because it's going to show you the statistics that you've collected, is the show IP SLA statistics command. And in this output, you can verify the type of operation, when it was last started, and some of the values returned. As you can see here, in IP SLA instance number 1, it has a start time, and then you can see the number of successes and failures. So our test has succeeded 7 times. Our ICMP echo request has succeeded 7 times. Now for the second IP SLA operation, we performed that one mainly just to show you, to remind you of how to code something like that. But right now we're not actively running a UDP jitter test. We don't have a valid responder on the other end. But that being said, speaking of responders, now if you'll remember, a responder is not required, but can be used. Now if we jump on router 2 and we do a show IP SLA responder, you can see here that it is disabled. Now you can go ahead and enable router 2 as a responder with IP SLA responder. Now obviously there's some other options, but quite simply we're just going to hit enter for now. And now if we enter in the command show IP SLA responder, you can see we're getting different feedback now. We see that we have received a control message with 0 errors, and we received it from 192.168.1.1. So you can gather statistics on both ends of the flow, but the most important point to make here is that, let's say you do not have access to the source, and let's say it's run by a third party, but you do have access to the responder, the destination. You can configure it and run the appropriate commands to see that things are working appropriately. Should you need to troubleshoot, and let's say you only have access to one side of the communication flow. Finally, let's jump back onto router 1, and let's go ahead and run a debug on the first IP SLA process. And you can see here the alarm scheduler has basically woken up, starts the operation, provides you the source IP and the ICMP echo it's sending from that source IP, and then notifies you that it is updating the result. So you can get very granular in your troubleshooting of IP SLA, not just running IP SLA commands, but running the debug specifically for IP SLA and seeing how things are operating. All of these are fair game in your CCNP troubleshooting exam. You should definitely know this material. So here's what you've learned. You've received a brief overview of IP SLA with a reminder if you need to get into detail, you should go over to the CCNP route videos for a longer video on IP SLA. But then we got into the lab and you saw the most popular commands that you need to know to troubleshoot IP SLA, the most likely commands you will be tested on in your CCNP troubleshooting exam. I wish you the best of luck in your studies.
Hi, this is David Voss, CCIE 11372, and in this video we will be discussing policy-based routing and IP SLA. So we're just going to focus in on these two topics, and what we'll do is we'll cover them at a high level and then jump into the lab and configure them as well. The configurations are exactly what you're going to need to know for the CCNP route exam. So policy-based routing intercepts selected packets on the incoming interface. And then instead of simply routing them based on destination, it makes a decision based on other information, such as where it came from or what tags it may have. So it doesn't base routing on where it wants to go. It bases routing on other information. So a good example here is, let's say we have a web server and users who try to access that web server. And there are multiple ways to get there. And let's say, just by the nature of how routing's set up, that they choose the middle path. Now that's the way routing's set up. The next hop to reach that web server, the best path is over this middle connection. But let's say you have a new group of users who are not high priority users, and you want to send them over a lower bandwidth link. You can do that by simply saying anything coming from these users, I'm going to create a policy, policy-based routing on this router to say, if you are coming from this new group of users, I'm going to forward you over to the lower bandwidth connection over to this other router, and you're going to use that. So the high priority users use the typical route best path. The lower priority users, policy-based routing sends them over a lower bandwidth link. The best way to show this to you or explain it to you is actually to do it in the lab. So between router 4 and router 1, we're going to connect on the back end the two fast Ethernet interfaces. And we're going to get this point-to-point link up because we're going to use it for policy-based routing. So on router 1, we're going to bring up fast Ethernet 01 and assign it an IP address, 192.168, and let's choose 201.1 and make it a /30. And then we'll jump over on router 4 and we'll configure the other side of this point-to-point. And now we just ping across it, make sure it's working okay. And it is. And just to verify, let's just trace, make sure we're not learning a route some other way. And there it is, it's directly connected. So what we're going to do is, right now on router 3, if we try to reach the loopback for router 1, it's going to fail. It goes over to router 4, and then router 4 sends it back to router 1, and there's a loop, and it's confused, and packets get dropped. So what we want to do on router 4 is, router 4, anytime he receives a packet from router 3 destined for router 1's loopback address, we want to forward it over that new point-to-point link. So first thing we do is set an access list permitting anything coming from router 3's serial interface and destined for router 1's loopback, and we designate that, and then we create a route map. We want it to use FE, and we're going to match the IP address, the ACL we just created, and then anytime it matches, we're going to set the next hop for that traffic over the point-to-point Ethernet connection. So anything from 172.31.1.2 destined for 192.168.10.1, the next hop will be then set to 192.168.201.1. And we apply this on the inbound interface from router 3. So on the serial interface on router 4, we're applying the route map. the IP policy route map. And you'll see now if we do a trace, it's not going to time out. It's going to work. It'll be there. It'll make it there in 2 hops. Now let's give it one more try here. We'll give it one more try here. And there we go. So now router 4 is forwarding traffic over that point-to-point circuit based not on destination necessarily, but using the route map based on where the traffic is coming from. Now if we go back to router 4 and if we remove this route map, this IP policy route map, we will see that once again traffic times out. So policy-based routing allows you to manipulate routing. Now it does take up extra CPU on a router. It is usually not the ideal, but it is an option for you if you want to route, for example, based on where the traffic is coming from. Now let's talk about IP SLA. IP SLA measures the ongoing behavior of the network, and it can act as a tool to test and gather data about the network. And specifically, all the information that it gathers can be accessed by network management tools, and it collects that data and can provide reports. But IP SLA is actually a critical and underutilized feature in routing, but also something you really need to know for the CCNP route exam. So you can use IP SLA to monitor many different things, as you can see. Here are just a few. And what we're going to do is that in the lab, we're going to set up monitoring of, let's say, a certain loopback on a certain router using ICMP. And what we're going to do is we're going to jump on router 3. And let's say on router 3, we want to monitor the loopback of router 1. Just to see the status of it, to monitor the status of it. So we'll type in IP SLA 101, and then we're going to monitor ICMP. And we're going to measure up-down status, basically. And we're going to choose the loopback of router 1, which is 192.168.10.1. And we're going to initiate these packets. We're going to initiate these packets from our serial interface over the frame relay connection. So the frequency, we're going to monitor every 10 seconds. And now we're not done yet. We need to schedule it. So let's schedule this. IP SLA schedule. We choose the SLA number we've chosen. We're going to do a start time immediately. We are going to run it ongoing. So now this router is monitoring the loopback of router 1. And we're going to show IP SLA statistics. And you can see here we've had one failure already, so it's not reachable. And this will go every 10 seconds. It will test. Here we have additional failures. So this is just a very basic example of how IP SLA works. But that's about the level they would like you to know for the CCNP route exam. So here's what you've learned. You've learned about policy-based routing and why we would use it and how to implement it. And you've also learned about IP SLA, the advantages of using it, how to implement a very basic scenario, but a typical scenario of what you might be tested on. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're covering SNMP and IP SLA. Specifically, we're going to learn about SNMP, and we're going to go into a lab and configure it. We're also going to learn quite a bit about IP SLA and syslog as well. So all of these can help us maintain a highly available network. Let's begin with SNMP. SNMP is an application layer protocol that provides a message format for communication between SNMP managers and agents. SNMP provides a standardized framework and a common language used for the monitoring and management of devices in a network. The SNMP framework has three parts: an SNMP manager, an SNMP agent, and a MIB. Let's cover these in depth. The SNMP manager is the system used to control and monitor the activities of network hosts using SNMP. The most common managing system is called the Network Management System, or NMS. The term NMS can be applied to either a dedicated device used for network management or the applications used on such a device. The SNMP agent is a software component within the managed device that maintains the data for the device and reports these data as needed to managing systems. The agent and the MIB reside on the routing device or the switch. The SNMP agent contains MIB variables whose values the SNMP manager can request or change through get or set operations. A manager can get a value from an agent or store a value onto that agent. A key feature of SNMP is the ability to generate notifications from the SNMP agent. These notifications do not require that the request be sent from the SNMP manager. There's unsolicited messages or notifications, and these can be generated as traps or inform requests. Traps are messages alerting the SNMP manager to a condition on the network, and inform requests are traps that include a request for confirmation of receipt from the SNMP manager. Now, notifications can indicate improper user authentication or restarts, the closing of a connection or loss of connection to a neighbor router, or other significant events. Traps are often preferred because informs consume more resources in the router or on the switch in the network. Unlike a trap, which is discarded as soon as it is sent, an inform request must be held in memory until a response is received or the request times out. Also, traps are sent only once, while an inform may be retried several times. The retries do increase traffic and contribute to higher overhead on the network. There are three SNMP versions that you should be aware of. Version 1, which is the full internet standard defined in the initial RFC 1157. SNMP version 2C, which is community string-based administrative framework. The C stands for community, and it is an experimental internet protocol defined in RFC 1901, 05, and 06. Now, that being said, SNMP version 3 is an interoperable standards-based protocol defined in RFCs 2273 and 2275. SNMP version 3 provides secure access to devices by a combination of authenticating and encrypting packets over the network. The security features provided in SNMP version 3 are as follows: message integrity, which ensures that a packet has not been tampered with in transit; authentication, which determines that the message is actually from a valid source; and encryption, which scrambles the contents of a packet to prevent it from being learned from an unauthorized source. Let's go into the lab and configure SNMP. The first thing we'll do is we'll define an SNMP community string. We use an SNMP community string to define the relationship between the SNMP manager and the agent. The community string acts like a password to regulate access to the agent on the router. So we configure an SNMP community string by simply typing SNMP server, community, and then the string we desire. Now, if we want our switch to send traps, we need to define that in SNMP as well. We do that through the SNMP server host command. we simply type in SNMP server, the host, and the host ID, which is normally the IP address of the host, and then what we would like to send to the host. Also, you can specify what version of SNMP you are running and if you are running authentication as well. A popular use of SNMP programming is when someone sets the contact location and serial number of the SNMP agent so that these descriptions can be accessed through the configuration file, and so that should somebody want to pull up information about the device, they can easily do so via SNMP. To configure contact location and, for example, and serial number, you simply type in SNMP server and then contact, and you would put the contact name or the phone number, SNMP server location, and then where it actually is located, and finally SNMP server chassis ID, which is where you would enter the serial number. Now, to monitor SNMP status, which we'll do now, let's check all of the changes we've made. We can do that very simply by typing show SNMP. On to IP SLA. IP SLA allows you to monitor, analyze, and verify IP service levels. It's comprised of two components, a source and a target. Operations can broadly be categorized into 5 functional areas. Let's take a look at an example. You can use IP SLAs to monitor the performance between any area in the network, core distribution, and edge, without deploying a physical probe. It uses generated traffic to measure network performance between two networking devices. So as we draw this out, this shows how IP SLAs begins when the source device sends a generated packet to the destination device. After the destination device receives the packet, depending on the type of IP SLA's operation, it responds with the timestamp information for the source to make the calculation on performance metrics. It then can communicate with a performance management application via SNMP to provide real-time analysis of the network. It should be noticed that IP SLA can communicate with any IP device on the network that's enabled for these types of measurements. You're probably already aware of syslog, that it's a protocol that simply allows a host to send out event notification messages. A syslog daemon or server is an entity that listens to the syslog messages. It uses UDP as the underlying transport mechanism. There are additional high availability tools that can be used on the network. These include Cisco iOS Embedded Event Manager, which provides real-time network event detection as well as onboard automation, and Cisco Network Analysis Module, which improves network performance visibility to help manage application delivery. Let's take a look at Cisco Works LAN Management Solution. This is an excellent tool to ensure that you have a highly available network. There are many different modules that can be used or applications, such as Cisco Works Health and Utilization Monitor, Device Fault Manager, to name a few. Cisco Works LAN Management Solution is an integrated suite of management functions that simplifies the configuration, administration, monitoring, and troubleshooting of Cisco networks. Now, there are many functional areas that you should know about, but specifically, let's talk about monitoring and troubleshooting. You can quickly and proactively identify and fix network problems before they impact end users or services. So here's what you've learned. You've learned the basics of SNMP and a good foundation for moving forward in your studies. You've learned about IP SLA and how basically it works on the network. You've received a refresher in syslog. And finally, we briefly covered some additional high availability tools. All of these will provide you a solid foundation moving forward in your studies.
Hi there, and welcome back to this video series on the CCNA security exam, implementing Cisco IOS network security. We're progressing, and this is the section 2, security and Cisco routers. This is the part 1 video in this section, and there will be several other parts. In this video, you will learn about the borderless networks. We'll also introduce some Cisco devices, and then we'll move on to the different planes of a Cisco IOS device. And finally, the really fun part, will start with the practicals in this section. So what is the borderless network? In times past, the organization was one. So you had an organization, you had their servers, you had their users, maybe a few laptops, mind my drawing, maybe a few laptops. And then, so let's say you have the server farm, and everybody was one. Everybody connected to the servers in the organization while they were on the organization. So nobody connected from outside or anything like that. If you needed resources and access to the organization's resource, you have to come into the organization. Now things are a bit different. You have servers, the servers or whatever of the organization in the organization, and then you have the internet. We could call it the cloud. So this is the organization, and maybe it has some servers in there. So connected to the internet. Now people connect to these resources virtually everywhere. They use laptops, they use computers, they use iPhones, they use their iPad, they use their mobile devices. Basically, the network has gone borderless. There's really no border like we see here. So there was like a border, a perimeter in the first one, and it's either you were in the organization, you were out of the organization. Right now, people can be anywhere and still be connected to the organization's resources, whether via VPN, or you have this thing about bring your own device right now, and then bring your own device. That's like a laptop, your iPad, your iPhone, and you can still connect to the organization. This is because of the needs of today's organization. And this is what the borderless network deals with. But this poses problems for security. When everything was in one place, it was easier to secure everything. But now when you have people connecting from virtually everywhere, you have to take into consideration your security practices and your security methods. Now let's have some Cisco devices that are used in the borderless network. The first are the routers. This is how a router looks in real life. And this is like an icon. So when you see this in any Cisco book, you know it's a router. Sometimes we draw it like that, but you know it's a router. Cisco has this thing they call the ISR routers. That's the integrated service routers. They basically have a lot of features in them. They can do routing, they can do packet switching, they have security features on them, and things like that. Next device that we have on the Cisco list are the switches themselves. So we have the Catalyst switches, you have the 6500, you have different types of switches, basically depending on whether it's a branch or whether it's a campus network or whether it's a really big one. And this is the icon for the switch. This is supposed to be CCNA knowledge, and you should already know about these things and their icons before taking the CCNA security exams. But if you didn't, you can always know about them here. So switches connect the access layer. This is where you have your end devices, your computers, you have your laptops, you have your iPhones, and things like that. But switches are not only used for the access layer, they're actually also used for the distribution layer and the core layer. This, like I said, is CCNA level knowledge, and you should know about them. Next on the list of devices that we're going to see is the Cisco ASA firewalls. It was formerly called the PIX firewall, but now the name has changed to the ASA. ASA stands for Adaptive Security Appliance, and this is the icon for it. So when you see this icon anywhere, you know they are referring to the ASA firewall. The icon for the peaks is something like this. So this stands for the peaks, and this is what we use for the ASA, but most of the time we can't draw something fancy like this when referring to the ASA or the firewall, so we still use the same icon for the peaks. We also have devices like the Cisco ISE. It used to be just like a NAC appliance, or maybe your AAA server or ACS, what Cisco called the ACS Access Control Server. And we'll also look at these devices in this CCNA security series. Now, all these devices have different placements in the network. Routers may be placed towards the edge. Switches are usually at the access layer and maybe in your data center for your distribution and your core, while your ASA will be used to split up borders. Since this topic is about securing the Cisco routers, we will begin with understanding the parts of the Cisco router that we need to secure and what parts of security applies to each of these planes. A Cisco IIS device has 3 planes. The first is the management plane. The management plane. Now, what is the management plane? The management plane is the part that deals with the configuration and management of the device itself. So anything that applies to the router as a whole, or anything that applies to the switch as a whole, is taken care of by the management plane. So for example, when you telnet to the router, you are actually interacting with the management plane. Also, when you're configuring, as we're going to see, through CLI, you're actually interacting with the management plane. The second plane is the control plane. Now, what the control plane does is to ensure that the network device, which is like in this case, the router, can maintain the functionality of the network. So it consists of protocols that enable communication on the network. So you have protocols like ICMP, you have protocols like EIGRP, you have other protocols like, say, OSPF. And finally, the third plane of the router is the data plane. Now, the data plane is the one we're most familiar with because that's the one that deals with transit traffic. So if a host A on the network sends a packet to a host B and the packet has to travel through this iOS device, right? Then the plane that handles this transit data is the data plane. Those are the 3 planes on a Cisco iOS device, and every security feature that we're going to implement will target one of these planes. Now let's talk about the different security features that can be implemented for each of these planes. I'm just going to clear up the screen right now so I have a fresh screen. Now we have a fresh screen. The first that we'll consider is the management plane. Like I said, the management plane is the plane that deals with traffic that is sent directly to the device. The management plane is very important and it needs to be secured because it gives access to the configuration of the device. So any unauthorized access to this plane can be very devastating. The kind of protocols that we have for the security of this plane include SSH and HTTPS. SSH is secure shell, while HTTPS is secure HTTP. For this plane, it is better to use secure protocols like these 2 that I've mentioned rather than using things like Telnet. Telnet is also a remote management tool that we will consider, but it sends things in clear text. You shouldn't use things like Telnet and maybe HTTP. Use the secure version, SSH and HTTPS. Also, you can use ACLs to permit certain IP addresses to connect to the device. Other security measures under this plane include role-based access control, authenticated network time protocol, and syslog for logging and reporting. Now let's move on to the next plane, which is the control plane. For the control plane, this is mainly about protecting the brain of the iOS device, which is the CPU. If the CPU is overwhelmed, then all other planes will be affected. Something that you could consider under here is authenticated routing protocols. Because if your router is fed with bad routes, then basically your entire network is compromised. So you need to authenticate your routing protocols. Another feature that we have here is the control plane policing. Also known, the short form is the COPP. So it allows the administrator to control the amount of traffic that is destined to the router itself. Another feature that we have for protection here is the CPPR. This is quite similar to the COPP, but it allows finer granularity than the COPP. Now let's move on to the third plane, which is the data plane. For the data plane, we mentioned that this is about protecting information that is transiting the router or the iOS device. First and foremost, you don't want illegal traffic or unwanted traffic to transverse your network. So you can use checks like the Cisco iOS IPS. IPS stands for Intrusion Prevention System. We're going to configure this feature later during this series. Another security mechanism here could be firewalls. So there's a Cisco iOS firewall, but it's known as the ZFW. That's the short form. It's zone-based firewall. And then another security feature here would be iOS ACLs, Access Control List, which we'll also consider during this video. And finally, you want to protect against denial of service attacks. So you have this feature called the TCP intercept, which can help you prevent against denial of service attacks. So we've seen the three different planes of the Cisco iOS device and how we can configure security measures for them. Now we'll set up our lab that we'll use throughout this series. This is the lab setup that we're going to use. As we go on, we would add more devices, but for now, this would do. So we have R1 and we have R2, both connected through their FA00 interfaces. Now we also have loopback interfaces on both of them, and we're going to configure this right now. I'm going to set this up on JNS3 for this first class, so you see how it is done using JNS3, and then from then on, I'll just be showing you the console. So when you open up JNS3, it brings up the new project setting. I'm just going to add the project name as the CCNA security, and I'm going to press OK. Now I have already set up all my iOSs. I have set up my console and everything, so I hope you have already done that. I'm going to add two routers, R1 and R2. Like I said, they're connected via the fast Ethernet interface. Now let's start both of them up. Now I'm just going to open up the console of R1, and from there we'll configure our basic settings. For this video, I'm going to show you how to change the settings for PuTTY, so I can make it bigger for you. Change settings. Under appearance, I can change the font. So let's say I use 14. And let me also make it bold. I can change my colors. Screen. The background, I can leave it as white. Yeah, that's much better. Now, for our settings, we said this is going to be on 192.168.12.1, 255.255.255.0. No shot. We also said we're going to configure the loopback and give it an IP address of 1.1.1. It's a 32-bit map, so all of it will be 255.255.255.255. One more thing to do before we go here, let's configure EIGRP. And I will just add 192.168.12.1. I forgot to add the no auto. I'll also add the 1.1.1. Let's just check our config. You'll notice that you can have the do when you want to run show commands. So I have everything there right now. I'm going to go over to R2 and do the same. Config T interface FA00 IP address 192.168.12.2 255.255.255.0. No shot. I would also add the loopback IP address 2.2.2 255.255.255.255. Let's also add the EIGRP here. No to network 192.168.12.2. You should understand the basic EIGRP configs from CCNA exam, so I'm not going to explain that. Now you'll notice that the EIGRP has already formed. Now we can just check our route table, and you can see I can see the loopback of 1.1 just to confirm. But do a ping, and yes, we're good to go. I'll just save my config right now. And that's it for the initial lab configuration. From the next lesson, we'll start using this lab fully. This brings us to the end of this video, where we have looked at the borderless networks and how users can connect from virtually anywhere. We have also looked at some of the Cisco devices that we'll encounter later in this series. And then we have considered the different planes of a Cisco IOS device, namely the management plane, the control plane, and the data plane. Finally, we set up the lab that we're going to use in this series. Thank you for watching, and I hope to see you in the next video. Hi there, and welcome back to this video series on the CCNA security exam, implementing Cisco iOS network security. This is the second video in section 2, which covers security and the Cisco router. In this video, we'll be talking about password management. As you may be aware, there are two types of exec modes that a router can be in. The first is the user exec mode. So the user exec mode is something like this, where you have the router and you have the greater than sign. And secondly, you have the privileged exec mode. Privileged exec mode. Now this is where you do a lot of your config, because the user exec mode is very limited in what you can do. Privileged exec mode looks something like this. It has the pound sign. When you're in the user exec mode, you can do maybe some basic show commands. Maybe you can ping. Sometimes you can't even telnet, you can't SSH, you can't do basic things. Now when you're in the privileged exec mode, you can do everything. Everything is available to you. But as we'll see in security, this is not always the case. Now the mode that we're usually interested in protecting is the privileged exec mode, because this is where the configuration of your router is being done, or the configuration of your switch. And in this video, we'll be looking at the different ways to secure this privileged exec mode. The first method that we're going to be considering is the enable password. Enable password. I'm going to bring up our JNS lab setup right now, and you should already be familiar with this. So now I'm connected to the console of R1. You see that our config should still be present, and I should still be connected. I should still have the connection to R2. So I haven't changed anything from the last video. You notice right now that I'm connected to R1's console, and as you can see, it's the pound sign, meaning I'm in the privileged exec mode right now. If I exit out of the console and I press return, you can see I'm still placed in the privileged exec mode. This means by default, there's no password that is asked. What this means for you is if someone gains access to your router, so if you have your routers in a data center and you have an attacker who comes in and just connects to your router console port, it means without password or anything, the person is able to change your config, is able to cause a lot of havoc. Now what we could do is to set an enable password. Let's call it Cisco. Now what this means is before you can get into enable mode also called the privileged exec mode, before you can get into enable mode, you have to type a password. Now let's test that. We'll just write this config, copy run start. You can say do write. Now the do is because I'm not in the privileged exec mode. The do in front of it allows me run commands that are supposed to be like a level lower. So I'm just going to write that. and I'll exit out of the console. Now when I press enter, as you can see, I'm still placed in enable mode without a password. Why is this? Let's check the running config. Now you notice under the line console 0, which is what we are connected to, we have this privilege level 15. It means that by default, when you log into the console, you are placed at a privilege level of 15, and this is the highest level of the router. We have between levels 0 and 15. We'll talk about these privilege levels later in another video. For now, let's remove that command, line console 0, and we say no privilege level 15. Now let's exit again and press enter. Now you'll notice now that I'm placed in the user exec mode. If I show privilege, we'll talk about this command later. You'll notice that the current privilege level is 1, which means we're basically in user exec mode. Now to get to privilege exec mode, I have to type enable. As you'll notice now, it asks me for a password, and I'm going to type the password. Cisco doesn't show the password that you type, so I'm just going to press enter. Cool. Right now, we're placed in enable mode, and as you can see, that's a level of protection for us against any potential hacker. He needs to know the password before he can log in. Now let's just take a look at the running config. Now notice this, enable password Cisco. That's a problem because we can actually see our enable password in plain text. This is a problem because if, for example, you are trying to log into your router, let's say remotely, and there's an attacker that is looking over your shoulder or something, he can actually look at your config and see that your enable password is Cisco. This means that there is no protection at all for someone who can read your configuration file because your password is actually in plain text. Now there's something that we can do, which you may be familiar with from the CCNA exam. Is called the service password encryption. Basically what this does is it adds some encryption to all your passwords or all your Cisco password. So if I type this right now and I look at the running config, notice now that my password is in some encrypted mode, and you notice this 7 in front of it. We didn't have that before. Now the 7 just means it's encrypted with the Vigenère algorithm. What this means is that you have a level of protection, meaning that all your passwords are not in a plain text. But all is not well in the networking world. I'm going to show you why I said all is not well. Let's open Internet Explorer and go to Google. I'll type crack Cisco password 7. The first cracker that we have, we just open it in new tab. So it's the Cisco password cracker. Now let's just take our password from here, copy it and paste it here. As you can see, it just cracks it easy. It means that the Vigenère algorithm, which is used by the password encryption, is not secure. It means you need a different level of security. So let's look at the second method. The second method is to have enable secret. Now enable secret and enable password do the same thing. The only difference is they use different encryption or hashing algorithms. And we're going to configure enable secret. It's the same command syntax, enable secret Cisco. So it means we cannot enable, so we already have an enable password and the enable secret should not be the same thing. So let's just remove the enable password. We'll type the enable secret again. And as before, we would log out and try to log in again. Enable Cisco. So it basically does the same thing as the enable password, but what's the difference? Let's look at the running config. Notice that the enable secret uses some sort of different algorithm than the enable password. Now this 5 stands for MD5, and anywhere you see 7, like after a password, that means it's using the Vigenère like we saw before. The 5 means he's using MD5. MD5 is much stronger than the Vigenère algorithm, and right now there is no freely available tool to crack the MD5. So we could just do a search, crack Cisco password MD5. Let's see if this works. As you can see, this utility will only decode passwords stored with the 7 algorithm, not the MD5 hash. So there's basically no freely available tool to crack the MD5 password. Let's just look at another one. Now you'll notice that the Cisco Type 5 passwords are sorted with MD5 hash, and they require brute force attack to recover the password. It means this offers us a better level of security than enable password. But what if you want to have different users log in to your router or to your device, rather than just having one general enable password? So you can create users, like you have a user called Bob, you have another user called Fred. What if you want to give them different passwords to log in? The third method is to use local password. Now with local password, you can actually create users, and then each user would have its own password. Config T, let's say user Bob. The command is actually username Bob secret. So let's give Bob secret of Cisco 1, and we give Fred a secret of Cisco 2. Now you need to understand that just putting this username without changing anything does not affect the configuration. So if I exit right now, it's still going to only ask me for the enable password, which is Cisco. So just typing in your user and not configuring other things will not do anything. So now let's look at how to make it ask for the username and the password at login. Right now we're focusing just on the console, so any setting that we'll make will be on the console. Now this login command allows you to have the local, which enables local password checking. So if I put login local and now I log out, one warning here: if you put login local on your console and you don't have any username in your database, in your local database, you have effectively locked yourself out of your router, and you need to perform a password reset, which is not good. We really don't want to lock ourselves out. So let's exit and enter. It asks me for a username Bob. The password of Bob is Cisco 1. And now you'll notice I'm still placed in the user exec mode, so I have to type enable and Cisco. So this is like two-form authentication. The first one, before I can even get access to the user exec mode, it asks me for username and a password. And the second one, before I can get access to the privilege exec mode, I have to answer the enable secret. We would see how we can change these default behaviors as we go on in these videos. So here we have seen password management, and we have considered the enable password. We have also considered the enable secret. And finally, we have considered the local password. I hope this video has been informative, and I hope to see you in the next one. Thank you. Hi there, and welcome back to this video series on the CCNA security exam, implementing Cisco IOS network security. This is the third video in the section 2, which deals with security and Cisco routers. In this video, you would learn about password management for remote connections. We'll first talk about connecting with only a password, and then we'll move on to connecting with username and a password combination. Let's kick off exactly where we stopped. Let's look at the config of R1. That was what we configured in the last video, if you remember correctly. Now you notice we have our enable secret like we configured last time. We also configured some users with passwords apart from our initial configuration of IP address and EIGRP. And then we added something under the line console, which is the login local command. Right now I'll just refresh your memory on where we are. If I exit out of R1's console, notice that I have to enter a username. One of the usernames that we configured was Bob, and we gave him a password of Cisco 1. You also notice that after Bob has logged in, he still has to enter the enable password. I'll get to the explanation of this later. Enable, and then our password is Cisco. So right now, we're back to the privilege exec mode. That's where we stopped in the last video. Now let's kick off from there. Up until this moment, we have configured the password management for just the console. However, most of the time, we're interested in remote connections. So things like Telnet, SSH, people connecting to your devices, to your network devices externally. What will be the case of this? Usually you can't go into your data center and plug in your console cable. Sometimes you may be at home and you have to edit a configuration, or you have to allow something, or you have to check something. That means remote connections are very useful. There's a topic on the CCNA security exam called secure management. And when we get to that topic, we'll explore the different remote connections. But for now, I'm just going to configure the basic settings that you should be familiar with, probably from your CCNA exam. Things like Telnet and just basic SSH. So let's start with the config. On R1, first of all, I'll just scroll up and show you. So R1 has 5 VTY lines, 0 to 4. It means you can have 5 remote connections, 1 on 0, 1 on 1, 2, 3, and 4. So let's go to R2 for example, and try to telnet into R1. First of all, I'll just make sure I can ping 1.1.1. Alright, so if I try to telnet without doing anything on R1, just the basic settings on the VTY lines. Okay, notice the message it gave me, trying 11111, and then it found it to be open. However, it says password required but none set. Let's go back to R1 and see that that's the case. I'm just going to exit out of here, show run. I'm going to give you a tip here. Rather than viewing the entire configuration, I could use some regular expressions. You could look this up later, but I'm just going to view the line configuration that relates to line. So right now, what this section line means is show only the part of the config that starts with line. Now notice under my VTY line config, I have the login command. Let's go back to R2 and see the error message again. It says password required but none set. So why am I getting this password required message? It's because of the login command under the VTY line. But if you notice, there is no password configured for the VTY line, and that's why it's saying password required because of the login, but none is set because there's no password set under the VTY. So let's change that right now. Line VTY04 and put a password. Let's say the password is Cisco. Now if I try to telnet again, yes, so now I get the prompt for the password. And now I'm in user exec mode. Notice that by default, I am placed in the user exec mode and not given privilege exec mode. I have to type enable, and then if I know the password, I'm going to put the Cisco password. Let's take it a step higher. I'm going to exit out of this remote connection right now, and I'll go back to R1. I'm back on R1, and I just want to remove the enable secret that we configured, which was Cisco. If I check that, so notice that it's not there anymore, just to confirm, because sometimes you can get it wrong with your regular expressions. But I'm just going to go through the normal config and see that enable password is not there. Notice I only have the username. I don't have the enable password anywhere. Cool, so it's gone. Now let's go back to R2 and try to telnet. Okay, so I still get the password prompt, Cisco, and now I'm in user exec mode. Now if I type enable, what happens? It says no password set. Now this is what you get when you don't set either an enable password or an enable secret password. And in effect, what you've essentially done is nobody can get into privilege exec mode unless you configure the enable secret or the enable password. So if you made a mistake or you forgot while you were configuring your router and you went home and tried to telnet remotely, and then you probably configured your password and you're able to get into the user exec mode, but you forgot to put the enable password or the enable secret, that's it, you can't get into it. And this is the error message it's going to give you. So no password set, and basically until you add either an enable password or an enable secret, you will not be able to log in. So I'm just going to put the enable secret back. And now notice he asks me for a password. Cool. I'll exit out of this again. I'll go back to R1. We're back on R1 now, and let's just take a look at our running config. Let's scroll all the way down to the line password, line V2I. Now what does this 7 tell you? It tells you that it's in the Vigenère algorithm. So if I put this password into the crack or the website that we used in the last video, we'll be able to figure out that this password is actually Cisco. And the reason we have that in the encrypted form is because we have the service password encryption configured. If this command wasn't there, you'll have seen the plain password. If you remember in the last recording, we wanted users to be able to log in with their own username and password, and we did that for the console line. We can also achieve the same thing for the V2I lines using the same command that we configured. If you remember the command, it's the login lookout command. Now login has, if I use the question mark, you can see that this enables local password checking. So login local. Let's go back to R2, try to telnet and see what the difference is. Now he asks me for a username, which if you remember, there's one of them, one of the users we created is Bob, another one that we created is Fred. Let's just use Bob, and his password is Cisco1. Enable and Cisco. Right, so right now we have changed it from asking for just the password to asking for a username and a password. Let's stop our configuration here for a moment and take a look at what we've already learned. So we've learned that by default, there's a login command under the V2I lines that requires a password to be set. But by default, Cisco does not set any password. So if you want to have remote connections, you need to set a password using the password command. We also learned that to change this default behavior of the login, we can configure the login local, which enables local password checking. But for you to do this, you need username and password combinations in your configuration. So if you remember, we already configured usernames like Bob and Fred. Also, we learned that if there is no enable secret or enable password, then if you connect remotely, you will not be able to get into the privilege exec mode. This is a summary of what we've learned so far of our configuration. In the next video, we'll take a look at privilege levels and see what they are all about. Thank you for watching, and I hope to see you in the next video. Hi there, and welcome back to this video series on the CCNA security exam, implementing Cisco IOS network security. This is the 4th video in section 2, security and Cisco routers. In this video, we would learn about privilege levels. We'll see how to use the enable, the line privilege, and the user privilege to gain access to the privilege exec mode. Now let's begin. Let's take a look at where we stopped from the last video. Show run, and I'll just show the config that relates to the line, which is what we set up for the telnet, if you remember in the last video. So we have a password, but right now the password is not functioning because we're using the local login command. So if we go to R2 and login, telnet 1.1.1, notice that we connect using the username and the password that we set for Bob. Now at this point, I'll just like to stop and show you what privilege level we are currently on. By default, when Bob logs in, he's put in the user exec mode. Now using the show privilege command, you can see what level you are on. So the current privilege level is 1. Privilege levels specify what one can do while on a router. So think of it like this. The CEO of an organization has access to all the information pertaining to that organization, financial accounts, the clients they have, and things like that. So we can say the CEO is at the highest level of authority. Now, one step below, you could have like the manager of a functional department. So he's on a privilege level lower than that of the CEO, and so on and so forth. That's the way it is with the Cisco router. When you're connected to your console, you are usually placed at privilege level 15, although we changed that in some video. We'll see how all these things work in this particular video. What you need to know is that right now we're on a privilege level of 1. This is the default when you log in via Telnet or via SSH, and we'll see why this is the default. Now you're probably familiar with how to get into the privilege exec mode by typing the enable command. Enable, and then our password was Cisco. Now if we do the show privilege command again, notice now that we are placed on privilege level of 15. This tells you that this is the first way to get into the privilege exec mode. To gain access to the privilege exec mode, you can do so by typing the enable password or the enable secret, whichever one is configured. Now I'm just going to exit out of this and we'll go back to R1 and do some configs. Now the second method that we're going to consider for gaining access to the privilege exec mode is the line privilege itself. We saw this on the console line before we changed it. It was this privilege level command, and we're going to see how it works. You can actually set this privilege for the entire line. So it means anybody who connects on that line will be placed at that privilege level. But as we'll see, this default behavior can be overridden. For this to work, I'm just going to change the login. I'm going to remove it from local username login to just the plain login. And then I'm going to set a privilege level of 15. Now let's go to R2 and see what happens. Telnet 1.1. Now as you notice, I've turned off username and password checking, so it only asks me for the password. And the password we set was Cisco. Notice straight away that I am placed in the privilege exec mode. Show privilege. As you can see, I'm in 15. It means straight away it places me into privilege level of 15 because of this command that we have here. So what this command does is that everybody who connects on that line will be placed at the privilege level that is set or that is configured for that VTY line or for that console line or for that aux line. By default, the configuration on the console line and the aux line are usually placed on privilege level of 15. That's why the default behavior of the console is that you are placed at a privilege level of 15. Although we changed that for R1. Let's see that for R2. Let me just exit out of this. Show run for line. Okay, so that's that command there, privilege level of 15. So if I exit now and I press enter, you see that I'm placed directly in the privilege level of 15. Show privilege of 15. That's the default behavior of Cisco routers. So by default, they have this command, privilege level of 15, under the console and under the aux port. However, for VTY lines, there's nothing like that. Now let's go back to R1. You notice that I had to change this back to login for this to work. I'll show you why it did not work. I'll change it back to login local, so it checks for username and password. And even with the privilege level of 15 that is there, we'll try to log into R1 again. Telnet 1.1.1. And it asks me for a username Bob and a password. The password is Cisco1. Now you can see that I'm at a privilege level of 1. That's because if we go back to R1, we find that this login local basically changes the way the router thinks. Instead of just requiring you for a password, it requires a username and a password. And what it also does is it checks the privilege level configured for that user. So even though the privilege level of 15 is configured on the entire line, it's actually checking the local database for the username and password, and that's the privilege level it's going to use, not the one on the line. This brings us to the third method by which someone can gain access to the privilege exec mode. Let's look at our configuration. Now if you remember, we configured the username of Bob and we configured the username of Fred, and we only gave them their respective passwords. Now let's change that, or rather let's add another user. So let's call this Alice. Now notice the options that you can configure under Alice. We have configured the secret. Remember that secret and password are the same thing. Secret just uses MD5, while password can be unencrypted, or you could use the Vigenère algorithm. But now notice this privilege command. You can actually set the privilege that a user is supposed to be on. So let's set that command now. Privilege between 0 and 15. So let's place Alice on a privilege level of say 3, and then give her a password of Cisco 3, for example. Now let's create another user called Aaron. We'll give Aaron a privilege level of 15 and give him a secret of Cisco 15. Right, now something you have to be very careful of here is your privilege level has to come before your secret command. Else it's going to take your password as everything after the secret command or after the password command. So what I mean is, if you do something like this, say 4, your password is actually going to be Cisco test privilege 4. So this is something you have to be very careful about. Alright, so we've configured this for Alice and for Aaron. Now let's go back to R2 and see what happens. I'll just exit. Telnet to 1.1.1. Now he asks me for a username. We configured Alice and we gave her a password of Cisco 3. You'll notice that it's not the greater than sign, it's actually the pound sign, meaning we're not in the user exec mode. So let's check what privilege level that we are on. Aha, and that's it. We're on privilege level 3, which is what we configured. If we go back to R1, which is what we configured for Alice, privilege level of 3. That means it's actually now checking the privilege level based on the username. So let's just exit and log in with Aaron. Aaron, password is Cisco 15. Show privilege. And that's it. We have a privilege level of 15. Let's stop our configuration here for a while and do a recap of what we've learned so far. So we have seen that there are 3 basic ways by which one can gain access to the privilege exec mode. The first is the enable command. Either you have the enable secret or you have the enable password. The second one is the line privilege, but this only works if you have the login command rather than the login local. And then you have the user privilege, which checks for the privilege of the user, and this works when you have the login local command. Something I'll really advise you to familiarize yourself with is this login command, because it actually changes the way things work. Now you need to understand that these are the 3 basic methods by which one gains access to the privilege exec mode. There are other advanced methods, as we'll see under AAA. I hope this video has been informative, and I'd like to thank you for watching. Hi there, and welcome back to this video series on the CCNA security exam, implementing Cisco iOS network security. This is the 3rd section where we'll deal with AAA on Cisco devices, and this is the first video in this section. In this video, you will learn about an introduction to AAA. We'll also describe the different parts of AAA, and then we'll see how to turn on AAA. Remember that in the previous video, our lab setup changed a little, where we added the CCP workstation. Some of you may already be familiar with what AAA means. In fact, throughout this video series, we have seen the different parts of AAA in one form or the other. AAA actually stands for authentication, which is the first A. The second A is authorization. As the second A, authorization. While the final A is accounting. Now in some books you also see accounting or auditing. It basically means the same thing. So I will just put auditing in the bracket. So what is authentication? Authentication is verifying who a person is. So if I come into an organization and I show my ID card, then that is authentication. Authorization is what the person can do once the person is in the organization or is on the resource. So what a person can do. So basically authorization talks about level of access. And finally, accounting is what the person did. So accounting is more retrospective, what the person did. So it kind of looks back, it takes logs and things like that. Like I said, throughout this video series, we have seen different parts of this AAA in one form or the other. For example, when we configured all the usernames and password combinations, this was a level of authentication in one way or the other. One way that we have seen authorization is privilege levels. Or if you also remember the user profile that we configured on CCP, where we restricted the user from being able to use the configure button or the configure mode. Yeah, that's a level of authorization. We're saying what can the person do, and we said the person cannot perform configure actions. And finally, accounting. You may not have noticed, but we have also seen accounting in the logs. So when an interface came up, for example, and then it showed on the console that this particular interface just came up. Yeah, so that's an example of a log. Of course, it could be more than that, where we talk about what the user did while the person was connected to the router, for example. Maybe the person issued this particular command, and then we can view the logs later. If the person was not supposed to issue some things, and then he did, that's what accounting tells us. But what is the purpose of AAA to us? In the previous videos, we have seen how to use things like enable secrets, and we configured username on the data, that's on the local database of the routers. And then we have seen all these different parts of AAA. So why do we need AAA as a particular feature? Now you'll notice that in the previous videos, all we have been doing is configuring authentication or authorization for a particular device. So it was more about securing the management plane of the device, which deals with connections made to the device itself. But what of a network in general, like an organization's network? Organizations have different ways by which they authenticate users to their network, and one that you may be familiar with is the Windows Active Directory. So when you get onto your system, you log on to a particular domain. Now that's a form of authentication. In fact, in Windows, there are several authorization mechanisms, like if a particular user is in this domain, then he cannot connect to this printer, or he cannot use this particular resource on the network. So those are different levels of authorization. So you need to understand that AAA is not a Cisco feature, it's more of a security implementation. But as we'll get to find out, Cisco has its own implementation of AAA. I mentioned earlier that the features that we've been configuring deal with the management plane. But when we want to talk about the data plane, for example, so if you already have users on your Windows Active Directory, do you have to create them all over again on your local database? That would be very, very cumbersome. Apart from that, if you have several devices, let's say you have 10 routers and you have 50 switches, are you going to configure username and password on all those devices? There has to be a different method, and that is what AAA allows us to do. So in essence, we can say AAA looks beyond the device itself. It looks at the entire network. So we're not talking about just management plane, we're also talking about the data plane, which deals with transit traffic. Also, when we get to authorization, some users should not be able to connect to some particular parts of the network. And AAA allows us to restrict these users based on their authorization profile. It could be as deep as NAC. It could be as simple as privilege levels. We are going to see some of these features as we go on in this video series. So let's just wrap up this part with an analogy. If you go to your bank, for example, and you want to collect money over the counter, you have the customer assistant who attends to you. Now in the morning, the person probably came into the office or came into the bank and logged into the network. The person authenticated to the network, probably using their user ID and maybe a password. Now, just because the person authenticated onto the network doesn't mean the person can do everything. Doesn't mean the person is allowed to do everything. So if, for example, the person is not allowed to alter your bank balance, now this is what authorization does. And at the end of the day, the person is supposed to give an account of all they have done. And that is what accounting is about. So we have seen the three parts of AAA. The first one being authentication, who the person is, and then authorization, what can the person do when the person is on the network, and then accounting is what the person did while the person was on the network or on the device. Now let's head over to the configuration terminal and see what we have. So I'm just going to do a show run on R1 and see what we currently have on R1. So we have our enable secret. Notice here that it says no AAA new model, and we'll talk about these commands in a few minutes. Let's just go all the way down to the end. So we have different usernames that we configured, and then if we go to our line console, we can see we're still using the login locale. On our VTY lines, we're also using login locale. So it means if I exit out of the console right now and try to log in again, it should ask me for a username. So I'll use one of the ones we configured, Bob and Cisco 1. And then since we have an enable secret, we'll just enter it, Cisco. Now let's talk about that command, show run. I'll just include AAA. Now by default, AAA is turned off on Cisco devices. So the command to turn it on is actually AAA new model. But of course, you need to be very careful when you turn on AAA, because AAA changes the authentication and authorization features of the device entirely. Just take note of where we currently are, and then we're going to configure AAA. So AAA new model, this is the command to enable AAA. One thing that is advisable before you enable AAA is to have some username configured on your local database. Because if you configure AAA and you get locked out of your router somehow and you don't have usernames on the local database, if you are not on console, you may not be able to get in. Now I'll just show you why I said that AAA changes the authentication feature of the router. I'll exit out of console right now. Remember previously that before we were able to get back into console, right now we had to use Bob and we had to enable a password. So let me just exit and try to come in again. Notice that I'm placed in the user exec mode automatically. So AAA has overridden our login local. The login local on the console line is no more effective. But of course our enable secret is still there. So let me just enable and then Cisco. So as you can see, AAA has completely overridden everything that we have. Let's also go to R2 and telnet right now. So telnet to 1.1.1. So it asks me for a username Bob Cisco. No, it should actually be Bob and Cisco 1. Bob Cisco 1. So you notice that AAA has overridden our configuration on R1. So let's check our config right now, show run, and then let's just look at the section line. So look at what happened. Login local has been removed completely from the console. It has also been removed from the VTY lines. This should tell you something, which I'll highlight right now. When you enable AAA, automatically it removes every authentication that you have configured on your console. That is on the console. Now on your VTY lines, it automatically enables a username and a password. That is why I said that if you configure AAA and you don't have username and password in your local database, if for example you configured it while you were remote, like through a remote connection, and you try to log in again, you will not be able to log in until you come to console. So AAA doesn't have authentication features on your console, but on your VTY lines, it automatically enables username and password combination, which is what we saw in R2. So we've seen how to configure AAA through the CLI, and that is what we did on R1. Let's use the CCP tool to configure it on R2. By now, you should be relatively familiar with this interface. So this is 1.1.1, which is R1, and then 2.2.2, which is R2. I have discovered these devices. So we're concerned with configuring 2.2.2. So if we just come to the community member here and select 2.2 and go to configure. Now under router, you'll notice AAA, there's a folder called AAA. And under that folder, there are different subfolders. We'll look at all these other ones later, the AAA server and groups, the authentication policies, authorization policies, and accounting policies. For now, we'll just go to the AAA summary. If you look at the AAA summary, it tells you the value for all of these things. So the AA server groups, we have nothing there. We have no authentication policies. We have no authorization policies. And if you notice here, it says that AAA is disabled. And then we have a button to enable AAA. So let's just enable it. Once you click on that button, this dialog box shows up. This is because the wrong configuration of AAA can be very disastrous. So it tells you that it's going to configure authentication and authorization for VTY lines. And then the local database will be used for both authentication and authorization. It also tells you that it's going to configure authentication for the console line, and then the local database will also be used for authentication. So let me just enable AAA. Yes. Now once I close this dialog box, I'm going to show you why I'm getting this config. Because for me, I like seeing the configuration that is going to send to my device. So you notice that this is the AAA new model. Now it's going to configure some authorization and authentication policies, which we're going to talk about in the next video. And then it's going to apply them here. For now, you don't need to worry about this. Just know that it's enabling AAA using the AAA new model. And I'm going to deliver this configuration to the device. And then it tells me configuration delivered to device. So I'm going to click on OK. And notice now that the AA has changed to enable. Before we end this video, I want to show you how to preview commands that are sent to your device from the CCP. So you just come under Application, you come under Options. So notice that this Show CLI Preview is checked. That is how I can actually see the commands that are being sent to the device. If I uncheck this, I will not be able to see it anymore. I'm going to click on OK. Now let's just confirm what has been done. So if I exit out of R2, notice that this is R2, not on R1. And I try to log in. Now it asks me for username and a password, CCP and Cisco. So this is because of the AA that has been enabled. If you remember on R2, we didn't need to enter username and password before we logged into the console. So let's just take a look at the AA configuration. Show run, I'm just going to say section AAA. So you can see that AA new model has been enabled. You can see that we have some authorization and authentication policies, which we will talk about in the next video. So let's stop this video here and take a look at what we've learned so far. This brings us to the end of this video, where we have looked at an introduction to AAA. We have described the different parts of AAA, which is authentication, authorization, and accounting or auditing. And then we have enabled AAA on both R1 and R2. If there's anything you take away from this video, it should be that AAA is not something to be joked with. You should always have a backup username and password combination in your local database before you enable AAA. I hope you have found this video informative, and I'd like to thank you for watching. Hi there, and welcome back to this video series on the CCNA security exam, implementing Cisco IRS network security. This is the second video in section 3, which covers AAA on Cisco devices. In this video, we'll look at an in-depth study of AAA. We will consider method lists and then focus on authentication. Now let's talk about this command for a moment, AAA new model. Remember that this is the command that we use to enable AAA on Cisco devices. So once you enable AAA, what does it do? The first thing that you need to know is that it enables all lines to use the local database to ask for a username and a password. So even if you don't have the login local on your lines, it's going to implicitly ask all lines to request for a username and password. So what this means is that if you don't have any username or password in your local database, you will not be able to log in remotely. But the only exception to this is that this is not configured by default for the console. So even though all lines would require the local database, the console is exempt. So if you configure AAA through a remote connection and you didn't have a username and a password, you still have a backup of coming to the device and connecting to the console line, because by default AAA doesn't apply any authentication to the console. But this is different with CCP, as we saw when we configured it on R2. When CCP configures AAA or enables AAA, it takes some precautionary steps. The first is that it enables authentication and authorization. So authentication and authorization on the VTY lines using the local database. And you also notice that it also enables authentication on the console line, also using the local database. Right, so these are the things that you need to be familiar with. So you need to understand these things about AAA and how AAA changes how the router thinks about authentication in general. So we'll move over to R1 and R2 and see what we've configured so far. So let's take a look at where we currently are. On R1, if we do our show run and we look at, well, let's just do the entire show run. We'll do the same on R2. Show run. So on R1, you notice that we enabled AAA. That's the command that's all we did. We only enabled AAA using the AAA new model command. And then if we scroll all the way down to our console, we see that we have nothing. Even the login local that we had there before, we don't have it anymore. If we go to R2, we see the same thing. Every login that we had is disabled. And we can scroll up and see the AAA. So we have AAA new model, and then we have this command that we're going to talk about in this video shortly. One thing that you need to note is that when you go to your line, so let's go to line console 0, notice you don't have the local command anymore. You don't have plain login, so you have to enable either login authentication or this other control C disable. So when you enable AAA, it changes the way your login command even functions. I'm just going to exit out of here. So let's just do a recap. If we go to R1 and we telnet to 2.2, which is R2, so we need a username to log in. And we need this username to log in even though we don't have the login local command on the VTY lines. So that is because we have enabled AAA. Just going to exit out of this telnet session. Now let's take a look at the configuration commands that we have under AAA. So I'm just going to do AAA with a question mark. So we have accounting, you have attributes. The one that we're interested in this video series is accounting, which enables accounting configuration parameters. You have authentication, and then you have authorization. We have some other group configurations that we're going to see and other server configurations that we're also going to see. So let's talk about method lists for a few minutes. Method lists actually give you a way to control the features. So when I talk about features, I mean the different features of AAA, that's accounting, authentication, and authorization for the different parts of your network or for the different parts of your device. So for example, on the console line, you may want to use your local database for users to connect or for users to authenticate. While on your VTY lines, you want them to use an external AAA server to log in. So that's what method list allows you to do. It gives you the flexibility of controlling how users can connect either for authentication or for authorization or for accounting. Now you notice that method list will be very different. So the method list for authentication will be different from the method list for authorization. They have different options, as we're going to see. In this video, we're going to start off with the one for authentication. Let's go over to R2. Remember that when CCP configured AAA for R2, it created some method list. So this is an example of a method list. AAA authentication, login, default, local. And this is the one for authorization. We're going to focus on authentication in this video. In the next video, we'll talk about authorization. Now let's go back to R1 and see authentication and look at the options under authentication. So notice the different options that we have under AA authentication. We have ARP, we have attempts. So attempts, we can set the maximum number of authentication attempts. So this can be good for like brute force attacks. So brute force works by trying to use thousands of passwords in a particular minute. So if you set the maximum number of authentication attempts, then brute force would be kind of limited. You can also set the banner for use when logging in. And then we see that .1x, this is something that we use for 802.1x. If you're in the Cisco security world, you're still going to need this 802.1x, maybe in your CCSP or in your CCIA. Now you notice that we can also set authentication for enable. So it won't use the enable secret or the enable password. It will use what we configured here. So you also have a fail message, and then you have login. Now the one that we are concerned with and the one that would be our focus, because that's what you use for like your console line and your VTY lines. Everybody who tries to log into this device, this is the option that we're concerned with. You can also change the password prompt and you can change the username prompt. So let's focus on login for a while and look at the options. So you can see that we're building our method list gradually. We started with AAA, now we're on authentication. We're going to go to authorization in the next video, and we'll also look at accounting in another video. Now we are configuring something for the login, and then the next thing it tells us is a name. So it asks us for a name. Either you use the default, so default is a keyword, or use a word. Now let me tell you something about the different types of names that you can have for your method list. If you use the default is going to apply to all lines that do not have a named method list. So for example, if you look at R2, this is default. So the name it's like a keyword, it's a Cisco keyword, default. So default means that on all lines mean your console, your aux port, your VTY lines, all lines that do not have a named method list would be applied with this particular method list. So we can say default is like a general method list that is used for everybody that doesn't have a specific method list. So right now I'll leave it as default, And then let's look at the options. Now these are the different methods that you can configure. So what it says is that what method do I want the lines that have this method list applied? What method do I want them to use to ask users to log in? Do I want them to use the enable password? Do I want to configure a server group that's either TACACS or Radius, as we're going to see later? Do I want them to use Kerberos authentication? Do I want them to use the line password? Do I want to use local username or to use a case sensitive local username? Or do I just want them to log in without any authentication? And then here I can set the password expiry. So this is where we see the true nature of method list. These are the methods that you can configure for people to access. In this case, we're configuring authentication methods. So people can either authenticate using the enable password or the group. Group, as we'll see, let's just do that. Group has several options. So you have Radius or you have TACACS. So you have a server group name, which can be Radius or TACACS. Now, for these methods, you can have up to 4 configured. Now, what I mean by up to 4 configured is, so if I have something like Radius and then I have local, and then I have group, and no, not group, okay, let me just say group TACACS, and then I have none. Now notice that I can have up to 4 methods configured. The first one is the group Radius, the second one is the local, third one is the group TACACS, and the last one is none. Now it checks it in the order in which I have configured it. If for some reason the group Radius, that's the Radius server, is unavailable, it's going to check the local database. If the local database is unavailable for any reason, it's going to move over to the group TACACS. If the TACACS is unavailable, then it's just going to allow the user to log in. So this enables you to have like flexibility and high availability. So if your Radius servers are unavailable, then you can fall back. So we're configuring like fallback methods. But what you need to understand is that unavailable is not the same thing as fail. So if a user, let's say Bob, has a password of Cisco 1, now an attacker tries to use a brute force for Bob and says Bob's password is Bob 1. If this Radius server should reply with a reject, that means like the password is wrong. It will not fall back to local because this has already failed. So unavailable is different from fail, and you need to keep that in mind. So let's do something real now. Let's say we want to have 2 authentication methods. One of them would allow the user to log in without any username and password. So that's using none, as you notice here. So none is like no authentication. And then the second one I want to configure, I want it to use the local database. So let's go AAA authentication. It's for login, so I want to use it for my VTY lines or something. I don't want to use the default, so I'm going to name it. So let me say this one is no auth 10. So no authentication. And then I said I want to use none. So I don't want any authentication on this. I'm just going to use none for this particular one. And then I create the second one, A authentication, login, and I say local. I can call it local DB. And then I say I want to use the local database. Now you need to understand that just creating method list and not applying it to any line has no effect, except it's the default. So if it is the default, it is automatically applied to all lines that do not have anything configured. So let's test this out. On my VTY lines, actually on my VTY, let's say 0, I'm going to use this authentication none. So you notice you use the login command, but instead of login local, it has now become login authentication. And then you can specify the method list. Notice that default is also there, but the method list that I want specified is this no auth. So no auth. And then I go to my line VTY 1 2, that's every other thing. And I give them the login authentication local database. Cool. So now let's just see how it looks in the running config. Alright, so line 0, I have login authentication no auth, and line VTY 1 to 4, I have login authentication local DB. So if I come to R1 and telnet, R2 and telnet into R1, the first one should not ask me for a username and a password because of the no authentication that we configured. And then the second one, so that's like VTY 1 to 4, should ask me for like a username and a password from the local database. I will not end this session, but I just want to open another connection. So I'm just going to use the Ctrl Shift 6X. It takes me back to R2 and I can telnet again. Now notice he asked me for a username, Bob and Cisco 1. Now let's do who to find out everybody that is connected. So you notice that VTY 0, that's the first connection that we have that we opened on R2. And then we have VTY 1, which is the Bob user that's connected on VTY 1. So you notice that this works. So with our method list now, we could say that no authentication on a particular VTY line, why we want local authentication on another one. So let's just exit out of this. I would also exit out of the second one. Let's stop here for a while and look at what we've learned already. In this video, we have taken an in-depth study into AAA. We have begun exploring method list, and we started with authentication method list. We configured login authentication method list and applied the method list on our VTY lines. We saw how to apply different method lists on different VTY lines. In the next video, we'll see how to do everything that we've done using CCP, and we'll configure this on R2. I hope you have found this video informative, and I'd like to thank you for watching. Hi there, and welcome back to this video series on the CCNA security exam, implementing Cisco IRS network security. This is the third video in section 3, which deals with AAA on Cisco devices. In this video, we will be using the Cisco Configuration Professional tool for AAA configuration, and then we also see an introduction to AAA servers. Our lab setup remains the same. If you remember where we stopped in the last video, we configured some method list on R1. So if I do a show run right now and do a section, say AAA, now you can see that we configured two authentication method lists. One was no authentication and one was for the local database. So we applied the no authentication on one of the VTY lines. Let's just look at that. Section line. Right, so we attached the no authentication on the first VTY line. So right now, if you try to log in for your first remote session, you're not going to get any authentication prompt. But for the other VTY lines, that's 1 to 4, we configured it to use the local database. That's where we stopped, and that's what we did on R1. Now let's go over to R2. If you remember, so I'll just do a show run. If you remember, when we used CCP to enable AAA on R2, CCP took some precautionary steps, and one of them was that it created authentication and authorization method list, and it used the default. Default means that it's applied to all lines that do not have a named method list on them. So let's go all the way to our line config. So you notice that even though there's no login on any of these VTY lines or any of the console line, because it's default, it applies to all the lines. So let's go over to CCP and configure some method lists for R2. We are back on the CCP tool. If you notice, I've discovered my devices, R1 and R2. Before we configure R2, let's just take a look at 1.1 and what we have configured on it. If we go to router, we go to AAA, we go to the summary. So first of all, you notice that AA is enabled because we enabled it. Now look here, you'll notice that we have some authentication policies. So we have two login authentication policies. We have none for IP over UDP and we have none for .1x. Every other thing is 0 because we do not have any authorization policies and accounting policies. Cool, so now let's go back to R2 where we want to configure things. Still under the AAA summary, AA is enabled because we use CCP to enable AAA. Now we do not have any server groups. We're going to talk about AAA server shortly. Now look at the authentication policies. We have 1 and then we have authorization policy 1. This 1.1, that's the login, and then the exec authorization policy was created by default from CCP. But let's assume that we want to create our own authentication policies. For example, I don't want to have to be logging in with a username and a password on the console. So let's create an authentication method list for the console where it will be none. So it will not be required to enter any username and password. So I'll just come here under authentication policies. So this would give you like a summary of what is configured. Now if I want to configure one, I just go to login. So notice here there's one called default and then the method is login. And like I said before, there are up to 4 methods that you can configure. So let's just add one. Now notice the name, it says user defined. That's because there's already a default. So let's specify it as, let's say, console. Or let's keep our naming convention the same, like the one we used on R1. Now you can specify up to 4 methods. So if I click on add, You can use your control key or your shift key. So you can use shift to select or control key to select, like up to 4. For now, I just want it to be local. For console, it's going to be none. So okay. So notice that there's none there. And I can click on OK. Because we have command preview enabled, we're going to see the command that is going to deliver to the device. So notice it's like what we did exactly. AAA authentication login, no authentication, and then none. So let's just deliver that. One more thing that you can notice here is that it adds this to the running config, not to the startup config. So if you wanted to add it to the startup config, you can select this checkbox. For now, I'm just going to click on OK. Now let's configure another one where we're going to use, say, the group radio servers. I know we don't have any radio server, but I want to use it for practice. I want to show you something, and then we'll configure a backup of local. So let's just add. Let's call it for VTY lines. So let's say VTY lines. I'm going to add the methods, group radius and local in that order. So notice it says AAA, this is the name, VTY lines. Then the first method that is going to use is radius. So it's going to try radius server first, and then if radius server is unavailable, it's going to try the local. So let me just deliver it. Okay. So remember that these are not default method lists, so they are not applied automatically. We have to apply them to the lines. So we just come to router access here. Click on, so let's apply the VTY lines. So you notice what is currently applied. It has an authentication policy of default. Let's change that. We'll edit, and then we can change the authentication policy here. So I'm just going to select VTY lines. I'll leave the authorization policy as it is. Okay. So you notice that it's the same commands. It just goes to the VTY line, and then it's going to apply the login authentication under the VTY line. For now, we will not focus on the authorization exec. Let's just deliver the commands. Okay. As you can see, it has changed here. So now that we've applied the ones that we configured for the VTY line, we need to apply the one that we configured for the console. I went through the CCP tool, and there's no place where you can actually edit the console configuration. So I'm just going to go and add it directly to R2 in the CLI. So what's the name? Let's just check. Right, so the name is Node. So I'm just going to go to my line console 0 login authentication node. Right, so let's just view everything that we have on our line right now. Cool, so our login console has node, so when we try to log in via the console, we will not be asked for any password. Our VTY lines have the VTY lines configured, and the VTY line means group radius and local. Now this is where the fun begins. Let's debug AAA. So we can debug AAA authentication. Now let's go to R1 and try to telnet to R2 2.2.2. Alright, now look at the debug. So it says it picked the method list VTY lines. Now it tells you that AAA bad server error, so it cannot process authentication server type radius. So if I go and use CCP and Cisco, which is one of the usernames that we have in our local database, and click on enter, go back to R2. So you notice what happened. Even though it couldn't find the radius server, it fell back and used the local database, and that's why we're able to connect to R2. So that's the difference between unavailable and fail. So unavailable means, so if you notice here, it says it cannot process authentication server type radius. That's because it doesn't know it. So this radius server was unavailable, and that is why it went to the next configured, so like a fallback method. Let's look at it again. Cool, so this is it, the VTY lines. So the first method is group radius. So what it did is it tried to contact the radius server. There's actually no radius server configured, so that just failed completely, and then it fell back to the local. So that's the difference between unavailable and fail. You should keep that in mind. So we'll just stop here for now and look at the different types of AAA servers that we can have on Cisco. Now let's take a look at AAA in general. AAA can be divided into 3 basic parts: client, the authenticator, and then the authentication server. So let's take an example. If you go to a VIP party and then there's a list of those that should enter. Now when you arrive as the guest, you are the client. Now the person at the door, let's say there's a security guard at the door who checks the list. Now the security guard in this case would be the authenticator. Authenticator in Cisco terms can be routers, can be switches, can be your firewalls or anything like that. Now your authentication server will be the list that the security guard refers to. So authentication server is the one that has all the profiles. So who should attend this party or who should attend this event? Now that is what the authentication server is going to have. It's going to have things like your authentication profiles, your authorization profiles. You may have things like NAC and other profiles like that. So far we have used the local database. So in effect, we have merged the authentication server and the authenticator as one. We have been using our Cisco devices and our routers and the local database for that. But generally, there are two basic types of AAA servers. The local AAA servers, which is what we have seen. Now, this is not a Cisco term, it's just for your understanding. So local AAA servers like your Cisco database, the local database, and then you can have remote database. So those remote databases will be like remote authentication servers. So what is the benefit of having remote authentication servers or remote AAA servers? Imagine if you had 500 devices on your network. You would have to configure local usernames and password for all the users that need to connect. Wouldn't it be better if you had like a centralized AAA server that does everything? That's all your authentication and authorization requests. You could have two for flexibility. But in this case, your remote authentication servers or remote AAA servers allow for centralized authentication and authorization in an organization. When it comes to remote authentication servers or remote AAA servers, there are two basic protocols that are of interest to us. The first one is Radius. Now, Radius stands for Remote Authentication Dial-in User Service, while the second one is TACACS, or we call it TACACS Plus, which stands for Terminal Access Controller Access Control System Plus. Now, let's look at the differences between AAA and Radius. Now, this is very important, so you should pay attention. The first basic difference is that Radius is an open standard, while TACACS is proprietary. So TACACS is actually proprietary to Cisco. It's actually Cisco's implementation. Now, Radius uses UDP, and then the ports vary. Sometimes you have 1812 and 1813, and then you could also have 1645 and 1646. So it varies depending on who implemented it. While TACACS is TCP, TACACS uses TCP, and it uses a port of 49. So port 49 is what TACACS uses. Another difference that we can have is Radius doesn't support things like NetBIOS, so there's no NetBIOS support, there's no AppleTalk support, while TACACS has multi-protocol support. So TACACS supports things like NetBIOS, supports AppleTalk, and others. Now, another very important security feature is that Radius only encrypts the password field. So just the password portion of the packet is encrypted, while TACACS encrypts everything. So encrypts the full header, the full packet, except the TACACS header, of course. Another very important difference is that Radius combines the authentication and authorization features. So it combines it into one, while TACACS splits everything. So you have authentication, you have authorization, and then you have accounting. So these are the basic differences between Radius and TACACS. Both of them have their strengths and weaknesses, but when you're doing things like command authorization, because Radius actually combines authentication and authorization, TACACS is better for command authorization. This brings us to the end of this video, where we have looked at AAA configuration using the CCP. We configured some method list on R2. We also saw an introduction to AAA servers, and we saw the two types of AAA servers that we can have, local and remote servers. And we looked at the two basic protocols that are used with remote authentication servers, Radius and TACACS Plus, and we saw their differences. I hope you have found this video informative, and I'd like to thank you for watching. Hi there, and welcome back to this video series on the CCNA security exam, implementing Cisco iOS network security. This is the first video in section 4, which deals with iOS ACLs, that's access control list. In this video, we'll look at an introduction to ACLs, we'll consider the uses of ACLs, we'll consider the types of ACLs, and we'll see how ACLs are processed. Notice that in our lab setup, I have removed the Cisco Secure ACS. That's because we don't need it anymore. Our network diagram still remains the same because R1 and R2 are still on the same LAN. Even though I understand that access control list is a topic on the CCNA routing and switching exam, especially since the CCNA routing and switching is a prerequisite for the CCNA security exam, we'll still cover access control list here, and it will just be like a review for you. So the first question that we need to ask ourselves is, what are access control lists? Why do we need them? And what do they do? So when we see this name, access control, the first thing that comes to our mind is packet filtering. And that is true. Packet filtering is actually one of the features that access control lists are used for. But these days, access control lists are used for so much more. So packet filtering is one. We also use access control lists when we want to specify the host to use for our NAT, as we'll see. NAT is network address translation. Another use of access control list is with routing protocols. So with routing protocols, you can actually use ACLs for summarization. So you have route summarization. That is just one of the features that you can use ACLs with. And we also see use of ACLs with VPNs. So when you want to specify what host would match your VPN tunnel, you can use access lists to specify things like that. And as you can see, the list goes on and on and on. So ACLs are not just used mainly for packet filtering as we had before. They have so many other uses, as we can see from here. However, for this particular video, the focus would be on packet filtering. So we're just going to focus on packet filtering right now while I clear the screen of the other uses. So when we say packet filtering, what do we mean? Let's take a network diagram to explain the concept. So let's just let this be our internet. And then I'm going to draw a particular router connected to the internet, which connects to some host. Now let's also say we have some servers and then some host. So this is a server and this is a particular host. And then this is the internet. Let's say we have some user on the internet somewhere here, outside user. Right, and this is our router. So you understand from this diagram that this is the internal portion of the network. And this side is the external. So when we say packet filtering, what do we mean? Usually you want to protect your internal host or your internal LAN or your internal local area network because that is what is trusted. So it is usually the case where we want that every packet that is going from our internal, or maybe not every packet, but most of the packet going from our internal to the outside should be permitted, while any traffic that is coming from the outside to our host or to our internal network should not be permitted. Now, this is what ACLs can help us do. In this example, from the internal to the outside, there won't be need to filter any packet since we want everything to be permitted, but there will be need to filter coming from the outside going to the internal. So an example is we could place an ACL at this point of the router. As we'll see, there are different positions where you could place the ACL, inbound, outbound. But right now, for this example, we'll say that we could place an ACL here that filters traffic from the outside going to the internal. And as you may be familiar with, ACLs can match traffic based on protocols. They can match traffic based on IP addresses, and they can match traffic based on ports. These are the three basic criteria that ACLs use. So let's talk about the different types of access lists that we can have. Actually, we'll talk about IP access list because access lists can be used not only for IP protocol. We also have access lists for AppleTalk. We have access lists for NetBIOS, for IPX, and others like that. But for this video, we're going to focus on access lists that are IP based. The first type of access list that we're going to consider is the standard. So standard ACLs. Standard ACLs are used to match source IP address. And then if you remember from your CCNA, of course they could be named, but in this case we're considering just their numbers. Their numbers start from 1 to 99. And then the extended range is 1300 to 1999. Actually, that's 1999. So those are your standard ACLs. Standard ACLs, like I said, are used to match source traffic. So if you use standard ACLs to match traffic, it only matches the source IP address in that particular traffic. The second one that we could have is extended. Now, extended is more granular. Actually, it affords more complexity than the standard. So it is used to match both source and destination. But if you are familiar with extended, you know it can do more. It can even match different protocols and then it can also match port numbers. So for example, you can have one matching TCP from a particular source to a particular destination on a particular port. So you could have something like this. So the range for extended, that's the numbered access list, is 199 or from 2000 to 2699. Actually, these numbers are very important if you are going to be using numbered ACL. For me, I prefer to use named ACLs, which is the third one that we're going to consider. So we have the IP named ACLs. So with named ACLs, you don't have to remember that this number goes here. You can actually name your access list with reasonable names. But of course, for your CCNA exam and for knowledge in general, you need to be familiar with what these numbers are. Standard access list 1 to 99, and then the extended range is 1300 to 1999. And then you also have the one for the extended, which is 100 to 199 with an extended range of 2000 to 2699. So like I said before, IP named access lists help you specify names for your access list. So you don't just use numbers. You can use something like in to out ACL. So this way it makes more sense to you to know that, okay, this access list is doing this particular thing or something like that. Throughout this video and the entire video series, these are the access lists that we'll be talking about: standard, extended, and the named. But I also want to briefly discuss some other types of ACLs that we have. So let me just clear the screen right now. So another type of access list that we can have are the time-based access lists. Now, time-based access lists are just normal access lists, but as the name suggests, they are time-based. So they apply only at certain periods of time. So let's say, for example, as a network administrator, you are required to block access to Facebook during working hours, so 9 to 5. So you can actually apply, that's 9 a.m. to 5 p.m. You can actually apply a time-based access list that will only be effective during that particular time. Of course, your clock must be set. That's your device clock, your router clock. Another type of access list that we could have are the reflexive ACLs. Now we have other features that have superseded these ACLs, like CBAC, although CBAC has also been superseded by Cisco iOS Firewall, which we would see. Cisco iOS Firewall, which we would see later. But in summary, what reflexive ACLs help you do is to punch holes in access list. So if, for example, you have this, so you have this host trying to go to this server on the outside. This server is on the outside and this host is on the inside. If you have a deny all placed at that point, what reflexive ACL helps you do is that if this user wants to go to the web server, it punches hole in this deny all for the return traffic. So by default, if the server tries to initiate connection to the host, it won't go, but the returning traffic of the host from the server would be permitted. That's the reflexive ACLs. We just punch holes into that. There are other types of ACLs like turbo ACLs, like dynamic ACLs, but we'll not consider those here. The ones that we're going to focus on for the CCNA security exam are the ones that we saw at first: standard, extended, and named ACLs. Finally, in this video, let's talk about how access lists are processed. This is an example of an extended access list known as test. The first thing you need to understand is that access lists are made up of access control entries. So this is an access control entry, this is another one, this is another one, and this is another one. So each line of an ACL is actually made up of access control entries. Now, as you'll notice, access lists are also made up of permit and deny statements. Now, depending on how the access list is used, permit could mean that the host or whatever traffic is permitted. So for example, in this case, TCP from host 10.1.1.5 to host 3.3 for port telnet is permitted. And deny could mean that whatever is matched in that ACE is denied. But this is for packet filtering. It may not be the case if you use something like route maps, for example. But for packet filtering that we'll be considering, permit means that traffic will be permitted, while deny means it will be denied. Something else that we need to know is that for every new ACE that you type, so for every new entry that you type into your access list, it will be placed at the end of the line. So if after this access list is done, you place some other permit statements, the next permit statement will be here, the next one after that will be here, and things like that. However, there are some times when these statements may have line numbers. So you could place something between their line numbers. So if you have entries 10, 20, 30, if you want to place something here, you could just create an entry with line number 15, for example. Another important factor that we need to know is that every access list has an implicit deny all at the end. So it may not be shown, but it's implicit. That's why it's called implicit. It's not explicit. It's not explicitly stated, but every access list has an implicit deny all at the end of that access list. This is very important because if traffic comes into a particular interface that you have this access list applied to, if that traffic doesn't match any of this, it's going to match the deny all and it's probably going to be denied. If that's what you want, then fine. If that's not what you want, then you can override this deny all by doing something like permit all. So you can permit IP any, for example. If you're going to do a permit IP any, then you probably have an ACL that has deny statements before this permit IP any. Now let me just clear the screen of all this scribble. So how are access lists processed? They're processed from top to bottom. So this statement will be matched first, or rather traffic will be matched against this statement before it is matched against this, before it is matched against this, before it is matched against this, and finally the deny all. So what does this tell you? It means that you should put your more specific statement at the top. Looking at this example, for instance, this statement is more specific because it matches a particular host and a particular host on a particular port. That is fine. But now if you come down, you see this permit statement and it permits all the hosts on this subnet to this particular host 3.3.3. Now you need to understand that TCP is an IP protocol. So this statement is in fact not needed, except you want to do some logging. Because what it says is that if you have already permitted IP in this list, it means that this TCP is basically useless. Meaning that if what you wanted is for TCP to be permitted to that particular host from this host, then it is already matched in this statement, since IP covers TCP, ICMP, and UDP. Now, something else that we need to note here is the deny. Now, you notice that this deny is for that subnet to that host on port 80, which is www. But like I said, TCP is already part of the IP protocol. That means this statement will never be matched because you've already permitted all the subnets on the IP to go to that host. That means TCP would never be matched. So this statement would never get to this statement. That means you must have placed your deny statement above this permit statement. Now looking at this last entry, it goes from host actually there shouldn't be host here. So it goes from this subnet 10.1.1.0, this subnet, and it goes to this particular subnet. Now it doesn't match anything before it. So this would work. And then every other traffic that doesn't match any of these statements will go to your deny. So you need to actually plan your access control list because like we saw, these deny statements will never be matched because of the permits that you have here. And we saw that this one is irrelevant except you are doing login because it's already matched here. So things that you need to concern yourself with are your deny statements, your permit statements, and also your specificity. So how specific is that ACE and where should you place it? This brings us to an end of this video where we have looked at an introduction to ACLs. It should have actually been like a review for you if you've already done the CCNA routing and switching exam. So we looked at different uses of ACLs, we looked at the types of ACLs, and we saw how ACLs are processed. I hope you have found this video informative and I'd like to thank you for watching. Hi there and welcome back to this video series on the CCNA security exam, implementing Cisco IRS network security. This is the second video in section 4, which deals with IRS ACLs. In this video, we'll learn about wildcard mask and network summarization. These are two concepts that we need to understand to fully implement ACLs. For many of you that are familiar with access lists, you know that there's this concept of wildcard mask. So for example, if you want to match traffic of this network or subnet, say 10.0/24. Now you know that wildcard mask is just like the inverse of subnet mask. It's also called inverse mask actually. So remember that /24 is 255.255.255.0. So the wildcard mask of 24 will be 0.0.0.255. If you are dealing with a single network and you want to convert that subnet mask to wildcard mask, the easiest way is just to subtract from 255. So you subtract every portion of that particular subnet mask from 255. So 255. If I do the subtraction right now, 255 and 255 is 0, 255, 255, 0, 0, and then this is 255. So let's take /25 for example. /25 is the same thing, but it's 128. So 255 minus 128 should give you 127. So your wildcard will be 0.0.0.127. We can take another one, /29. /29 is 255.255.255.248. That's like three bits difference. Right. So if you want to do this, it will be 0. The wildcard will be 0, 0, 0, and then 255 in this would be 7. So this is the wildcard mask for a /29 network. So let's take a real example. I'm going to clear this screen right now and then we'll come up with something else. So let's say in this example, we want to permit TCP from this network 168.10.0/30 to a host 10.1.1.10. Now, I'm not really particular about how the command is going to look on the Cisco IRS. I just want to drive home the point of wildcard mask. So it's /30, which is 255, that's the subnet, 255.255.255, /30 is 252. So the wildcard would be 255 minus 252 is going to be 3. So wildcard is going to be 0.0.0.3, right? So your statement will be something like permit TCP from 192.168.10.0. Now it will be this. So this part actually represents your wildcard mask to host 10.1.1.10. So what does this actually tell you about wildcard? It means that 0, so anywhere that you see 0 means that it must match, while a 1 means that it doesn't care. 1 is don't care. Now let me explain what I mean by that. 0 here is 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. This is 1, 2, 3, 4, 5, 6, 7, 8. This is 1, 2, 3, 4, 5, 6, 7, 8. And this is 1, 2, 3, 4, 5, 6, 1, 1. Right? So it means if we use this wildcard mask, everything that has a 0 under it, so you know that this IP address can also be converted to binary. So everything, so in this case, 192 must match, 168 must match, 10 must match. Now, this first 6 bits must match, but these other ones can be varied. That means I can have 00, 01, 10, and 11. This is 0, 1, 2, 3. So in essence, this access list is going to match anything that has 192.168.10.0, 10.1, 10.2, and 10.3. These are the addresses that is going to match. The reason I'm trying to point out this is because the router actually thinks in binary, 0 and 1. So all this 192.168 is just for our own benefit. The router is going to split everything down into binary. So when it gets any traffic and then gets the IP address, it's going to split the IP address and its subnet mask down into 0s and 1s, and then compare it to any access list that you have with your wildcard. Now, these 0s and 1 will become very useful in the next section when we consider summarization. So just keep this in mind. Let's talk about network summarization, that's network address summarization. Let's imagine that you're the administrator of a network, and then on your network you have subnets like 8.0/24. You have 192.168.9.0. So all of them are going to be from 168, then this is 10.0, and then finally you have 11.0. Now, if you want to use access lists, like you want to configure access list, let's say you have a server and that server IP address is say 172.168.1.1 for example, /32. This is just an example. So what if you want to write an access list to limit, so you want to block all this traffic from going to this place? How are you going to do this? Of course, one way is for you to write each statement. So you write each network 192.168.8.0, and then you block it for this, and then you write for 9, you write for 10, you write for 11. So in that case, you have 4 entries in that ACL. But imagine if this network is not just 4. Let's assume you had like 16 or something more than that. Would you be writing each one of them? There's an easier way, and it's called network summarization. Now, to understand network summarization, you have to think in binary. Since everything is /24, it works for you. We don't really need to consider what the subnet would be. But what are we going to write in our wildcard mask to match 8, 9, 10? Now, we know that 192.168 will be the same. So we already know that this will be 0, this will be 0. And then if we're matching a network, this will be 0. But if we're matching a host, it will be 255. So right now, let's just leave it at 255. So we need to solve what this would be. 8 would be 0, 0, 0, 0. That's 1, 0, 0, 0. 9 would be 0, 0, 0, 0, 1, 0, 0, 1. 10 would be 0, 0, 0, 0, 1, 0, 1, 0. And then 11 would be 0, 0, 0, 0, 1, 0, 1, 1. Now, if you remember from wildcards, we said 0 means that it must match, and 1 means that I don't care. Now, if you look at all this, what is similar to them? So this is just like some LCM or HCF, if you remember any of those things from mathematics. You'll notice that all this from here to here are similar, but these are the things that change. So it means that all this must match. That means it must be zeros for the wildcard mask, while this can change. This can be varied. So in essence, what I'm trying to say is your wildcard will be 0, 0, 0, 0, 0, 0, 1, 1. Right. So this 1, 1 means this bit can vary, this bit can vary, but it means that all these other bits cannot vary. So in essence, our wildcard mask would be 0 dot 0 dot, this would be 3 dot whatever we're matching. So in this case, it would be 255 if we're matching host. So it means that this wildcard mask covers 192.168.8, it covers .9, covers .10, and covers .11. So if I clear the screen right now, so it means that I can write an access list that has something like 192.168.8.0 and then 0.0.3.255, and it's going to cover all the hosts that are in this network. But something that you must remember is that you must be careful not to overmatch or something in that line. And how do you know if you've overmatched? So if you remember, we said .3. So .3 would be 0.0.0.0.0.0.1.1. So we're varying these 2 bits. So if you vary 2 bits, 2 raised to power 2 is 4. So these 2 bits would match 4 addresses. And if you count, we have 8, 9, 10, 11. So it's 4. Now imagine if 11 wasn't there. Let's write this again. So 8 would be 1, 2, 3, 4, 1, 0, 0, 0. 9 would be 0, 0, 0, 0, 1, 0, 0, 1. 10 would be 0, 0, 0, 0, 1, 0, 1, 0. So in this case, you still see that we have the same number of bits that are matched, and the things that we want to vary are 2. So we'll still use the same wildcard mask of 192.168.8.0 and then to be 0.0.3.255. But what we've done right now is that we have added .11. So anybody that has an IP address in .11 would also be matched in this access list. One thing that you could do is to put a deny statement for the 11 above. So you could put something like deny and then deny 11 before this permit, so that it denies that traffic from being matched. Of course, if you wanted to deny this host, then this would be deny and this would be permit, depending on what you want to do. Let's take another example. Say you want to match 192.168.24.0 and .25.0. Remember, what you need to do is write it out in binary. So 24 will be 0.0.0.1.1.0.0.0, and 25 would be 0.0.1.1.0.0.1. Right. So look at the portion that matches. You have this, So that means your wildcard here would, everything has to match. So you put zeros here. Now this would vary 1. Now you have to check, does it perfectly fit? So 2 raised to power 1 will be 2. And then you have 2 addresses. So it fits perfectly. So our wildcard bits, starting from the first one, will be 0, dot, 0, dot. Now this will be 1. And then if we're matching hosts, it will be 255. So if I want to write the entire statement, it will be 192.168.24.0, and then this will be the wildcard portion. Now you may be wondering how I know what to write here. You just have to write the part that is similar. So if we look at this now, the part that is similar is this 1, 2, 3, 4, 5, 6, something, and then so it will be 0, 0, 0, 1, 1, 0, 0, and then of course you fill it up to the end, and this is 24. So that's how I know what to write here. Now let's take one more example before we wrap this up. So if you have 10.1.say50.0, you have 10.1.51.0, and finally you have 10.1.52.0. So let's break it down. 50 in binary is 0, 128, 64, 32, 16, 0, 0, 1, 0. Okay, 51 would be 1, 2, 1, 1, 0, 0, 1, 1. 52 would be 1, 2, 1, 1, 0, 1, 0, 0. Right? So this is 32, 16, 48 plus 4. Yeah, 52. So that's fine. So now if you look at it, the parts that match here are this part, and then you have 1, 2, 3 bits to vary. 2 raised to power 3 bits to vary will be 8, but you have only 3 addresses to match, so that's too much. Of course, you can always write a mask that will still use this 3 bits, but then you have to deny some statements. A better way could be to break things down. So if you look at 51 and 52, the ones that match, only 1 bit varies, which is this one, and 2 raised to power 1 is 2, so it will match 50 and 51 perfectly, and then you can write 52 in another statement. So basically what I'm saying is you can write something like 10.1.50.0, 0.0.1.255. So this statement would match 50 and 51, and then you can write 52 on its own, 1.52.0, 0.0.0.255, sorry, and this would match 52. So you have to be careful, like I said, not to overmatch, as we saw in this example. There are 2 very good resources that I'll advise you to go through for access list. If I search right now for Cisco access list, notice you have this configuring IP access list is the first that comes out. This resource is actually very good. As you can see, it gives you types of access list, it gives you the mask, gives you summarization. Let's go to summarization. You notice that everything I've talked about, the mask, the summarization, you also see different examples. So I think this resource is actually very good for you, and how ACLs are processed. You go down, you see different types of access list. Another one that is very good is if we search on binary maths INE. It has a part 1 and a part 2. So this was actually written on the INE blog. So if you open both of them, well, for its CCIE level, so you may not need the part 2, but the part 1 is actually very useful. And then you can see everything that we've talked about, 31, 32, and you can see how everything is broken down into binary. No, it's not really for CCNA level knowledge, but it's for knowledge in general. As a network administrator, this would be very good for you to know. This brings us to the end of this video, where we have looked at wildcard mask. As we have seen, wildcard mask is just the inverse of the subnet mask. And then we have also looked at network summarization, so that we can reduce the number of entries in our access lists. I hope you have found this video helpful, and I'd like to thank you for watching. Hi there, and welcome back to this video series on the CCNA security exam, implementing Cisco iOS network security. This is the 3rd video in section 4, where we cover iOS ACLs. In this video, we'll look at an implementation of access control list, We'll also see where to place access lists as close to the source or as close to the destination as possible, and we'll answer the question inbound or outbound. Before we go to the command line, let's look at our lab setup. This is the lab setup that we currently have. So right now, let's add some loopback addresses so that we can simulate our ACLs properly. I'll add loopback 10 here and loopback 11. The IP addresses will be in the subnet 192.168.10.0/24. The IP address itself will be .1, while this will be 192.168.11.0/24, also .1. On R1, we'll put a loopback 8. This will be 192.168.8.0/24, and we'll also have a loopback 9. This will be 192.168.9.0/24. So let's quickly make the changes that we said. We're going to create loopback 8, IP address 192.168.8.1.255.255.255.0. We'll also do interface loopback 9. The IP address would be 9.1. Remember that we need to add it to EIGRP so that R2 will be able to get to it. So network 192.168.8.0 and .9.0. What happened? .9.0. I'll come to R2 and do interface loopback 10. The IP address is going to be 192.168.10.1.255.255.255.0, and then loopback 11. This would be 11, and then we'll also need to put it into EIGRP network 192.168.10.0 and 11.0. Cool. Let's check our routing table. So we have 8 and 9. If I try to ping 192.168.8.1, I have connection. 9.1, I have connection. If I go to R2, let's do a show IP route. If I try to ping 192.168.10.1 and .11.1. Cool, so we have connection. Before we continue, there are a couple of things that you need to consider when you're dealing with ACLs. The first one is that your access control list, so your ACLs, should match your security policy. So don't just go around configuring ACLs and denying and permitting, even though that's, as network administrators, we're always tempted to do things like that. But your ACL should actually be configured based on your security policy. So your security policy may say that some users in a particular subnet should not be able to connect to a particular server, or some users should not be able to connect to the internet at a particular time. So you configure your ACLs based on those kind of directives. To illustrate the second thing that we need to consider, we'll go over to a whiteboard. The second thing that we need to consider is the placement. So where should you place your ACL? Now, it's always either as close to source as possible or as close to destination as possible. Now, let's imagine that you have these users on LAN A and you want to restrict their connection to LAN B. So you want this to be blocked. Now, if you are using a standard ACL, remember that standard ACLs match just based on the source. So they match based on the source IP address. So if you apply your standard ACL here, what you are doing is you are not only blocking these users from accessing this server, you are also blocking them from reaching LAN B. So with standard ACLs, you apply your ACLs as close to destination as possible. Destination as close to destination as possible. So a better place to apply your standard ACL would be here. In this way, LAN A user will still be able to get to LAN B users. But if we're dealing with extended, as we're dealing with extended ACLs, remember that extended, you can match both source and destination. So if you're dealing with extended ACLs, you can actually apply your ACL here without any adverse effect on LAN B, because you match their source address and you also match the destination address of the server. So the ACL will not match any address on LAN B. So just a recap. if you are using standard ACLs, you place your ACLs as close to the destination as possible. But if you are using extended ACLs, you place your ACL as close to the source of the traffic as possible. So let's assume that we have this security policy. For example, this is just a part of our security policy that details access control. So it says that host on the 192.168.8.0/24, that's the loopback 8 of R1, should not be able to access any network on R2. So they should not be able to access any network at all, loopback 0, loopback 10, loopback 11. However, the host 192.168.8.8 should have access unhindered. So that means a host in this particular group should have access unhindered. And finally, we have that all the hosts on 192.168.9.0, that's loopback 9 of R1, should not be able to access any host on the 192.168.10 subnet. However, they can access the web servers that are on that network. So let's do our config on R2. The first statement on the security policy says that everybody in the 192.168.8.0/24 network should not be able to access any network on R2. Now, standard ACLs will have been very, very wonderful here if that's the only statement that we have. But let's look at it. Access list. So if you notice, these are the numbers that we talked about, 1 to 99. That's for standard ACL. For the extended ACL, you have 100 to 199. Then you have their expanded ranges, 13, and then the 2000 to 269. You can also have access lists for other protocols, IPX. This is AppleTalk. You can have some for NetBIOS and things like that. But I just wanted to show you that throughout this video, we're going to use named access list. So to use named access list, use the IP in front of access list. And you can see you have to specify whether it's extended or it's standard. So if I want to use standard, so I can give it, of course, you can still reference the number if you want, but then now you have the option of using the name. So here, I'm just going to say deny 8.4 and then enter. Now here you have your sequence numbers. Sequence number helps you place access lists. Like if you remember, I said if you have an access list that has entries in 10, 20, 30, and you want to place something between 10 and 20, yeah, this is what the sequence number will help you do. But for now, we'll just focus on the deny and the permit statements. So one thing that we could do is to deny 192. Now let me just show you what we have. So you can either match a host name, you can match any source, or you can match a particular like single host. If you want to match single host, you use the host command and you specify the IP address. But right now I want to match an entire network, 192.168.8.0, and then remember here we have to specify the wildcard bit, which will be 0.0.0.255. Now, if you apply this access list on the interface of R2, assuming that you want to place it on the FA00 of R2, you've effectively blocked every other traffic. Remember, there's an implicit deny all in every access list. So since you only want to deny this, you actually have to permit any. So what it's going to do right now, if we look at the ACL, so let's do a show run. I can just do section access list. So this is the access list that we have. So it's going to match this first, going to match traffic against this first, and then every other traffic is going to be permitted because of this permit any. If we didn't place this permit any there, we'll have effectively blocked every traffic. So the fact is we can't actually use this access list because you are only allowed one access list in either direction on an interface. And since we have other entries in our security policy, a better access list to use would be the extended. I just wanted to show you how to configure the standard access list. So I'll exit out of here. And now we'll create an access list, extended. Now let's give it a name. Let's say security policy 01. Of course, this doesn't really make sense, but for now that will do. So the first thing says that we should deny. Now let's look at the options that we have. Now notice that with this, you have protocols that you can deny. And we want to deny everything. So we deny the entire IP from a particular source address. So let's say 192.168.8.0, and then we use our wildcard 0.0.0.255, and we want to deny it to any destination on R2. So I can just say any. I can specify all the IP addresses on R2, but in case we add other loopbacks, I want this access list to be able to apply. Look at the options that we have. We can log, we can fragment, log impute, but for now, we're just fine with this. The second entry in our security policy says that we should permit host 192.168.8.8 unhindered. Now, if I do this, permit IP 192, I can specify the host 192.168.8.8 any. This entry will never be logged. The reason is that 192.168.8.8 is already part of 192.168.8.0, and since this is above, this will be processed before this. Now there are ways to go about it. It's either I remove this deny statement, add this first, and then add this, or I do a show run. No, actually I just do a show access list. Now notice this, the entry is 10, so I can place something above 10. So what I can do is I'll remove this one, and then I can put a sequence number, and then I can configure everything I just did. So now let's look at our access list again. You can notice now that the permit has come above the deny. So this is the use of the sequence numbers that we saw. Now let's move on. Our next policy says that hosts on the 192.168.9.0 network should not be able to access anybody on the 192.168.10 network. However, they can access the web servers in that network. So let's not make the same mistake that we made again. Let's configure the however part first. So what we could do is to permit. So it's www, that's web server, that's port 80, that's TCP. So permit TCP from 192.168.9.0 using 255, and then to 192.168.10.0 255. Now notice what we could have with TCP. The one that we're concerned with is this equal to. So this equal to matches packets that are only on a given port. You also have greater than. So you have packets with greater, like a port that is greater than. But for now, AQ would work for us. And then you can see the different ports that we have. There's FTP, there's Echo, but the one that we're concerned with is www. You can actually just specify the port number like this in case it's not listed. For example, SSH is not listed, but you could just specify 22 and then it will work. So now that we've done our permit, we can do our deny. So we're denying IP from that entire network 9.0.0.0.0.255 going to 192.168.10.0.0.0.255. Now let's look at our access list again. So we have our access list SPO1, the first permit, then a deny, then we have another permit and another deny. Now you need to know that there's a deny all, so there's a deny any after this. So because of the deny any, even traffic from 192.168.9.0 to 11 will be blocked. And if I don't want that to happen, I could just put permit IP any at the end, or I could be more specific. But since our security policy states only those things, I'm just going to permit IP any. Now if you look at it, yeah, so any other traffic that doesn't match this first four will be permitted. Now we have done one part. If you just configure an access list and you don't apply it, then the access list is not being used in any way. So we need to apply this on our interfaces. Now we need to decide what interface to apply it on. Since traffic is going to be coming from R1 into R2, we'll apply it on FA00. That's the connection between R1 and R2. And I can apply it access group, specify the name. Let me just complete this access group. Specify the name SPO1. Now, in which direction am I going to apply it? Inbound or outbound? Let's stop here and go to the whiteboard for the explanation. Sometimes it may get confusing in what direction to apply an access list, but let this help you. Think of this like, okay, you have a router and you have interfaces FA01 and FA00. Now you can think of these interfaces like doors. So this is door 1 and this is door 2. Now think about it. If traffic is coming in this direction, if you look at FA00, Traffic coming in this direction is coming into FA00. So it's coming into the router. So the traffic is going to go through the router and then it's going to come out of FA1. So in this direction, this is out and this is in. So any traffic here is inbound FA00 and then is outbound FA01. Now if traffic is coming in this direction, it goes in through FA00, so that is inbound in this direction. But if it's going out this way, it's going out, so it will go through the router, get processed by the router, and go out through this door, which is FA00, and that is outbound direction. So the router is your reference point and the source of the traffic. So if the traffic is coming in this direction, then you know it's going into the router and then it's going out of the router, depending on what interface you are considering. So if we look at our lab setup, traffic coming from R1 is going inbound FA00 to get to the destination. So we can apply this access list inbound. And that's all. So let's just check our config, section access list. So we have our access list, and then if we check a show run on our interfaces, we can see that we have our access group applied. Now when you do an access list, of course, it's always better to test. So let's test this one by one. Permit IP host 192.168.8.8 any, but right now we don't have any 8.8. We'll have one later. Let's test this deny first. So let's come to R1. R1 is the source that has, so if I do a show IP interface brief, the loopback 8 is the one that has the 8.1. So if I try to ping, let's say I try to ping 2.2, since it's any, it should work. And then I use a particular source. So my source will be loopback 8. Now you notice that it says what? Unreachable. That means the packets are being dropped. And then if we check our access list on R2, notice we have matches. So it's actually denying it based on that. Now let's go to the next one. We want to test 9 going to 10 on www. We can simulate this using telnet, and I think let's check. I think our HTTP server is running. Section. So our HTTP server is running, so it should respond. So if I go to R1 and try to telnet from, or telnet to 192.168.10.1, and I can specify a source interface. I think it's /source, yeah, /source, and then it's going to be our loopback 9. We just tested the last statement. Actually, we should have specified what port we're going to, and you can see that it's open. So I'll just exit out of here, go to R2, see our access list again. So you notice this permits on the WW 7 matches, and then the first one that we did, which was the normal telnet, got denied. And then you can see we already have some permits IP any of some other traffic that are not going. Now let's test this one. We haven't tested this 192.8.8.8. What I'll just do is I'll change the loopback of that is going to be .8. I'm going to change it to 192.168.8.8. 255.255.255.0. Now if I try to ping, it goes. So if you check here, you can see the match. Cool, so we've tested every statement in our access list, and then things are still being matched by the permit IP any. This brings us to the end of this video, where we have implemented and tested our ACLs based on a security policy. We have also seen where to place ACLs, and we have answered the question of whether inbound or outbound direction. I hope you have found this video informative, and I'd like to thank you for watching. Hi there, and welcome back to this video on the CCNA security exam implementing Cisco IRS network security. This is the third video in the section 1 of common security threats. In this video, we would go through risk assessment and analysis, dealing with risk, designing a secure network, and finally, we will consider security policies and documents. Risk assessment and analysis. In the previous video, we considered different types of classification: asset, threats, and we also saw countermeasures, or otherwise called controls. Now, how do all these things tie up? What do organizations use them for? It's all about a risk assessment. When you have identified your asset, let's say you have identified a server as your asset, and you have determined that that server has a vulnerability. Let's assume this is the vulnerability. And you have also discovered that there's a threat, a malicious threat that can exploit this vulnerability, for example. So this is the threat. Now, risk assessment helps you know that if this threat succeeds in exploiting this vulnerability on this particular asset, what would be the business impact to the organization? Now, if, for example, if it's like a financial software and it's a financial organization, if that software becomes compromised, then the organization will probably not be able to function. That is what risk assessment does for you. There are two methods for risk assessment. The first is quantitative, which uses monetary values, monetary terms. In this case, you could have something like the asset cost me $2,000. The control to protect this asset cost $500. If this asset is compromised, the business impact on the organization would be $10,000. It means that you can actually implement this control to protect this asset, because not doing so would mean you stand a greater risk should a threat exploit the vulnerability. The second one is qualitative risk analysis, which, like the name suggests, it doesn't use monetary values. It just uses different terms that are important to an organization, for example. Now, moving on, how do organizations deal with risk? The first one is to transfer it. So when you take an insurance, for example, it means you are transferring the risk to another party. So you have one party A, you have another party B, and A transfers the risk to B. So the first method is transfer. Now the second one is to avoid it completely. If it has been determined that Facebook is susceptible to spreading viruses, you could choose to block Facebook entirely and not allow your staff to go on Facebook. Thus, you are avoiding the risk completely. The next method is to reduce it. In this case, you are implementing a countermeasure to deal with the risk. This could be putting a firewall in your network to protect your servers, for example. And finally, we have accepting the risk. You know the myth that an ostrich puts its head in the ground during an attack. Yeah, that's basically what accepting the risk is. It means you understand the risk, you know how much it takes to implement a countermeasure, but you just are not going to implement a countermeasure. An example of this would be if you have determined that the cost to implement a countermeasure exceeds the business impact on the organization. For example, if it costs $5,000 and then the business impact, if that asset goes down, is what, $2,000, you probably will just accept the risk. Now let's consider how we design a secure network. You need to understand that security is not a product, it's more of a process. So it doesn't actually, you never come to an end of it. So we could have something like a secure network lifecycle, and it consists of 5 phases. The first is the initiation, the second is the acquisition and development, the third is the implementation, next one is operations and management, and finally we have disposition. Of course, it also goes round again. So it's like a never-ending process. Initiation is the beginning. In this phase, you consider things like risk assessment, which we have discussed in the previous slides. And then next, we go to acquisition and development. Here, you acquire controls and countermeasures to help in your security implementation. And in the implementation phase, you actually put to use the controls that you have acquired and developed. We move on to operations and maintenance, which has to do with the day-to-day running of your security controls. And finally, we move on to disposition. Security products actually come to end of life where they are no more useful, and then you need to replace them with updated security features or another product entirely. This is the secure network lifecycle. There are some principles to consider when you're designing security. The first of which would be defense in depth. Now, what does defense in depth mean? It just means a layered approach to things. So if you have a very important asset, you would have a countermeasure, you'd have another countermeasure, you'd have another countermeasure around it, just like a shell or like layers of an onion. This is what this diagram here is showing. Let's take an example. The vault in the bank is not placed where everybody knows. It's inside a room which probably has like a steel door, and to get to that room you need like an access code, and to get to that door that has the access code you probably need to have passed through security. So this is an example of defense in depth. The next is the rule of least privilege. Here you only make available what is necessary to perform like a particular goal. For example, someone who does not need access to your databases should be restricted. For the rule of least privilege to work, you should start with a deny all, and then from there you can go up and start giving access to only what is required. The next principle that we'll consider is the separation of duties. Basically, it just means that no one should have complete control over everything. You may have noticed that in the banks, if you want to collect money over the counter that is above a certain amount, 2 people have to sign off on it: the bank customer assistant who attended to you and probably her manager. This is the separation of duties. Nobody has complete control over something. Now, let's consider some documents in security. The first of which will be the security policy. A security policy is a high-level document produced by senior management dictating how security fits into the goals of the organization. Under this policy, you probably have things like the acceptable use policy document, you have things like the email policy document, you have like the network access policy and other things like that. We also have standards. Standards are mandatory activities that must be performed. Since the policy is usually high level, standards help elaborate on them. For example, a policy could state that all company staff must be appropriately identified at all times. The standard would then be the HR must issue ID cards to all staff, which must be worn at all times. That's the relationship between standards and security policies. Next on the list that we'll consider is baseline. A baseline is a minimum level of protection that is required. For example, a baseline could be that all computers in an organization must be running at least a version of Windows 7 and nothing lower. The next that we have are guidelines. Now, guidelines are recommended activities. They are leading you in a recommended direction. They are helpful when standards for a particular activity are not available. And finally, we have procedures. Now, a procedure is a detailed set of instructions about how to achieve a specific goal. For example, there could be a procedure for formatting any computer in an organization. First of all, you probably have what? Back up the data. Then you have format the system. Then you probably have something like install applications or reinstall applications. And finally, you probably want to restore the data, something like that. Yes, so this is how procedures, these are what procedures tell you. They give you like a detailed instruction of how to achieve a specific goal. This brings us to an end of this video where we have seen risk analysis and assessment. We saw the 2 types of risk analysis method. The first one is quantitative and the second one is qualitative. We also saw how organizations can deal with risk. They can either transfer it, they can accept it, they can avoid it, or they can reduce it. We saw the network life cycle of initiation and disposition and things like that. And finally, we looked at the different types of security documents, things like guidelines, procedures, baselines, and others. I hope you have found this video informative, and I look forward to seeing you in the next one. Thank you.
Hi there, and welcome back to this video series on the CCNA security exam, implementing Cisco iOS network security. This is the first video in section 7, which deals with Cisco firewall technologies. In this video,
we'll look at an introduction to firewalls. We'll also look at the different types of firewall technologies, their strengths and their weaknesses. You'll notice that we're back to our former lab setup. On one end, organizations want to make their networks available. For example, they want to have an online presence. On the other end, they want to make their networks as secure as possible from unauthorized access. So we could have something like this, and this is security, and this is availability. Now, the whole concept is to gain a balance between security and availability. So if you are going to be available, you are going to be not so secure, and if you are going to be secure, you are going to be not so available. So the point is creating a balance between availability and security, maybe somewhere at this point. So the extreme form of availability is when there's no form of security at all. So you just have an open access to the entire public. On the other hand, an extreme form of security would be like a complete lockdown where nobody has access to your resources. But thankfully, we have these things called firewalls that help us create a balance between availability and security. Let me clear this screen. So normally you have your organization. Let's just draw this as an organization. And you also have, for example, the internet. That's like the public network. So internet. Now the point is to connect your organization to the internet. But just allowing this connection means that it's the open access, which allows everybody access to all your resources, which is basically no security. But with firewalls, you can place a firewall here that is going to control access between the different domains. So for example, this is your trusted domain, your internal network is your trusted domain, and this is your untrusted domain. And that is what a firewall does. A firewall basically provides access control between security domains. So for example, between the trusted and the untrusted. Now, of course, usually you're going to have allow access from the trusted to the untrusted. This is going to be allowed, but access from the untrusted to the trusted will be denied. This is what firewalls, this is the basic concept of firewalls. They provide access control between security domains. From this, it is immediately evident what the features of a good firewall are. So features of a good firewall or features of a good firewall deployment. Let me just clear the screen up a little bit. The first thing is the firewall must be the only point of access into that network. So for example, if you have another link going to the internet, then this is not a good firewall deployment, because an attacker can effectively use the path of least resistance to get to your network, and then your firewall will not be the only thing on the paths to get to your network. So that's one. So the second one is that the firewall itself must be hardened. So it must be hardened to security attacks. That means, for example, a denial of service should not be able to bring down this firewall. There are different types of firewall technologies, including the stateless. So this is the oldest one. The stateless packet filtering. We also have the proxy servers, also called the ALG. That's application layer gateway. We also have the stateful packet filtering. So that's stateful. The first one is stateless, while the other one is stateful packet filtering. And we also have, so the fourth one is going to be application inspection. Application inspection. We're going to look at these firewalls in details, one after the other, and we'll look at the benefits and advantages and disadvantages of each one of them. The first firewall technology that we're going to talk about is the stateless packet filtering. It's basically the oldest. It's the oldest type of firewall technology, and it makes decisions based on the layer 3. That's things like IP address. So you have like IP address, and layer 4. So layer 4 would be things like TCP port numbers, for example. We have already seen an example of this with the ACLs when we configured access control list on the routers. Now you should understand that stateless, as the name says, does not keep track of state. So what does this mean? Let's take an example. If you have a firewall and you have this user going to this user, so let's say this is inside and this user is on the outside. Now if, for example, this inside user opens a connection to the outside user, now remember that a connection will be made up of several packets. Now with the stateless packet filtering, since it does not keep state, even if these packets are of the same connection, it treats them as individuals, so it treats them independently. Therefore, it's not able to determine that a packet is part of an existing flow or is part of a new flow. Now let's talk about the strengths and weakness of this. I'm just going to clear up the screen. Now one of the strengths, so just write strengths here. One of the strengths is that it is very simple to implement. As we saw with ACLs, you can easily write permit and deny statements. Another thing is that it has low processing impact. As we saw, we implemented it on routers and you can even implement it on switches. And finally, it is cost efficient. So you do not need a particular dedicated hardware appliance. Like we saw, you can also implement it on routers or something. Now let's talk about the weaknesses. Now, of course, the first weakness that we have is that it is stateless, meaning that it's not intelligent. It's not able to determine that a packet is part of an existing flow or is part of a new flow. Another weakness is that it is susceptible to IP spoofing attacks. So we know that even though this stateless packet filtering gives us basic packet filtering capabilities, which is nice because it's not so processor intensive, we cannot really use this firewall technology because it doesn't meet the needs of today's demands. The next one that we're going to consider are the proxy servers, also called the application layer gateway, ALG. Let's take, for example, we have this firewall. It's a proxy server. So proxy server, and then you have like a server on the outside and you have a client here. Now with the proxy server, connection is not actually made from the end user. So let's just call this the end user to the server. This is how the connection flows. The end user opens a connection to the end server, which is intercepted by the proxy server. And the proxy server opens a connection to the server. Now the server thinks it's talking to the proxy server, so the reply is made to the proxy server, and then the proxy server replies to the end user. So in this way, the end user is kind of protected. So you have some level of protection when you're using the proxy server. The proxy server can operate between layers 3 and 7. And because of this, so because it gets up to the application layer, it can be very, very granular. So let's talk about the strengths and the weaknesses. So here we'll talk about strength. Like I mentioned before, the first strength is that because it can get up to layer 7, it is very granular. Also, with proxy server, you can have very, very detailed logging. So it can tell you that this user tried to get to this particular server and this particular request was denied and things like that. And like I mentioned, you have protection for your end users because the connection is not actually between the end users and the servers. It's actually between the proxy server and whatever server they are trying to connect to. Now we can talk about the weaknesses. And the first one is that the proxy server is software based. And since it's software based, it is very processor intensive. Software based, so it's processor intensive. Now the second thing, or the second weakness that we can have, is that you may require a special client to be used on your end users. Special client may be required. And lastly, The third weakness that we may have is that not all applications may be supported. Now this is because the proxy server needs to know how to deal with different apps. So not all applications may be supported. This is the third type of firewall technology that we could talk about. That's the stateful packet filtering. So it's just like the packet filtering, like this, but then it's stateful. Now what does stateful mean? Also, you should keep in mind that this is one of the most used firewall technologies. So stateful means that it can determine if a packet is part of a new connection or part of an existing connection. Now, why is this important? I'll show you with a diagram. So if you have a firewall like this, and you had these internal users, and you had these external users. Now let's say on this edge of the firewall there's a deny all. It means that everybody from here cannot, so let's say this is the outside and this is the inside. So what it means that everybody from the outside cannot go to the inside. That's denied. Now when the inside tries to connect to the outside and this outside user tries to reply, by default, because of this deny, the packet is going to be dropped. But with the stateful packet filtering, it's able to automatically permit return traffic. That's because it keeps track of the state. So it keeps information like the source and destination ports and IP address and other information about the packet in a state table. So this is the state table that it uses. So for example, we could have something like source IP address, destination IP address, source port, destination port, and then you can have some other information like that. Now let's talk about the strengths and weaknesses of this firewall technology. So strengths, and the first strength is that the state table provides intelligence. So because of the state table, it is intelligent because it can determine if a packet is part of a new connection or part of an existing connection. Now it also provides protection against spoofing and denial of service. And this is still because of the state table that it keeps. Spoofing and denial of service attacks. Another advantage is that it can be used as a first line of defense, and it is actually being used as a first line of defense in several organizations. Now we can talk about the weaknesses, and one of the weaknesses is inherent in the packet filtering, the fact that it operates in layer 3 and layer 4. That means it may not be able to protect against application layer attacks. So that's because it does not go all the way to layer 7. Another weakness is that not all protocols are stateful. So you have protocols like ICMP and UDP. So for example, you have ICMP, which is not stateful, and then you have UDP. A third weakness is that it cannot provide user authentication. But like I said before, the stateful packet filtering is one of the most used firewall technologies. As we'll see, it can also be used with the application inspection. The final firewall technology that we're going to talk about is the application inspection. Stateful packet filtering firewalls can implement application inspections so as to see into the application layer information. Now these are similar to proxy servers because they operate at layer 7, thus they can see into layer 7, but unlike the proxy servers, they do not initiate and terminate connections for users. Application layer inspection is also called deep packet inspection. So when you hear deep packet inspection on the ASA or something, just know it's also referring to application inspection. That's DPI. One of the weaknesses of the application inspection is that it requires greater processing power. Now we have seen the 4 different types of firewall technologies and the Cisco firewalls that we're going to be looking at in this CCNA series. That's the Cisco iOS firewall and the Cisco ASA. That's the Cisco ASA. ASA stands for Adaptive Security Appliance. Now these firewalls implement packet filtering. That's the static packet filtering, like stateless packet filtering, so they can use ACLs. They also implement the stateful packet filtering. And finally, they can implement the application inspection. So of the 4, they don't implement proxy servers. This brings us to the end of this video, where we have looked at an introduction to firewalls, and we have taken a look at the different firewall technologies that we have, including their strengths and their weaknesses. I hope you have found this video informative, and I'd like to thank you for watching.
In this video, we'll cover the basics of 802.1x, including device roles and the authentication process. Normally, when someone connects their laptop to a LAN port, they are automatically given access to the network. So that's assuming that DHCP gives them an IP address or they statically assign one. It's the same thing when someone connects to the wireless network. That's assuming they know the key to connect to that particular SSID. But what we see is that organizations usually want more visibility into who is connecting into their network and also control what those users can do while on their network. Now this is where 802.1x comes in. It provides identity-based access control at layer 2. To put it simply, what 802.1x does is, when you want to connect to the network, say wirelessly or using a cable, some form of authentication will take place before you can connect to the network. So it could be username and password, it could be using certificates and stuff like that. There are 3 device roles when we're dealing with 802.1x. The first one is the client device requesting access to the network. That is known as a supplicant. The second one is the authenticator or policy enforcement point. That's PEP. And this could be a switch, a router, an access point, or anything like that. And finally, we have the authentication server, which performs authentication and authorization for the client's device. The Cisco Secure ACS and the Cisco ISC, which we have already seen, are examples of authentication servers. Let me give you a high-level overview of how 802.1x works using this diagram. Initially, when the supplicant connects to the switch port, all traffic is denied except traffic that is necessary for authentication. So for 802.1x, IP over LAN, IP stands for Extensible Authentication Protocol. IP over LAN is the protocol that we use to carry authentication information between the supplicant, that's between the client device, and the authenticator. Authenticator in this case could be like the switch, the access point, or the router. There are various authentication methods that we can use, such as PIP, IP-TLS, IP-FAST. Some of them require just username and password. Some require server-side certificate. Some require both server-side and client-side certificate. Now, when the authenticator receives the supplicant's authentication information, it relays that message to the authentication server using radios. So authentication server could be like the Cisco ISC. So the authentication server will perform 2 basic functions. One, is the user's authentication information correct? So maybe is the user's username and password, is it correct? And 2, what level of access should the user be given? So this can be placing the user in a particular VLAN, or you're applying certain access lists to such a user. If accounting is configured, the authentication server can also keep an audit of what the user does while connected to the network. So let's assume that the user successfully authenticates and is successfully authorized. Then traffic begins to flow normally through the switch port. Depending on how the authenticator is configured, the user may be placed in a guest VLAN or a restricted VLAN if authentication fails, or if the user does not have a valid 802.1x supplicant. Now at this point, it's important to note that not all devices have valid 802.1x supplicants. So for example, devices such as printers, you cannot use like a username or password to connect them to the network. One way we can authenticate such devices is to use MAC authentication bypass. From the name, you can see that it's not really authentication as such, since we are bypassing 802.1x authentication. But MAC authentication bypass, that's MAB, it basically authenticates using MAC addresses. This brings us to the end of this video, where you have been introduced to 802.1x. We have seen the different device roles, that's supplicant, authenticator, and authentication server. And we have also seen the 802.1x authentication process. I hope you have found this video insightful, and I look forward to the next one.